So, good morning, everyone, in this lovely, normally nice world, which is a little bit out of order at the moment. Nevertheless, due to electronic support, we still can connect all over the world. We got more than 100 attendees. That's really great. And what I really feel great about, from 35 countries. So it looks like we're really organizing something globally now. So welcome. Have a good day. I'm sure many of you are going to join only for some parts of the meetings, but that's totally okay. We are in Munich at the Two Süd premises here. Thank you very much. We got some coffee, some bread here, and we will have a glass of wine in the end after we survived the day. Okay. So just some words for the housekeeping. The whole session is going to be recorded. So by joining, you agree to be seen on the screen somehow. Please, everyone, keep your microphone muted. I suggest as well to switch your video camera off just for stability of the connection. To the speakers, of course, please switch your video and microphone on when you have to speak. In terms of questions, please look the chat feature of Zoom. You see the flicking light on the bottom of the screen. You just click there and we will see your questions. Just to introduce myself, my name is Axel Deike. I started in '79 at BMW. I'm an electronics engineer. I worked at BMW till 2012. In 2012, I went on my own feet, and since then, I'm giving support to all kinds of companies as an independent consultant. What is the idea here in terms of IEEE? I am supporting IEEE Europe. I'm the chairman of the Industry Connection Group. The idea of that group is to bring up all kinds of interesting issues around autonomous driving at the moment, of course, but it's not really restricted to it. We are on mobility as a service. So whatever feels interesting from all of you, please contact me. Any idea is good. So we will check whatever we can do. My program committee, you see on the right. Kashra is here as well. Thank you very much. Kashra is one of the most reliable ones, coming all the time, punctually in time. And Herman is here as well, sorry. So what are we going to do? The workshop is going plus minus all over the day. We have 4 sessions. Each session will be moderated by a different moderator so that I don't have to speak all the time and take care. The first session is going to be an update on regulatory activities and supporting standards. Some of you may remember we had 2 weeks ago, we had a webinar on that. So Hermann Brandt, for example, is going to give a summary what was communicated at our workshop. Kashra Haghigi, is that right? Okay, sorry, it's a Swedish name. He's going to be the moderator for the session number 2. Jürgen Neises, he is remote. I hope it's going to work. He's going to have the moderation for session 3, forward compatible vehicle architecture, so more to the car. Kashra is having the enabling technologies. We are going to see very interesting presentations there. And finally, Hermann from IEEE will bind up in terms of verification and validation. So, First is my friend and colleague, Alexander Kraus. He is the MD of TÜV Süd Mobility. And in the second function, he is as well the Chief Executive Officer of IMTS. IMTS, this is how we learned each other as well. It's a global initiative to bring all suppliers together in terms of testing devices, proving grounds, and such kind of thing. I love this initiative, Alex. So I'm just swapping the seat. Please go ahead.
All right. Thank you, Axel, for the kind introduction. And also let me welcome you again here, at least partially at the TÜV Süd headquarters in Munich. I believe we are all wishing that we can meet again in person and do such initiatives and events, including socializing sections and so where we can talk. Anyway, it's good having you all here. And I'm excited that we have such a high number of participants. And let me, here we go. Let me start with my presentation. And I would like, as a mobility enthusiast, since I was born, I'm dealing with mobility and vehicles, and I'm really emotional about it. But I'm also an engineer, an automotive engineer. Of course, as a German, being an automotive enthusiast, you also should be then automotive engineer, which I am, as I said, but I'm also a person that really believes that mobility should be available and has to be available to everybody, everywhere. And of course, mobility needs to be sustainable. And I believe in this technology disruptions, which we are facing in terms of vehicle technology, but also in terms of how we use those technologies. We all know that young people have a very different mindset and connection to mobility than I would have it, as I expressed in the beginning of my talk. And we see that there's a change in how we understand and use technology as well. And there's one big bottleneck, I believe, and this is that in terms of automated driving, we are facing huge testing deployments, so deployments of vehicles around the globe for testing purposes. But comparing this to the amount of investments that's done to get this technology developed and integrated and so on, this is not balanced at all. So at the end, there are very high investment costs for the industry and technology developers and you name it, OEMs, tier ones, tier twos along the value chain. And there is no scalable deployment, simply because we have a lack of standards, regulations, methodologies, which are proven as best practices, how to deploy those vehicles in a way that they can really serve society and they are working as a business model. So, and this is the major challenge, one of the major challenge. I'm afraid I don't have solutions to everything, but at least I want to give some impulses how I believe as a senior manager of a global third-party testing inspection certification company, how I believe we can overcome this gap, or at least shorten the gap and shorten the time to market for these new technologies. Let me start with the Vision Zero from the European Union. I know there are initiatives around the globe, but the vision is, as an entry slide here, that by 2050, there should be not only zero emissions, already by 2035, by the way, in terms of emissions caused by mobility, but by 2050, the aim is that there are zero traffic fatalities. And of course, getting there is an evolutionary development, but for sure, automation of driving functions as well as connectivity of vehicles is one of the major, or two of the major technology solutions to get there. As I said, to support this vision, which was just an example, as I said, we also should think of that technology needs to serve society. And I say that probably many times, but I really believe in it. It cannot only be business models, even they are, but at the end, Such a vision can only be achieved since human driver is not perfect and makes mistakes, gets tired and so on. We can only solve this by developing and integrating new technology solutions. And there are many, I mentioned it in the beginning, so we are facing technology disruption, as I would say it. So since the introduction of the combustion engine, there was probably not a real challenge. From an engineer perspective, we are always very proud about new technologies, but at the end, really to bring society to the next level, we see this disruption now by getting vehicles connected more and more. That is basis for a full-fledged automation of the driving function. Lateral, longitudinal dynamics need to be automated, and this is going on, and we measure it, or we define it by the SAE level 0 to 5 as an example. And of course, to get it sustainable, we also introduce electrified drivetrains to reduce CO2 carbon emissions. And of course, we want to reduce number of vehicles on the roads. So not everybody, and I'm living in Munich, I'm talking to you from Munich. And despite the COVID crisis, I have to say, I see on the motorway each morning, big, large, huge cars, SUVs, and so on. There's one person in each car, which is probably a bit accelerated through to COVID, but it's really stupid, I have to say at the end. We need to reduce the number of cars because of this traffic congestion as well. It costs us nerves, as I would say, so it's not very comfortable. But of course, it also consumes time, which is useless time, as long as we cannot do different things in those vehicles, or we share it as a community. So introduction of new technologies is happening, is necessary to enhance society with the vision of having sustainable, so emission-less, no emission mobility, but also having zero fatalities due to traffic accidents. And you are all experts. Anyway, who knows me, I showed this slide several times, but it's always impressive again to me. And I think even as an engineer, we forget about it. And I know how the automotive industry works. So there are engineers, they are really focused on their subject matter. And there are only a few who see the full system and understand the full system. And as a consumer or as a user of those vehicles, I would even say, I can talk about my wife, my kids, my family, my friends. They just sit in the car and expect it has to work no matter where you are, from Singapore to Sweden or so. It has to function. And just doing a benchmark and show the complexity of those vehicles already today, and this complexity is increasing by more and more software-defined vehicles. Forgive me. So comparing it to Windows 10, which has around 100 million lines of code, no sensors which are really life relevant, let's say, no actors, and all the system is running in one place. We know they are connected, we are using cloud and so on. But anyway, the laptop itself is 100 line, or the computer itself which runs on Windows 10 has 100 million lines of code, more or less. Compare this to a modern vehicle. We have round about the same number of lines of code. This is increasing, as I said, by more and more software-defined vehicles. But rebooting is definitely not an option. You don't want to have your car rebooting due to a software update or whatever malfunction or so. While you're driving somewhere, this would be a disaster. So it has to be functionally safe. The complexity is even higher since you don't have everything running on one engine, but it's split up to different sensor sets, to multiple microprocessors that have to be integrated. And if you look at the supply chain, we have tier N to tier 1, and the OEM integrates everything, at least for the traditional technology. And probably we all know that some of the systems that are delivered to the OEMs are black boxes for the OEMs. So how can we manage that complexity? That's a big question. And not to say the number of data that is generated in such a vehicle is really huge. And when we're talking about connectivity, which we probably need to have full automation of vehicles, we have to get this connectivity done as well, and have to have an infrastructure that is able to send all this data in more or less real time. And just last but not least, on the very right side of this slide, you see a complexity benchmark, and this shows that, and we should not forget this, that the vehicles already today and in future, as I said, even with higher complexity, are the most complex systems, technology systems on this planet. More complex than a space shuttle, than an airplane, than a hard lung machine or whatever. It's the most complex systems, and they have to be safe. And that's a good link to what I would like to say, just as an example as well. I'm sure I don't want to bash any OEMs, so don't get me wrong, but it's important to show some examples. And this is randomly taken these examples. But we see with implementation and introduction of this new technologies, last but not least, through this increasing complexity, we have diffuse safety threats. We see cars suddenly crashing somewhere. We have hackers that are able to take control of safety relevant functionalities of a vehicle. And to bring it to the point, I mean, we try to keep this technology under control, but if we have that vision of zero fatalities, this must not happen. So, and the question is now, how can we control quarters today? I take the liberty to also give you one of our DNAs of TÜV Süd, which is a global testing, inspection, certification company. Our business model and our DNA is safety of technology. And we do this with more than 25,000 people around the globe in all industries you can imagine. So we are doing this from textile through nuclear power plants to automotive and automobiles. And this is my profession, as I said in the very beginning, and it will always be. And I really believe that technology can solve many, many issues, but at the end, it has to be safe. And what we're doing inspections, testings, run the right test infrastructures, execute the right tests to prove vehicle technology and any other technology safe against existing regulations and standards. And if there are no standards or regulations existing, then we have to deal with it as well. And this will be some of the next slides I'm going to show you. In terms of automated and connected driving, the good news are it's possible to deploy them, but the bad news are only as individual vehicles so far, and only for testing purposes, more or less. There are some exemptions, but these are some examples I would like to show you. This is customers of TÜV Süd, where we have done by individual type approvals around the globe. This is from Israel, from Germany, from the United States. We have done single type approvals for those vehicles, but to make it very clear, this means each single unit needs to be individually certified. And this doesn't make any sense because the effort is super high. So you don't want to do that. You want to come to a level where you can do homologation, which means you get by testing one vehicle or proving safety and environmental protection or friendliness as much as it can be of one vehicle, you get a certification of a full fleet. This is what we want to have, but it's not possible yet. And this is really hindering the deployment of technology. I mean, there are some, at least I can remember one OEM, I will not mention the name, maybe you know, who is doing something in the gray area by deploying an autopilot, which causes threats. I mean, we don't want to have that. Yeah, we want to be safe on our roads. We don't want to have our children or ourselves being threatened, or our society by moving objects on our streets. So what does that mean for a company like TÜV Süd, but also for technology developers? There is not only a revolutionary change in the mobility setup in technology, as I mentioned, with some examples, but also how we validate safety and safety function of those vehicles is rapidly changing. I mean, just the example, so far in the traditional industry, what we do is physical testing. Validation is done by you do brake tests, you do crash tests, you do whatever, active safety testing. You have to consider functional safety of brake and steering system as an example. But this is moving more and more to the virtual world, just because of the sheer number of possible scenarios that such an automated vehicle has to deal with is so extremely high. That we cannot do it by physical testing, because just from the distance, we would have to drive from Earth to Sun and back, which doesn't make sense if you imagine. I mean, then development times are forever. So there are big changes. And another change I would like to mention is that it's not as it's done today. So you do type approval testing shortly before start of production for a market, but you will have systems that are constantly changing, as an example, through to software updates at a later point of stage. So when they're already deployed. And then this will create a huge individualization of each unit of a vehicle. And it also requires to do type approvals of software updates, as an example, when the vehicles are running on the road already. So, and what I would like to highlight, and this is why we have so many friends here today with IEEE, with Axel, who is supporting. We are working closely with SAE, with ISO, with Katak from China, with the DIN, which is the German Institute for Norming, and so on and so on. We are also working with UNECE, because we need to have a harmonization in terms of time and content and global reach of legislation, which sets the legal requirements of regulation, which works on standardization and harmonization of requirements down to industry standards. If this is super diverse, how can, as a technology developer, how can you deal with this, with the technology that takes billions and billions of development investments, and then you have to fulfill probably around the globe for your deployment thousands of regulation standards and legislation? It doesn't make sense. I mean, that's a matter of fact. So we need to harmonize. Let me give this in another picture, and you will see my colleague Alex Schwab also talking about it later in more detail, so I will not stress this too much. But technology development on the top line is going on, and it's just at the end a question of what is physically possible. That's one barrier. And how much money we put in development of technology. So this is the two barriers. And there's a lot of investments, so this goes on. And since it's more and more software-based in a very traditional, long, old industry, which was very hardware-based, this is accelerating like hell. So software updates are just coming faster and faster and faster. And if you ask me, we will see even new business models in the near future that you can, on demand, buy you for 2 days 50 more horsepower, as an example, just by getting a software update, as an example. So this is rapidly increasing in terms of speed and complexity, as I said. Versus this, we have industry standards. Forgive me, I forgot to put IEEE in here. Of course, IEEE is a key player here, but also ISO and SAE and UL, and you name them, there are so many that give us ideas how we can do and prove safely and standardize those developments. And of course, at the bottom line, there are regulations like the UNECE regulations, as an example. We have others as well. We have the United States with NHTSA, and we have China and so on. But this will be explained by my colleague a bit later. But this is what needs to be fulfilled. But at the end, this is the very basis. So we want to be better than the regulation at the end. Yeah. Time? Okay, good. So, and just one picture I would like to show, and as I said, I will not go in detail, but because my colleague will talk about it later, and you will get really a deep dive from his perspective, and I can only recommend to take a look at this presentation because it shows you that complexity. So at the end, what we see is just on the bottom line. I mean, on my picture I showed before, that the regulations are completely not harmonized. And this is just Europe. And now imagine yourself, you are one of the OEMs and you want to deploy your vehicle to the European market, which you have to do because you want to run it as a business model and you want to earn money with it. And you cannot keep investing forever without selling those vehicles. So at the end, this is the diversity of just across Europe, and it's getting more complex around the globe, of the readiness of level 4 plus market deployment regulations. And this means, I mean, in a nutshell, if you are an OEM and you want to deploy your vehicles to Europe, you cannot if they're level 4 or 5. You can do it probably very soon in Germany. We know there is the first level 4 regulation is just before to be in place. And this would be possible, but for the rest of Europe, not. So what you're doing when you go to Austria, you need to turn off your automation and you need to drive yourself, as an example. So it doesn't make sense. So why would I buy it and invest into this technology without having this basis? So, and another subject is I would like to mention quickly, which more addresses the industry standards. Even we are having, and we are proud on that as Germans, that we have the first level 4 regulation in place. But frankly speaking, no one knows what to do. we can have an idea about it, but there was not done a single type approval for level 4 or homologation for a high number of people. And if you ask the German authority, the Kraftfahrtbundesamt, that's the Federal Ministry of Transport that gives the certification for homologation, or to any technical service as we are all a little bit desperate here, because no one really can say, okay, I take the responsibility and do a technical report, and they grant permission, and then suddenly something happens. So there is no best practice in place, even we have the regulation. So that's the second thing we have to deal with. 2 points: diversity of regulation combined with lack of standards that tell us what to do, and no best practice. Okay. So, and with the absence of this complexity coming from technology, but on the other side, with this vast variety of rising industry standards and the vast variety and not harmonized situation with regulations, we made our mind up with many friends. Again, with Axel, with Hermann, with Konstantinos from IEEE, UNIXEC, we know each other also very well, and you joined this initiative as well. Couple of years ago, with SAE and so on. You will see it on the next slide. We made our mind up and we said we need to close that gap, and we need to find a way how we tackle this issue of not harmonized standards and regulations. And we started with the standards, and we said, let's share best practices from a global perspective, work out best practices and write them into de facto standards, which then can be used for the official standardization committees to harmonize and accelerate standardization for safety validation of automated vehicles and connected vehicles. So, and this was the birthday, I have to say, of the IAMTS. It's not standing for IMTÜV Süd. You could imagine that, but it's standing for the International Alliance for Mobility Testing and Standardization. And that's a coincidence. BMW made me aware of this and said, I get it. This is IMTÜV Süd. No, it's the International Alliance for Mobility Testing and Standardization. And as you can see, I'm also the chairman of this initiative. It's a member-based initiative. And you see all our friends here, our members on that slide. We are growing despite COVID, despite political crisis. This started in 2018. It's a membership-based initiative. Each member here pays a decent amount of membership fee every year, and it's non-profit, so nobody gets paid for it. Nobody earns out of this any money. This is really coming from the deep belief that mobility needs to serve humanity and makes only sense if it's safe and available to everybody. And this is the idea of having a team of SAE, IEEE, Qatar, DIN, all the TÜV organizations, and even the European Technology Chamber, which is close, NGO close to the European Union, but represented globally. We work on best practices jointly with all these technology members as well. How to validate and what's required to validate safety of a level 4 or 5 vehicle, or even 3 vehicle for deployment. So, and we have interlinks to institutions like the CETA, which is the global association of all the third-party institutions that stand for safety of technology. With ASAM, for sure, you know ASAM, Klaus Estenfeld supported us as well from day one. To not do something completely disconnected from development standards. in the industry. So there's a strong collaboration here. And as I said, we use then the competency, for example, of IEEE and the others, of course, to put this into documents that are white papers, specification documents, and so-called de facto standards. And we publish this as one team. Just to mention it, we have very high level attention here, as well as you look at our executive committee members, the persons that are mentioned here, as well as the technical leadership committee. We have Professor Dr. Wu, who is the vice president of Qatar. He runs the operations of the Chinese, let's forgive me, company TÜV-like company, and they're a very good friend of ours. We have John Tinninelli from SAE. We have Klaus supporting us from ASAM. We have Georg List himself from AVL running our technical committees. We have the very, very strong support from Hermann, who is here in this room from IEEE, and also Konstantinos Karachalios, who is the managing director of IEEE globally. So you see there's very high management attention to it. And then we have, of course, our working group leaders, which I have to say do an extraordinary job, because they do this despite their daily jobs at their home organizations at night and on weekends and in free time. And this is how this works, and how IMTS works, and how I really believe this will is very important work we are doing here, and it will not, but already does have an impact on harmonizing standardization. So we are working in working groups. We have 4 working groups. Working group 1 is working on the global scenario library. So what is a scenario? How does it need to look like? And how can we put it in an available, and I would even say discrimination-free library that is accessible and not hosted by single OEMs, single regions or so, because this is then it's in a silo. So we need to open this. Working group 2 is dealing with what global infrastructures in terms of test beds are available. And we put this in a database so that test beds and infrastructures that are usable for validation of level 3, 4, 5 automation are known and can be utilized. Just imagine how much investment it is to run your own test bed, which is so far state of the art in the traditional automotive industry. Let me take Daimler as an example. They have invested €750 million in a test bed here in Germany. And it's not this is not including operational costs. I don't know how high they are, but this is really crazy. And if all the OEMs do this and all the suppliers have to do it, it doesn't make sense. Why don't we use what we have and improve what we have? And this is the task of this working group. Then we have working group 3, which is dealing with one of the most, I think, subjects that is driving probably all of us, which is the correlation between physical and virtual testing. I mentioned it, having automated vehicles, level 3, 4, 5. They have to deal with all the different scenarios. And if the sun goes down and I'm driving my vehicle which has the newest version of the ADAS systems, and the sun is low, I'm driving like a drunken person across the motorway, if I don't take control myself. So we have to have simulation tools that meet, at least in a defined tolerance, physical testing to be used as one of the most important tools for development of automated vehicles, but also for the validation of automated vehicle safety. And of course, cybersecurity, I talked about it, they're all connected, and they really need to be more and more connected, those vehicles. And we must understand how can we do efficient and harmonized cybersecurity testing for deployment, and not a different thing in each single country or even region where you want to deploy such a vehicle. And of course, study group 5, which is also important. I'm proud on that, because all the other TÜV organizations, competitors of ours, of TÜV Süd, are also collaborating with us here and with the whole team in how to do vehicle lifetime compliance for type approval and for periodical technical inspections, or even how to deploy software updates, which might be safety relevant even after the vehicle is on the road for 2, 3, 4, 5 years. This is how we work. So it's all done by working groups. There are approval processes inside IEMTS because this is a democratic system. Yeah, so it's a membership-based organization, so there is no CEO who can give order. We need to decide jointly as a team here. Then we form working groups that are delivering output within 3 to 12 months, and the output is specification documents, papers, which we would call de facto standards, which then can be used by our members, by Qatar for China, by IEEE, by SAE, by DIN, and so on, to put it into real official standardization. And that, of course, has an impact as well, because we are also members of UNECE as an example, and we are in the WP29 working groups. And so if we have a consensus here, which is built on facts, we will also drive this into and we are doing this, we will, through our members, automatically have that common understanding in the official working groups for standardization and regulation. So to come to an end, it's not a question if this is not my note here, but it's not a question whether we can trust technologies on the roads. The question is really, can companies and regulators develop such technologies at all? And to get there, I always want to show this triangle, which I really believe is important. We have the technology and function development. As I said, it's a question of physical limits and of how much money to invest. Then, of course, we have users' acceptance. So we must not develop technology that nobody accepts because it is not safe, or it is not usable, or not available, or not affordable. So we must not forget the end consumers. If you want to drive in an automated vehicle, you don't want to go like a drunk person. You don't want to get motion sick in that vehicles, and so on and so on. So this is an important subject, and it needs to be validated safety. And to get there, we need harmonized standards and guidelines. Otherwise, it will simply not happen. So thank you for listening. And if you have any questions or so in the afterwards, please, here's my email address, reach out. Always happy to connect with people around the globe which share my passion. Thank you.
Thank you very much, Alex. It's always a pleasure to learn to know more and more about the world and the challenges ahead. Thank you. So I'm just under the impression still of Alex's speech. Plus, I joined 2 days now, a big conference in Stuttgart this year, normally at Ludwigsburg. Yesterday, 2 days. Really impressive presentations, all kind of CTOs and top managers there from BMW, from Daimler, from Aurora, from AutoX and Qualcomm and whoever. The key question there was L4. And of course, nobody knows really. We are going to learn from Hermann where the regulation world is standing, and Alex, or Alexander, I don't know how you want to call it, okay. We will have even a deeper insight. Just to give you some impressions of that big conference, really, the OEMs, the statements given there were quite easy. The car of the future will be not driven by a car, but by software. The whole industry is changing structures. VW, for example, set up a software company called Car8, where 10,000 engineers, software mainly, put together just to show all the power. BMW did that some years ago already. So the whole industry is reorganizing really for the challenges in terms of software. Yeah, it was mentioned already how to homologize, how to self-certify in United States a vehicle on L3. We are talking L4 here. Even L3 is not clear. But nevertheless, I can't say which one, but one of the CTOs in Stuttgart said there will be the first car going to be homologized in Germany. Okay, I can say it, Mercedes, the EQS, which is going to be the first car certified on L3. Unfortunately, only with 60 kilometers per hour maximum. That's okay, or at least in city. Okay, we will see how it goes further. From the AI companies, most interesting statements, unbelievable what Aurora and AutoX is doing. AutoX, the MD, he's called Professor X, an ex-MIT professor. He showed presentations I couldn't believe. Till yesterday, I would have sworn that it's not possible to drive automatically through a Chinese, small city area, big city, but small roads with all the pedestrians and roller coasters and whatever. It's so chaotic, but Aurora can make it. He showed a film, a video where in European terms, the automized car was going through the pedestrian zone of Munich. He even reversed when another car was in the way. Unbelievable. 500 people there just were looking with open mouths what this company can do. And of course, not to forget the semiconductor industry with NXP and Qualcomm mainly here. What kind of semiconductor power, which is pushing this software in the end to a level of capabilities, which is just unbelievable. 5 nanometer technology is going to come. I forgot how many billion of transistors are on one chip now, but this power is really, really enormous. And just to come back to Alex's presentation, how to make it really reliable. One of the experts did put it in a picture. The picture was 1 failure per car per 10,000 years. That's what we have to prove. I think that makes it very, very clear what the challenge is. And it starts, of course, with regulations and standards. So, Hermann, now it's your part. Hermann Brandt is the CTO, or managing director of IEEE in Europe. He's coming from the communication industry. He worked there for many, many years, and he's running the IEEE setup in Vienna, and he's going to give us an overview of the regulations and standard as it was presented by SAE people, by UNECE people, by IEEE specialists at our webinar some weeks ago, in end of October. Please start.
Thank you, Axel, for the kind introduction. So I'll quickly move to the next slide. Now, well, okay, so yeah, my task here now is to reflect on the webinar we had. We had a webinar on the 27th of October with, you see, Bill Gauss from SAE. So he gave an overview about what's going on in UNECE, mainly work package 29, but also work project 29, but also 1. We had John Tintinelli from SAE Europe to talk about ongoing standardization activities in SAE International. And I made an overview about ongoing standardization projects in IEEE, of course, all related to the challenge of digital transformation of the transportation industry. Before I start, according to the IEEE Standards Board Operational Manual, I have to say that please regard what I say as rather as personal views and not as official statements of the IEEE. So now let's go into, the overall idea for this webinar was do a sort of first standards landscaping exercise. And of course, standards landscaping, it's not easy. There are so many bodies being active, and nobody really has an overview, and it takes a lot of time to gain some oversight. And so I want to start here by looking into one of the many initiatives, and this one even funded by the European Commission, to look into the standardization landscape. So that they looked into, or they identified 15 organizations which are most relevant, including SAE and ISO and IEEE and others, of course. And what they saw is clearly there is an enormous increase of published standards since 2014, as you see here. So up to 2020, last year. So the number for 2021, of course, it's not the latest version. It counts all the published standards up to August this year. So it's not the final number, and that's why the drop here is not really serious. What's interesting, so they say 175 standards in the field of connected and automated driving have been published, 51 still under development. And from this 175, they say 75 are about connectivity. 25 are about verification and validation, and the others about ADAS. And they also interestingly identified some gaps, and the major gaps they say are about perceptions or automotive sensor performance standards, and also functional architecture standards. Why do we expect more standards even in the future? And this is already pointed out by Alex in the previous presentation. So the digital transformation of the automotive industry, driven by information and communication technologies. And it's really a cross-sector challenge. And there are so many rapid technology innovations in the industry and in the research communities. There are many new incumbents and many new entrants, and of course the old incumbents investing a lot of money, and there are diverse policy priorities in different regions of the world. The standardization landscape is an ecosystem of its own. And what you see here, it's really about IEEE and SAE. So the automotive and the electronic engineers, and electronic engineers means these days microelectronics and software engineers, they have to join forces to tackle all these challenges. And of course, I said the standardization landscape is an ecosystem of its own, because there are different bodies. And there are, first of all, at the bottom here, there are industry alliances developing best practices. One example here is IMTS. Other examples, so IMTS is really the industry alliance where SAE and IEEE jointly support all the ongoing work. But there are others. So, for example, the Automated Vehicle Safety Consortium from SAE, ITC, or the MIPI Alliance from IEEE, ISTO. And And of course, SAE and IEEE, we both are, so to speak, formal standards bodies. So we work according to WTO principles and are recognized to support legislation. And we work closely, jointly with ISO and IEC and others. And so the nature of all these deliverables is different. So the standards basically are anyway voluntary consensus agreements. But in the sense they support legislation, the requirements in standards are mandatory. So it's a bottom-up process of developing a consensus about key technical issues and to eventually integrate those consensus standards into regulatory frameworks. And the idea of IEEE, for example, is to make those standards globally applicable and to be flexible in terms of adoption by different formal standards organizations, and to help to integrate those standards into diverse regulatory regimes. Now let's get back to the three bodies, so UNECE, and we will hear more detailed analysis of what's going on in the next presentation, and then SAE. And of course, it's really a difficult task to give an overview about standards, because standards, there are so many numbers, there are so many titles. So I would rather focus on work areas and maybe also highlight what's going on and include some timelines so that you get a feeling. And please regard the numbers here rather as hints to look into more details. So it's really a sort of hook if you are interested to investigate further. So let's start with UNECE. So as you might anyway know, the Inland Transport Committee, they made a decision for, I think I remember 16, and invited VP1 and VP29 to look into automated driving, to say it more generally. And you see, already in 2016, there were 2 milestones were reached to open up the regulatory framework for automated driving. On the one hand, to open the door to allow automated vehicles in traffic, and the other one to remove the 10 km/h limitations for autonomous systems. And so most of the work nowadays is going on in GRVA, in the Automated and Autonomous and Connected Vehicles group. This slides depict some of the deliverables of UNECE. So you see the cybersecurity, the automated lane keeping. So we will hear more about that in the next presentation. Software updates, and the very good master document of the new assessment test methods for automated driving. Now, brief overview about what's going on in VP1. You see here the link to the report where you find more information. It's interesting to see, so the first one, the resolution on safety considerations for activities under the driving undertaken by the driver when the automated driving system is exercising dynamic control. This is more about the transfer of the driving task between a human driver and the automated driving system. The second one is about a remote driver, and the optical and audible signals. This is interesting because it's about how the car or the automated driving system should interact with a human driver who will be a passenger somewhere, and also how to interact with other cars and with pedestrians in the streets and so on. A new group of experts was established on drafting a new legal instrument on the use of automated vehicles in traffic. So I understand they will have their first meeting in November and another one so they are just in the initial, let's say, kickoff state. So they plan to have a second meeting in December. So by the way, these slides are based on the presentation of SAE from the workshop, from the webinar in October. Yeah, now touching upon VP29, these are partly task forces, informal working groups, special interest groups on the automated lane keeping system, the cybersecurity and over-the-air issues, advanced driver assistance systems, functional requirements for automated vehicles, validation methods, and data storage systems. And I understood artificial intelligence is in the context of vehicle regulation. So this is an upcoming new initiative, which is not yet official according to the information I have. There is a good framework document outlining also principles, and the link is here, and also the meeting. There is a link for the meeting calendar, so for those who are interested to follow up on this work. Yeah, here is just some information about timelines. So the functional requirements of automated vehicles, they meet again next week, I think, in November 2021, and the plan is to endorse in March next year the validation methods for automated driving. So this is they highlight three different aspects here. One is behavioral competencies of an autonomous vehicle during normal operation, performance during crash avoidance situations, and performance of fallback strategies. The approach is a multi-pillar approach, so they have in mind simulations, track tests, on-road real-world tests, audits, in-use reporting, and so on and so forth. They plan to have guidelines available for endorsement in next year, in March 2022 and June 2022. The other one, the event data recorder, it's even further down the road. It's determined to be, I'm not sure whether endorsed already in November next year. So and of course there are ongoing discussions for what's the difference. So what should be in the event data recorder? What should be recorded to have evidence in case of an accident, and what is used, what needs to be in the data storage system for the operation. Now, a quick look at standardization activities in SAE. And to start with, maybe it's useful to look into one of their most used publications. It's not a standard, it's a taxonomy. It's a document to define some important terms. And what is defined in this document for level 4, it says perform the complete dynamic driving task and also perform the dynamic driving task fall back within a limited operational design domain. And of course, so the discussion about L4 level of automation, it's very much about this dynamic driving tasks, and also what is the operational design domain and how to define the operational design domain. And I think we will have more information about that later today. Yeah, as already said, it doesn't make sense, and we don't have the time to look into all these different standards. So it's rather highlighting the work areas, the focus areas, as it says here. And you see there is more going on for terms and definitions, security, safety, interoperability, the human factors, driver interface, and also test and verifications, besides vehicle system performance requirements. More concretely, you see some work in progress. Again, some informational reports, some best practices, some taxonomy. So for example, the first one, the automated driving reference architecture, it's thought to be a best practice document. So if you are interested, you may look into these projects at the website of SAE for more information. A very interesting work area is cooperative driving, and it goes with cooperative perception and cooperative infrastructure. So intelligence in the vehicle and intelligence in the infrastructure, and how they cooperate and jointly enable higher levels of automation. Yeah, and of course, for these scenarios, communication is very important. And you see here various classes. So it's also about defining messages to be communicated, to share status, to share intent, and to share and actually I see there is a mistake here, and also to give over control to a vehicle. The last one, cybersecurity guidebook and the cybersecurity engineering. So this joint standard ISO SAE 214/35/34, it's anyway one of the important standards nowadays to be considered. And of course, again, there is more work going on. Also, for example, for trucks and buses and ground vehicles, telematics, and so on. So with that, I'll go to the IEEE. And the IEEE, yeah, in fact, the standardization activities in IEEE are much broader than just road. So we cover airways, we cover waterways, we cover railways in particular for high-speed trains. The work for road transportation is organized as a mobility practice initiative with three work streams. The first one being most relevant for the topic today, the automated driving. It's called the Smart, Safe, and Trustworthy Transportation, Zero Accidents Vision. And it's very much about data engineering for AI for autonomous driving, and sensors, and a few more topics I will discuss in the next slide. But first of all, we said ICT, information communication technologies, are driving the digital transformation of the automotive industry. And of course, IEEE standards are foundational for the internet, so the communication standards, and ICT is in the DNA of IEEE. So there are many different activities and available standards and expert communities to be leveraged to address the needs of the automotive industry. So I regard these expert communities as a huge potential to be used for the needs of the automotive industry. And I touch upon a few competence centers here, like microelectronics and electronic design, software and systems engineering, testing, conformity assessment, the connectivity at the physical layer, but also at higher layers in terms of cloud and edge computing and software-defined networks and network function virtualization. Then at the next level, information modeling, data interoperability, and data governance activities. And of course, also making sense out of data, deriving information out of data by big data analytics, and using data for training machine learning algorithms in the broader context of artificial intelligence. Not only machine learning, but much more. There is the instrumentation and measurement society, very active in sensors, and of course all the many of these communities, they look into how to apply these technologies for the automotive industry. Coming back to gaps of standards, so I mentioned already vehicle architectures, functional architecture standards, which is mentioned here. Of course, there are more organizational and process standards needed. And already mentioned also and identified by others, technology enablers, which will be the second session after this one, including sensors, AI techniques, communication, also high definition maps. So it's always said, so there are standards missing to harmonize various functions for high definition maps. And of course, intelligence is not only in the vehicle of the future, but also in the infrastructure. There is a significant role for road operators in the future, not only to provide physical infrastructure, but also digital infrastructure. Here are some examples of ongoing IEEE standardization initiatives. So you see the time-sensitive networking, automotive Ethernet. So, and we will hear more about that in other in presentations later today. Then the sensor topic. So there is ongoing work on camera system image quality, LiDAR performance, radar performance metrics and testing. And there is some very relevant safety related work, most prominently the assumptions for models in safety related automated vehicle behavior, the P2846, but also, as I already mentioned, the chip level, the microelectronics level, so the exchange interoperability format for safety analysis and safety verification of IP socket mixed signals integrated circuits, the P2841. Yeah, to conclude, I want to mention some other examples how to leverage the expert communities in ICT for automotive purposes. So the first one, the federated AI, federated machine learning, then the distributed ledger technology and connected and autonomous vehicles in vehicle augmented reality. It's also a very interesting application area for yeah, mixed reality, in fact. Then yeah, the smart city infrastructures, smart city data governance, including data exchange to manage traffic by the road operators. Last but not least, the verification of autonomous systems, reliability of hardware. And recently, we started a new project, P3130, security requirements and testing methods of operating systems. So in connected vehicles. So it's more, it's the software car in mind. The motor vehicle event data standard was published in August, and they have now created a study group to determine the scope and purpose for highly and fully automated vehicles. So in response to also to the discussions going on in UNECE mentioned earlier. And with that, I invite you to connect with us by, for example, sending an email to AV for Mobility as a Service at IEEE.org or visit the Industry Connection homepage. Thank you very much.
Thank you very much, Hermann. A real pleasure. I love this global world at BMW. My time at BMW, at least 33 years, I learned how important it is to think global. And I can assure you, still today, the automotive industry is most frightened of different regulations and standards all over the world. So let's see how this is going to be unified as far as possible. What is going on L3, what is going to wait for us on L4. Just to mention AutoX again. AutoX is driving around in Shenzhen with 1,000 vehicles operational as taxis, freely available for everyone without driver. And of course, Alexander, there's no regulation there. The regulation there is just that Xi Jinping just said, do it, and even gave a lot of money. I just thumbsucked. He must have got something like 500 million euro or so ever. They even did set up a factory to build these cars. There's redundancy in the vehicles, so it's not just on top in an engineering way to prove a concept. There is, at least they envisaged all the the standards and regulations which might come. Technology is really, really impressive. And they said there was no accident yet. Another aspect, of course, discussed very much in this conference was how the automotive industry, Mercedes, BMW, and whoever in the world is going to differentiate when everything is regulated so much. That's a good question. Nobody knows yet. You have to adhere, you have to follow the traffic rules. So BMW can't be faster than whatever. So we will see, but you can be sure they are thinking very, very hard how to do that. And the keyword may be emotions, how to do it. How does a car feel? And of course, they all know that this different world has to print some money somehow for them as well, which was clearly said there. They will do only what is somehow profitable. This is why I believe that the first autonomous cars will come in the truck industry or the lorries long distance in America to go from east to west or west to east. Of course, technically a joke compared with going through a pedestrian area in Munich or in China. Okay. Alexander Schwab, he is the specialist of TÜV Süd here in Munich. I think it's not too far away from here, your office. Sorry to say so, Alex and Hermann, we are a little bit of an older generation, and I love these young people engaged on autonomous driving. The future is yours. Please go ahead. Yes, I'm the oldest.
And then we were reading last.
So also good morning from my side. My name is Alexander Schwab. I think we will talk about the next half an hour about how the regulatory framework for level 4 certification will probably look like, or what's the state of the art right now. So at first, a short introduction of myself.
Young man, as I said.
Yes. In 2018, I started at TÜV Süd at the highly autonomous driving team. Here I wrote my master thesis, a method for the selection of challenging driving scenarios for AVs. It was part of my mechanical engineering study at the Technical University of Munich. And after that, I stayed at the TÜV and jumped into the technical affairs team with, the main point is the vehicle safety. And on that, I added the officially authorized expert for motor vehicle traffic in Germany from the KVA this year. Yeah, and so on. Let's jump into my presentation. At first, I will give a short introduction. Afterwards, we will jump into the activities regarding connected and automated vehicles of the UNECE, the United States, a short overview of Chinese, the European activities, and also the driving is one important thing. I will talk about it later. So let's start. At first, I will talk about the benefits of connected and automated vehicles. As you can see, the automated driving offers a wide range of benefits. For example, safer roads because accidents caused by human errors can be avoided. A second point is the protection of the environment by optimized vehicles, optimized driving routes, and so on. One very important point is, I think, the better accessibility of impaired people because they don't need driving license. They are not always have to go to the public transport or the taxi. A fourth point from my point of view is the economic growth because of new technologies, new systems, and so on. And also, not only if we don't need drivers anymore, there are also new jobs because of new technologies that have to be done and so on. But as you all know, there are still some obstacles to overcome. And what does it mean from the point of view of a testing, inspection, and certification company like us at TÜV Süd? So I think you know that slide from Alex's presentation half an hour ago. I will go quickly over it. Today we have a look on individual vehicles for approval, and yeah, they are no longer sufficient. That means we have to look on intermodal mobility. Also, vehicles are inspected at defined periodic intervals, and vehicles are only validated before they go into public, like us at TÜV Süd and another technical service companies. But in the future, this will no longer be sufficient because of higher AD levels. Here we have to look on more pillars, more multi-dimensional with vehicles, safety, functional safety, the cybersecurity, and other topics will become scope of the PTI and the vehicle approval. Yeah, also there are constant changes in the systems, and it will not only be enough to rely only on fixed intervals. We have to look always at the vehicles. We have to bring software updates. We have to look at the cybersecurity and so on. But for this, there are also convergences and developments in this area. I will show you on the next slide. I think you also know from Alex's presentation, as you can see on the timeline above, more and more new technologies are developed, like it started with the adaptive cruise control, the lane keeping, the level 2 or level 3 autonomous driving system, the ALKS. And however, the standards and corresponding regulatory basis to be able to use these technologies are still getting smaller. They are missing a little bit, but as you can see with the ALKS regulation, the gap is smaller. Yeah, for a further example for here is the AFGBV, the German Act on Autonomous Driving. I think we will have a look later in my presentation. So at first, let's start with the UNICE activities regarding automated and connected driving. As you can see on the map here, some kind of AD or AVs is always possible all over the world, for example, for testing, just for showcases, or for individual cases. But so far, there are no harmonized requirements and test procedures to roll out and introduce the technologies across the borders of more than one country. As like Alex said, you can drive in Germany, but not in Austria or France, so on. However, the international stage of regulation and standardization is well on the way to achieve this, which I would like to show you in the next few slides. Yeah, now let's have a look at the UNICE, like Herman mentioned before. The UNICE has recognized that for a successful rollout of new technologies, it is necessary to define requirements for the technical systems and also the human behavior. The legal act of the UNICE of 1949 and 1968 provides the framework for this. So there can be new developments done under the two conventions. The UNICE defines technical requirements for AD systems in the Working Party 29. And for that, the Working Party 29 has defined a framework document to create the necessary conditions for the global harmonization to enable autonomous driving all inside the UNICE. The special thing here is that these developments take place on the basis of the 58 and the 98 agreements. That means in detail that the created requirements and the developed test methods can be applied internationally in all relevant markets. And for this purpose, 13 key issues were created that are valid for all participating countries to establish a uniforming process. To achieve this goal, several working parties were established under the Working Party 29, which I will highlight in a later slide. One of them, for example, is the Working Party on Automated or Autonomous and Connected Driving, the GRVA. And it is the umbrella of all relevant connected and automated vehicle activities within the UNECE. So let's have a look at the GRVA. It includes 6 working groups and task forces. There's focus on functional requirements for AT functions, on the development of new assessment and test methods according to new functional requirements. I also focus on the definition of requirements for systems which collect and store vehicle data, which is now under the GRVA. Yes. The development of requirements for cybersecurity and software updates, the further development of the UNECE Regulation 157, the IEEE-SA, like higher speed, lane change, and so on. And there's also a task force for advanced driver assistance systems. Also, the Working Party 1 deals with the requirements for autonomous vehicles, but not at the vehicle level, I say, it's more on the road level. And so far, 3 regulations have already emerged from the GRVA. I think we all know them. It's the Regulation 155 for cybersecurity, the 156 for software updates, and the 157 for automated lane keeping. The 3 regulations are in force since January this year. And in the following, I would like to briefly describe the regulation for all ALKS in more detail. Yeah, with the ALKS regulation, a framework for a type approval of a level 3 system has been created. In short, it can be said that the system can be activated on freeways, highways, at speed below 60 kilometers per hour. And it does not need further driver inputs during the driving.
We seem to be having technical difficulties, so we're trying to get them back.
Hi, everybody. This is Alex speaking. So we lost connection here with the presenting computer. I'm afraid, but I need to say maybe a 5 minutes bio break will help to give us some time to reconnect. So please give us a couple of 5 minutes. So we will start at whatever time 35. So in 5 minutes. And sorry for the hassle and the inconvenience.
Okay, perfect. So if you can hear me, it would be great if you can give me a short feedback.
We can hear you.
Oh, perfect. Okay. Okay. Then I will keep going there. I think I stopped that the puzzle pieces of the ALKS are also part of the FRVA and the VMAT, and they also want to try to close this. Okay, then I will jump to the next slide. Furthermore, it can be seen that the two working groups are following a similar path, as you can see in the middle. On the left side, you can see that the informal working groups are aiming the same points. For example, the VMAT develops a new assessment and test method approach to assess automated driving systems in a whole by setting additional methods to conventional ones. Okay. And the graphic in the middle shows the overall multi-pillar approach, which is aimed by the VMAT. It's a completely new point here. But what does it mean in detail? Yeah, from the ODD description on the top left corner and the requirements, the scenarios will be founded, which will be tested by simulation on test tracks and also in the real world. Also, the audit part shown in the orange box gets input from the requirements. It considers an audit of the safety management system of the manufacturer and also of the AT system itself. Another new thing is that the multi-pillar approach considers in-use monitoring during operation to be able to continuously improve the process. Yes, in summary, the FRAV and the VMAT create an approach for test requirements. And furthermore, the multi-pillar approach extends and refines already existing test methods for virtual proving ground and real-world testing. So then let's have a look at the United States activities regarding the connected and automated vehicles. In the United States, the regulations of the US federal government are completed by the regulations of the individual states. The NHTSA specifies minimum safety performance requirements for vehicles and equipment. Also, the manufacturers must certify compliance before they are selling the vehicle. But as we all know, an AV does not meet the current FMVSS requirements. For this purpose, the NHTSA can approve a limited number of exemptions from the existing regulations. For example, a vehicle without a mirror or so on. The individual states are regulating licensing and usage of the vehicles. This means all the test releases are made by the states so far. But the states have recommendations from the federal government they have to follow, or they should follow. It's better. But as you can see, there are no harmonized regulations for AVs in the US that apply through the complete country. As you can see here on this map I displayed the use of AVs over the states. And as you can see, in some states, AVs are already in use. In some, only testing is possible. And in some, I think there are no automated vehicles on the road so far. However, there are also some applications here where a safety driver no longer needs to be in the vehicle, like I think it's in California or in Utah. Yeah, but what's the NHTSA's current approach so far? In 2017, they have published the Automated Driving System 2.0 guideline. It was followed by the Automated Vehicles 3.0 guideline in 2018 and AV 4.0 in 2020. And in January this year, they published the AV Comprehensive Plan. With this, they want to promote collaboration and transparency. They want to modernize the regulatory environment, and also they want to prepare the transportation system on AVs. Further, another part is the AV test initiative. The goal of it is they want to provide the public with direct and easy access to inform about the testing of AVs all over the states. They inform regarding the activity, the legislation, the regulation, and the local involvement of the vehicles. And they also have information about companies which are developing and testing automated vehicles. Yeah, in summary, it can be said that testing of AVs already takes place in different kinds, like in simulation, on test tracks, on the real road traffic. But so far, it's not uniformly regulated. Initiatives such as the AV test initiatives are intended to create transparency and acceptance of the systems among the general population of the stage. But the work so far is also underway to improve harmonization. It's very important, and revise the regulatory environment to enable wide-scale deployment on automated vehicles. So next, let's have a short look at the Chinese activities. Yeah, it's a very big slide. China first time addresses the strategic importance of automated vehicles in 2015 by a state council. Since then, the National Reform and Development Committee, the Ministry of Public Security, the Ministry of Industry and Information Technology, and at least the Ministry of Science Technology make series of joint and separate industry strategy, policy and development plan regarding automated vehicles. In 2018, the road test management specification for ICV, short, it's the RTMS, was released for the AV public road trial. And in 2021, it was extended to automated vehicle demonstration guideline countrywide. There's a detailed evaluation methods were defined via typical AV scenarios in the closed proving ground and relevant requirement for the public road testing and business mode demonstration with passengers or cargos. And the next step here is to further shape the law, the regulation standards to support the commercialization of the vehicles to higher automation and connected level and relevant applicable scenario based on the experience gained during the trial and demonstration stage. Yeah, but also the European Union is, of course, active in the field of the automated and connected driving. I think, as we all know, at the European Commission, the implementing act is regulating that. It regulates the application of the type approval regulation 2018-858. And right now, the highest level of an AV under the type approval directive can be the automated lane keeping system as a level 3 system. But from next year, 2022, the type approval directive will be extended by the General Safety Regulation 2.0. And in addition, a law is to be drafted that will allow level 4 AD systems under a defined operating range, also under the General Safety Regulation next year. But right now, let's have a look at the current published systems of the GSR 2.0. Yeah, the GSR includes several driver assistance systems and offers also a further step in Europe towards automation. Examples for needed systems for the type approval of next year are the intelligent speed assistant or an emergency lane keeping system. As already mentioned, the European Commission plans to publish a level 4 directive under the GSR, but so far for this, Germany, like Alex also mentioned before, seems to get a pioneer position with its own level 4 regulation and also with the level 4 directive. This level 4 directive with its scope, approval process and main requirements I will present shortly in the next few slides. So let's jump into Germany. Germany has here chosen a national single path for a law. For this purpose, the Autonomous Driving Act and the Autonomous Vehicle Approval and Operation Ordinance, it's short, it's the AFGBV, has been created. And it enables level 4 AV functions on public roads for national series of vehicles in defined operation areas. That's a very important point here. With the directive, a distinction is made between mobility as a service and another point is the individual transport. The focus of the AFGBV is more on test vehicles and less on individual vehicles. Nevertheless, that doesn't mean individual vehicles can't be placed on the market. This also will be possible. Furthermore, a third point are the later activatable functions that are considered in the AFGBV, but so far they are not defined in detail. For this purpose, there are requirements from the regulation that I would like to describe in the next slide. Yeah, as you can see here, there are different requirements for the vehicle. The focus on the functionality, on the test and validation methods, the data storage, and the cybersecurity. As you can see, the requirements of the AFGBV are comply to the specifications of the UNECE or like the European Commission. And these are supplemented by requirements for the owner and the technical supervision of the automated vehicle, which is always necessary. That means that a person doesn't need to be inside the car, but a technical supervision always has to be in the backup of online that can overtake the vehicle. Yeah, the AFGBV is parallel to the German road traffic regulation, the STVO, and the road traffic approval regulation, the STVZO in short. And it is appended under the Road Traffic Act, which has become an update for level 4 and level 5 driving in July this year. In detail, this means that the German road traffic law applies in the same way like on other vehicles without an automation. But let's have a look on the process to get a vehicle on the roads right now. Yeah, on the way to the operating license, there are 3 bodies involved in the release. The first one, or the highest authority here, is the Kraftfahrtbundesamt, the Federal Motor Transport Authority, which deals with the release and the permission of the automated vehicle and the general operating license. It has no focus on the operating area and where they want to drive and so on. The next body involved is the road traffic authority or the local road traffic authority. No, it's the state department, the state traffic authority. They regulate the operating area and where the vehicle should drive later. And the third party involved is the local authority. They focus on the license, on the registration. In short, it can be said they have a focus on the license plate, and from them you get the license plate, and after that you can go on the public road. So then I'm at the end of my presentation. Let's have a short summary and the outlook. As I've shown in my presentation, autonomous driving is handled different in each country and each part of the world. But however, it can be seen that in addition to local regulations, virtual and physical testing is relevant. Further, vehicles with lower AV levels are already being operated in all countries. And rather, new areas like cybersecurity and software updates are considered in all parts. But here are still some legal gaps that need to be closed. And as Alex mentioned before, I think one important point here is that we need harmonization, that you can drive not only in one country or in just one local area. It's important that you can drive in all over the world so far. So thank you very much for my side. If you have any questions or later on, you can find my email on the bottom left corner.
Thank you very much, Alexander. Great pleasure to listen to the young people. Okay, just to give you some feedback or some information from the conference, which is usually every year in Ludwigsburg. The first presentation was given by the MD of ZF. And of course, some of you may be of the opinion that the old German automotive industry, which is ZF, of course, part of, is sleeping and falling apart and going to be killed by the Apples and Googles and whatever. I can assure you this is not going to happen. These companies did understand very well what's going on. ZF changed the whole company structure really from a what is the English word for Zahnrad? Tooth wheel, from a tooth wheel company, metal company, to a real software-driven company. They are capable now to build a complete car, what they do for shuttle buses and so on. And they changed the structure in terms of sales. When I worked at BMW, most of the time we talked about a box with some little software. And the software came for free, of course. Of course, software is not for free anymore. And even ZF and Bosch made the same statement. They are selling software only as well. Big, big change in the industry. All these companies are putting together the software capabilities within their huge organizations. This was one of the main things to do. Then we had a presentation by the board member for R&D of Daimler. Same message: everything will be electric, everything will be emission free, everything we know, we understood. And a new message was as well that everybody understands in the classic automotive industry that the money will come not so much anymore from the car only to sell it, that the money has to come out of whatever kind of service will be put on the car, whatever kind of service is going to be possible by the software architecture, which has to be set up. Daimler, of course, you know, they are a big company on the big lorries, Freightliner in the United States, Daimler-Benz worldwide. And of course, I think that is common sense within the industry that the first applications will come in the long distance haul, which is easier, which is almost a fenced area, which is relatively fast to be implemented. That was stated there as well. And of course, they changed to H2. Yes, a big discussion about world architecture, Alex. Of course, everybody hopes that the regulations will not be so different in the world, that we need different architectures in the vehicles. This is, of course, something which is most frightened by the industry. Nobody was sure yet, is it going to be the same or not? Everybody hopes that IMTS and whoever in the world is hopefully globally responsible for regulations and standards is going to be successful in terms of standardization. A very strong message from BMW. They are also the board member for R&D was there. Also there clearly to see these people are getting younger. They understand software. Strong management with strong messages. Long talk about vehicle OS. I think, Hermann, we are going to run the next session in this series about vehicle operation systems. There was a panel discussions on that as well. Most interesting statements made. One of the key statements which was made, what is an OS in the car? Nobody understands it. It's complex vehicle systems in software. And of course, within the classic automotive industry, you have legacy in, you have to make a system from old as well as new. And to put that all under one standardized operational system, what is the dream, of course, for a software architect, I think that will not happen, or at least not so easily. Of course,
The management group has been doing since 1985. So I'm wondering, why is it so damn difficult to get something that has been running banking systems all over the world?
I'm not sure that you can understand in the background. It will be a challenge, very clear. This was a BMW statement. BMW puts lots of effort on easiness of use. So their statement was very clear, their differentiator, because of course a BMW can't go faster in traffic. They have to adhere to the traffic regulations as much as any other car. So emotions is the difference, how to use, easy of use, less buttons in the car, less and less language, speaking with the car. The message, which I didn't know, for example, was that 95% of all navigation use is by natural language now. Nobody uses any more controllers or whatsoever. Okay, I'm going to call you to tell you a little more later. Now we are going to have a coffee break or lunch break or evening break, wherever you are in this world. And we will set up the system newly here to get an unlimited Wi-Fi ticket here. So please wonder if we are going to disappear for some minutes. For sure, we will be coming back after half an hour break. Thank you very much for the moment. Das ist meine Maus.
Aber das passt schon.
Ja, warte mal, ich mache mal den, is going to be our session on enabling technologies. It's nice to have a wonderful regulation and standardization background, and I'm totally convinced it doesn't work without that. But we need some technologies as well to make it happen. And of course, AI is one of the most frightened technologies in the automotive industry. Why? Very easy, because nobody understands it. But we have so many people here who understand it. So let's convince us that the technologies which are available now will make it happen. I'm sure it is. Kashra is going to be our moderator for the next session. So I'm changing the seat. Kashra, it's yours now. So hi, everybody. I'm Kasra Hagigi, CEO and co-founder of UniqueSec. And today I'm going to host this session for enabling technology. Today we'll listen from different words, from sensing to AI technology for autonomous driving. And we have three wonderful presenters from different areas, from Sweden, from United States, and from China. Our first presenter will be Ms. Fahime Rafinia, which is our CTO, and she will talk about automotive radars. She is also chairing the new standardization working group, IEEE standardization working group on automotive radar and testing. So I would like to invite her to start her presentation.
Thank you for the introduction and hello. I'm Fahime Rafinia. Basically, radars and test and verification of radar has been the focus of my career since 2015. Our company began with developing radars. Then we found a solution for test and verification of radars. We have a radar target simulator in frequency domain, which I am a co-inventor of it. As Castro mentioned, I have also started in the standardization area recently. In this presentation, I'm going to talk about automotive radars and their challenges, their advancements, and validation and testing for level 4 and level 5 automated driving. And I'd like to start with a very short introduction about the role of the radars for level 4 and higher level of automation, then the expectations and demands from radars in different automation levels, the challenges and limitations of radars today, and how new radars and new radar technologies are going to rise up to these challenges and solve them. Finally, a standardization landscape and what is as the demands for this in this area. And also, I'd like to invite everyone to the newly started working group for IEEE-SA automotive radar standard. Our cars today are very complex and sophisticated systems or products, and advanced driver assistance systems and automated driving are making them even more complex. As Alex Cross mentioned, maybe they are even the most complex systems we've ever had. They include a state-of-the-art software, hardware, AI and machine learning, and sensors that feed all the algorithms with the information about the surrounding environment. Level 4 automation requires 360-degree perception of the surrounding environment around the cars, and sensors are here to do this. Here, only one type of sensor isn't enough, so there is a need for cameras, radars, and other sensors. But radars are one of the most important sensors on the cars. They are very good at measuring distance and speed. They are operating at nights. They are least affected by harsh weather conditions. And also, they are very affordable. After ultrasonic, they are the second cheapest sensors on the cars. So they are a definite must-have on our cars in the future. But the expectations from radar sensors are changing, and they are going to be more expectations from radars as the level of automation goes higher. For instance, automatic emergency braking in level 1 automation requires the radar to measure the distance to an object and activate the braking if it is below some value. If we take a look at adaptive cruise control, it is basically the car requires to detect an object and it requires to resolve objects in different lanes. So the traffic in the upcoming, in the other lanes shouldn't be detected by ACC. So a radar with a quite low angular resolution, I can say, is enough for this application. But if you take a higher level function, for example, traffic jam pilot or valet parking, not only the sensor needs to provide information about the distance and speed of all objects, but also it requires to resolve all the objects with a good angular resolution. So when we go to higher levels, the need for higher fidelity perception is more. And for a radar sensor, this means higher angular resolution and the possibility to provide a 300-degree point cloud of the objects around the car. Basically, the radars today usually have a relatively low angular resolution compared with cameras and LiDAR. This is one important limitation of the radars. Also, it has always been a very key challenge for radar signal processing to have a radar with low false positive rate. Interference is another issue which is becoming more and more important. As an active sensor, a radar emits a signal and analyzes the reflections. It is possible when multiple radars are operating in the same frequency band, it's very likely that they receive each other's signal as their own signal, and this can lead to low-level data corruption. But there are new radars coming to the market, both tier 1 and tier 2 radar manufacturers, and many startups are developing new radars with much higher resolutions. These high resolution radars are also called the imaging radars because they provide almost an image in terms of the amount of data they provide. I'd like to review some methods that help enable these high resolution or imaging radars. Theoretically, the angular resolution of a radar is directly proportional to the effective area of the array aperture or array antenna. So one very straightforward way to increase the angular resolution of the radar is by adding to the number of antennas or the transmitter channels. One way to do this is using multiple radar chipsets and use them in a cascaded way together in order to achieve higher number of channels using virtual channels. And the other way is to basically design new transceiver chipsets. And the other enabling technology is new antenna design, for example, using metamaterials. Analog beamforming has been possible with much less complexity and more availability. The other important point is the signal processing. It's the signal processing and the signal model. So typically automotive radars use FMCW signals, frequency modulated continuous wave signals, but it is possible to use other signals, for example, PMCW, phase modulated continuous wave signals. And many radars, some radars also use multiple frequency bands in order to use different penetration rate in different frequencies and see through occlusion, for example, in radars. And also AI is an important part of the radar evolution as well. I can say that almost all new radars claim to use AI in some way, for example, for pattern recognition and target classification specifically. Some radars basically mix these technologies to design even better radars. I'd like to bring some examples of some of the startups or existing companies who are developing such new radars. So we know ZF, Bosch, and Continental very well. They use Infineon chipsets or Texas Instrument chipsets or chipsets from NXP that are typically in the market. They usually use the cascade method, so they combine these chipsets. For example, you see here 4 TI radar chips that are cascaded together to achieve a more high resolution angle radar. The concept here is not to have a very big antenna size. So they use virtual arrays instead of having physical antennas, a lot of antennas in the receiver side. They add to the number of transmitters, and by maintaining the orthogonality between these transmitters, it's possible to achieve even the same number of receiver channels as you see in this picture above. Arbor Robotics and Under designed their own chipsets with many transceiver channels, with many antennas. Arbor's radar also uses uses an AI-based processing chipsets. You see here an example of the point cloud and high resolution perception that this radar can provide. Under not only designs its own chipsets with more number of transceiver channels, but also uses a different signal model. It uses a PMCW signal. And also, Vayar is another company, another startup, which uses a large number of transmit and receive signals, which leads to over 2,000 virtual transceiver channels. This is because the amount of power from this radar can go very high. It can be used only for in-cabin monitoring and short-range applications. But it's quite high resolution, I can say. And Echodyne, Metawave, and Gapwaves are the technologies that the companies who use new antenna technologies. They do analog beamforming and achieve very low angular, very good angular resolution, sub-degree, I can say. NPS is a new, newly launched company. They develop advanced driver assistance systems and specifically automated driving system. They design their own camera, LiDAR, and radar with AI-based signal processing. The radar technology in this in NPS system uses 4 frequency bands from 77, 22, around 10, and I guess lower even. So they claim to see around the corner, and they use also AI and machine learning. Oculii, on the other hand, uses usual chipsets, like typical chipsets with less number of transmit and receive channels, but the processing in this radar is working with AI, and the intelligent software updates itself and improves the radar resolution as the radar collects more and more data. So this, a lot of new radars are coming. They are appearing very fast, and one needs to verify if they are really responding to or they are really reliable for the applications and for the functions that they are intended for. So as again, I want to refer to Alex's presentation that he mentioned that the standards provide a really safe and scalable ground for both the development and deployment of of ADAS and AD, and Herman gave a very good overview of the global standards all over the world. And I want to just refer to some of the activities around the radar standardization. The frequency band and spectrum usage is already standardized for radars by ITU and ETSI. ISO has done a lot of standardization regarding test targets. For example, balloon targets in form of pedestrians, cyclists, and 3D passenger cars. There is also a lot of standardization on the functions and the overall systems. But also test scenarios are very much discussed in different standardization bodies, including NCAP, IAMS, ASAM, and SAE. Also, there is some activities about the radar itself. There is a standard draft on automotive radar testing and measuring methods by Qatar in China. They are also in this in this workshop, so I'd like to invite them if they want to join the IEEE workshop and radar standard. And then I want to mention that when we talk about radar standardization, it's very much linked to the automation level, to the type of the radar, to the application of the radar. As an example, a radar in level 5 should be able to detect vulnerable road users, which might not be really needed in lower levels. When we talk about the type of the sensor, type of the radar, it's also quite different. For example, the front radar, which is used in ACC, should be able to detect within certain ranges in order to detect targets at higher speeds and longer distances, while a corner radar basically has to have a wider field of view, and it should detect targets in shorter ranges with higher resolution. Also one radar, a same radar can have different applications, can be used in different functions. For example, cross traffic alert and blind spot detection both use rear back radar. And while the blind spot detection needs to detect targets in longer distances and higher driving speeds, the cross traffic alert should find targets that are closer, maybe smaller, for example, a pedestrian, while the car is driving in a parking lot. Another important part of the standardization should be on the effect of the interference on the performance of the radar and how the mitigation methods are effective in combating interference between the radars. And finally, the testing is one of the key factors in the standardization. We need to ensure these standard metrics that we defined are met. And there are many methods to test, but for level 4 and above, because the radars are more complex and the scenarios are more complex, there is some needed for a very agile and flexible radar target simulation and test method, which enables generating many targets, which enables generating vulnerable road users. And virtual testing, as mentioned in this workshop so far, is a very powerful tool. For radars, virtual testing is possible using radar target simulators, which basically enable testing and validating radars using by creating echo signals artificially. So there are two classes for radar target simulation. One is time domain method and one is frequency method. The companies like NI, Keysight, DSpace, Keycom, and Rodan Schwarz, they provide such solutions, and there are newcomers also like Unixec and Ulm University who provide the frequency domain emulation. And in the new IEEE-SA automotive radar standards P3116, we are going to address radar's performance under different use cases, considering different automation levels from ADAS to AD, and also define the testing methods that are going to be used for ensuring this performance metrics. There are a few companies who initiated to start this standard, like NI, Kyrie, and Unixtec, and some joined later as Keysight, Denso, and SEFT. There are others who have expressed interest. The first initial meeting of the working group will be held on 7th of December this year. So I'd like to invite everyone to go to this webpage and register and join us to assure the safety of future radars. And thank you very much for listening.
We have 5 minutes for questions.
So if there is any question, I would like to ask you to ask it on the chat box, and I will try to look into the chat if there is any question.
No. So how do you see we have the LiDAR specialist next. We don't have anyone on the camera side. We have radars, LiDARs, and cameras. I'm an automotive guy, and we like to reduce. We would love to be based on, AutoX, for example, uses 28 cameras and 6 LiDARs and whatever. That just sounds a little horribly expensive. So which way is it going to go? Who is going to be kicked out? Radar, LiDAR, cameras? Cameras, I don't think so. So
Do you want to ask this question from Elon Musk?
yeah, Elon Musk got a clear answer. I know that.
But maybe Fahimi can answer from her point of view.
Yes, I think the new radars are also going to be expensive, but not as much as I think cameras and LiDARs. So they bring very unique features to the measurements and providing the data for the algorithms. And I think I cannot say which one is a bit controversial, but I can say that the radars are one of the sensors that will be on the car. It's my personal view.
Any chance to reduce the amount of radars by wider range, wider angle in one unit?
Yes. So many radars now are working on their signals, on their even antennas. They have different types of the antennas in the same unit to cover both short range with wider field of view and long range with a smaller field of view. So I can say yes.
Okay.
Yeah.
And last question on radars. I know that the window is quite big in front, and of course the automotive designer don't like to have a lens of 60 millimeters or whatever it was in the past in front. So is the lens in front going to be a little smaller in future?
Not every radar has a lens, but you mean the size
window
of the radar. Yeah. I am not sure about that. Some of the new radars that are coming are even bigger because they should enable more number of antennas. But I hope the sizes aren't very big. I mean, they remain at least this size.
But there's a chance to integrate in the lamp house the radars as well. So
I am coming from the automotive industry, as you know, so packaging and combining of issues, the headlights are going bigger and smaller. You know, there are so many functions in the headlights now. So to integrate radars into the headlight, I thought it's easy as well. I understand your idea, but they told me just yesterday at the evening, no way. So please make it smaller and cheaper. Cheaper, we know, works usually in automotive technology or semiconductor, and you are semiconductor driven. Usually the Moore's law goes also in terms of smaller, cheaper, and less weight. Please help the automotive industry and make the window in front a little smaller so that the automotive designers are not going to hate you so much in future.
I submitted some questions in the chat as you requested.
Yeah. So
I will repeat them verbally.
yeah, if you would like, I can.
Yeah, so first let's start with the middle one. So there is a proposal for, as reflectivity is an issue in radar design and testing, there is a proposal for a standard called open material by ASA. Is this somehow relates to the IEEE work group, or are you familiar with it? It's a proposal from BMW actually.
Yes, I actually didn't know about it, but what we want to do is there are some, for example, activities that have been done about the interference effects. So we want to use all these information, but we are going to consider the radar with its fascia, with its lens and everything. So the testing includes the whole radar testing. And perhaps this it can also be used in this standard.
I would assume that the testing is not that of the radar as an isolated entity, but rather within the full system, right?
Yes.
Yeah. So
That's one of the major challenges that should be dealt with in a function rather than as an only component, because this is also demanded not only as a separate system, but also as a whole, basically.
Now, the other question is, I was quite surprised to see your comment on level 5 must have VRUs.
Yeah.
And this is from two reasons. One, level 5, we will never see it in the next 50 years, by definition. Level 5 can drive anywhere.
Are you talking SAE
SAE level 5.
or German level 5?
SAE level 5. And second is why, what about level 3?
So I was bringing an example that is a definite must for level 5, but in certain cases it might not be needed. For example, as I said, it's very much dependent on the application. For example, in even cross traffic alerts, your car has to detect the vulnerable road user in a parking lot. So
it's level 2.
It's a level 2, so it is needed, but we should look at the application.
So level 4 and 3 would need it as well, but for 1, it's definitely because there is nobody in the car in level 5, so it cannot hit a pedestrian, and all the liability is on the manufacturer, basically.
Also, in 4 within the ODD, you don't need to have a person inside, so
sure.
It's the same.
Yeah, when, for example, a partial when automation is on a highway in certain roads is possible, then these roads might not be really having the challenge with the pedestrians. So this might not be important in that case. But of course, the scenario always matters. So this is why we should consider in what kind of the scenario radar has to operate. If it is a really urban area, then vulnerable road user should be considered. So this is what why I mentioned that type of the sensor, also the application and the scenario and the automation level all play a role in defining the requirements for a radar.
I think we need to leave the next question for the offline discussion. I would like to invite Björn Gessler for the second presentation in this session. He's the director of autonomous driving development for Luminar, which is one of the groundbreaking LiDAR technology, and has a big IPO recently. So please.
Thank you very much. All right, let me see. Okay, thank you very much for giving me the opportunity to present. Hello, everybody who's not in the room here with me. And I actually, it's a pity that Axel just went out of the room. I kind of wanted to address the question that he just had on reducing the sensor set and so on. And I think we'll have some time to discuss about LiDAR plus radar plus camera, or LiDAR versus radar versus camera in the break. So I won't make this about that. Maybe before I go into the company presentation, just 2 or 3 words about myself. I started in automotive industry 16 years ago. I started at Audi. This was at the time when the big autonomous driving challenges were going around at DARPA. So the Grand Challenge, the Urban Challenge, that kind of thing. And I went into Audi because at that point, 2005, it was totally clear that the automotive industry is the one thing that's going to be building autonomous robots in the future. And I'm a robot guy. And I was extremely disappointed that in 2005, nobody was talking about autonomous driving. It was all about sporty cars with maybe a bit of functional, a bit of active safety, nothing of the kind. So it's 16 years later, finally, we're getting to the point where we're starting to realize the real problems of autonomy. The universities have known this for 20, 25 years. Exactly. And it's not, I mean, we're building robots, right? We're telling people we're building cars. What we're really doing now is we're trying to build autonomous robots. So we should be looking for the at the robotics guys and at the trends that the robotics guys have been working around for 20, 25 years. And they have been trying to get the complexity down because they're seeing, you know, it's not the number of sensors you put in the car, it's the software you write to combine them and to make something work with those sensors. And it's becoming so complicated that it's actually becoming a socio-political problem in the combination of the number of people that are working together. It's a small state that you're trying to harmonize, right? So that's one of the reasons why when Luminar, I was coming from Samsung middle of last year, and when Luminar said, do you want the Samsung team, the ex-Samsung team to join Luminar to do function development? I looked at the LiDAR data that they showed me and said, okay, exactly, this is what we need. And that's why we're there. So very quickly, I won't go into all the details on this slide. This is just the company presentation. So the company was founded in 2012 by a gentleman called Austin Russell. He's 27 now. He was 19 at the time. Yeah, do I need to say more? Fantastic guy. I have the highest respect. We've come pretty far in the last 8 years. In 2021, we announced our own autonomous driving program that we call Sentinel in collaboration with Zenseact. We have the first automotive customers under our belt. And Axel, because you talked about design earlier, when you see that thing up there, sorry, let me go back. That thing up there that you can't really see very well because there's the zoom window.
We can see.
Yeah. So on the right, that is the roofline integration of LiDAR for Volvo. That is something when I was at Audi and that when I was at different tier ones, there was a complete no-go to put a LiDAR anywhere near there because LiDAR had to vanish in the front of the vehicle, right? The thing is, if you put it up there, you see lane markings to 150 meters instead of just 70. And you can see through the windows of the cars in front of you. So you get this kind of tunneling effect that you know from radar, but you get it with a LiDAR point cloud. So there's so much functional advantage to put it up there that otherwise you'd have to program loops around, adding to the complexity. Okay, so let's leave it at that. We have a couple of customer wins. We're working together with Mobileye on their system. Globally, we're mostly in the US, but we have a couple of outward sites. I'm from Germany. We sit here in Munich in Lindbergstraße, and we do the autonomous driving functionality. The program that we call Sentinel, it's based on our LiDAR offering. The LiDAR is called Iris. It's a flat, relatively small LiDAR, sub €1,000 in cost for the OEM. And we put a perception stack on it, and we put a planning, decision making, and control stack on that. So with our software, we go to an ASIL B qualified level 2. We don't go to the level 3 and level 4, just LiDAR only. But we'll partner with camera suppliers, OEMs, and so on to basically be 1/2 of the level 4. So we're totally going there. And we have 120 degrees opening angle, so we don't cover 360 degrees with just one LiDAR. If you want that, you need a 3 to 4 LiDAR configuration. And we have a couple of projects where we're showing these individually. Okay, why are we doing this? We come from the opposite side of the spectrum, really. We come from the idea of making vehicles more safe. We have 1 million of fatalities in traffic worldwide every year. Second?
1.3.
1.3 even. This one is the fatalities per million miles just in the US per year. And you see it's going up. It's not going down. I remember showing that that curve of fatalities every year where you could see, okay, here we introduced the seatbelts, here we introduced the airbags, here we introduced ESP. That was 2000, the last big bump was 2005. Nothing happened since then. And for us, it's an imperative to bring something that's actually making roads safer. That's why we're not just addressing level 4, but also level 0 to level 2. Okay, so complexity. We want to make the whole thing a bit less complex. And I'd like to just have 2 slides saying why are we talking about complexity at all? And what's the big problem? It's not the number of sensors in the car. It's really the software and the way we use the way that we use them and to make them work together. And that's because the automotive industry is talking about complicated problems. A car is a complicated problem. It's difficult, it's non-trivial, it's hard to solve, but it's mostly deterministic. And we're trying to make the whole autonomous driving thing deterministic by shoehorning it into ASPICE and SAE, and ISO 26262, basically bringing all sorts of processes around it. But the reality is what we're looking at in traffic is we're looking at a complex problem. So it's difficult and hard to solve, but it's mostly non-deterministic. And that's why we're trying to build mountains of software around it that basically try to capture the complexity of the situation. What do I mean with mountains of software? This is a logarithmic scale, and we're talking about lines of code here, right? So a typical iPhone app has 50,000 lines of code. I've developed a couple. It's not that easy, but it's manageable. Mac OS X, the first rollout, had 80 million lines of code. That's an operating system plus graphical user interface and so on and so forth. So if we're talking about autonomous, about vehicle operating systems, that gives you an order of magnitude. We currently have about 100 million lines of code in the current car. The rollout deadline for a current car is about 3.5 years. The common house mouse has 120 million lines of code. We don't call them lines of code, we call them base pairs, but that's the complexity that a common house mouse has. Now, a mouse is not necessarily the smartest thing on the planet, but I have a cat. And I know what mice do to try to escape cats. That's pretty smart behavior there. We're not at the point with a car, right? And we had a rollout deadline for the common house mouse of about 500,000 years. So we had some time to develop it, right? And now, and this number is not something that I thought up, it's from Gartner. Gartner estimates the complexity of an autonomous car to 10 billion lines of code. It's nothing of that kind of magnitude on the streets yet, but it's pretty big. And I think we're getting there. And now we're saying, okay, we have 10 to 20 years to do that rollout. All right. Good. So that's a problem, right? And it's not, we're putting 8 sensors in the car. It's 10 billion lines of code. Who manages that? Who tests that? Who develops it? How do we manage? And that's why I'm saying we're talking about the coding output of a small nation state of programmers here. Who manages the social cultural interactions between these and between the individual companies? So let's look at how we can reduce complexity. So the first thing that I think is accepted by now, Google started with Alphabet back in the days saying, okay, we're going to do autonomous city driving. I think in the automotive industry, we're pretty well established that we're going to start traffic jams first. So we're simplifying the ODD. By the way, we're talking about automation levels. It's a great shame that the idea of situational complexity and ODD never made it into the SAE levels. I remember screaming at the VDA members, and when I was, I think in 2012 in Las Vegas preparing for CES, I was on the phone on one of the VDA discussion rounds. We discussed, what do you mean level 3? And also, what do you mean level 4, but without the idea of situational complexity? Because level 4 in a traffic jam is a whole different animal than level 4 in a city, or even level 4 on a highway at night. Right? It would be really, really good to have that in there, and not just to have the concept of taking the driver out of the loop. So that's the ODD. And then on the right-hand side, we need to simplify the system complexity. The computer science guys have been using something that they call O-calculus for a while, that basically describes how complex is a thing. And they're not thinking about how long does it take for an individual bit of the algorithm to run, but how many times do I need to run that algorithm? Translated to a car system, that's essentially how many lines of communication do I have between individual entities in that system, and how many basically different entities need to talk with each other, right? So we're not talking about the individual algorithms here, but we're talking about number of connections. So if we look at a typical level 4 sensor setup, this is from one of our customers. I'm not going to say which one, but they have surround radars, they have a front radar, they have left and right cameras looking to the back, they have a front camera, and they have our LiDAR, then they have 2 ECUs in the car. And for every single of these components, you have a perception block. For camera perception, we're going to go into a bit more detail in a second. Radar perception, we've just seen and heard a lot about. And LiDAR perception, we can also talk about. And then with the perception, after the perception block, before you can actually fuse that to a common view of the environment, you have to predict everything and to synchronize it to a common timestamp, because all of these run on their separate cycles. And then from there, you go typically into one main functionality block that's shown in blue here, and one redundant functionality block that's shown in pink. There's a number of ways that you can cut this. You can also do it monolithic, all in one big thing. That doesn't reduce the complexity, it increases it. So this is already the simpler one. And alone in the bit, talking to the 2 fusion blocks from the individual sensors, we're talking 36 connections here. So let's very quickly talk about the socio-cultural implications about this. We tend to talk about technical stuff, like how many sensors do we have on the car? Is it CAN bus or FlexRay? Is it LVDS? Is it automotive Ethernet? But we're at a complexity level where we need to talk about what is the relationship between the individual companies delivering the individual sensors here. So let's say we have an automotive radar that comes from, let's call them company C, that also sell you a camera. And we have in the same system, a camera system, on the same car, a camera system that comes from, let's call them company M, that only sell camera and don't sell radar. Company C really wants to sell you the camera as well. They are not going to integrate very well at the OEM's perspective. So they're going to make this very hard for you. So we're talking about Game of Thrones level of complexity of interactions here, where people need to work together to integrate into one system that really don't want to. So at that point, and at this level of complexity, that's not technical anymore. So we need to get to a point where it's so simple that we can talk about technicalities again. All right. Quickly, that's where we come in. And that's where this turns a bit into like a sales pitch. I don't intend this to be a sales pitch. This is supposed to be a discussion about complexity and technicalities. And I think it's pretty in line with what we just heard about better radars. I think that the main statement here is we absolutely need better sensing. We need to be able to get away from the number of sensors we have in the car and the number of companies involved in that, and to get to that, the robotics guys have known that for quite some time. They moved from cameras to LiDARs in that case. There's no way you can do radar in a lab, but they moved from cameras to LiDARs 15 to 20 years ago, because of course you can do a lot of stuff with stereo cameras, but using it with a LiDAR is so much simpler that you just don't have to coordinate hordes of master thesis students anymore to make sure something good comes out of it. You can do this in one master thesis now. And from the LiDAR that we currently have, we can do point level classification of road surface of the objects, of lane markings and so on. We can do object detection. We can do lane detection on the basis of that point level classification. We can do full odometry without wheel ticks and without steering wheel, without IMUs, just on the basis of LiDAR. Of course, we're going to use LiDAR, IMUs and wheel ticks and so on because it's there, but you don't necessarily need it. We can do direct velocity estimation from the point cloud, and we can set tracking on top of that and so on. So what you have here is essentially something that allows you to do level 2 in a box. Right? If you're not going to level 4, you don't need a camera for this. You don't need a radar for this. And you don't need a radar for this. You can do that with a radar as well, right? So that's just valid for the pictures that you showed before. Yeah. The point is you can break this down to one sensor. We're back to 1999 with where we had the first ACC radar only with just one sensor in the box, and that talked to your gas and your brakes, right? We wouldn't want to do steering with it at that time, but we probably could. Now we're back to the point where we can do level 2 with just one sensor. So just a couple of things on ranges: 300 meters on vehicles, 200 meters on motorcycles, 140 meters of small obstacles like tires or pallets or stuff like that. So let's skip that and see specifically camera, where we have, I think, a great advantage here. And that's, again, I'm trying to talk on a technology level, not so much on an individual sensor and manufacturer level. One of the problems when it relates to complexity with camera is you come from an image, you have to do basically 2 domain changes. You move from the image to the domain of classified and detected objects, free space, and so on. And then you move into the 3D domain and basically say, okay, I've seen this object in the 2D space in the image. Now I know from some extrapolation, this is where it is in 3D. So it's like 100 meters out, whatever. The red blocks here are machine learned. And I've been in so many board meetings where we start to talk about level 4. I've been involved, for example, for ZF, for the level 4 setup team. And the first thing that nowadays you seem to start discussing is, okay, so how do we do the data recording setup? How do we do big data handling? Where's the fleet that starts recording data for our classifiers to work? Because if you run with camera, you need classifiers. Otherwise, you're not going to do this. Everything that you do with camera is learned. The only thing that's provable is structure from motion, and that has the slight disadvantage that it can only see static objects. So for LiDAR, and also the same goes for radar, you don't do that. It's provable. You have the point cloud. You don't do machine learning, full stop. So you do machine learning, of course, because you want to know what kind of object is that. So you do a classification step, but it's not in the critical path. So if there's a, let's take a completely arbitrary pulled out of the cloud example. If there's a toppled over truck in front of you and your radar screams bloody murder, you're going to brake for it. If the camera says, I've never seen a truck that's fallen on its side, I don't know, there's probably nothing there, just plow through, right? That's not what you want to do. You want a sensor that basically says, I don't care what it is. It looks like a wall, you're going to hit it. So please do a braking maneuver. right? And with LiDAR and also with radar, you don't need that. So that's, I think, where the grave advantage in complexity lies, right? Again, we're talking about, you don't need 2 or 3 years of fixed systems architecture going into the field recording data before you can start to basically get your camera performing. You don't need that. You put the LiDAR in the car and that's it. And that's, by the way, why the Munich AD platform team took about 6 months to almost done. Took about 6 months to develop an autonomous emergency braking system that right now is better than everything that we've tested it against, with 6 months with 15 people. I mean, I love the guys. They're excellent programmers. They're excellent function experts. But in 6 months, better than industry standard with that number of people, that's a testament not just to the team, but to the technology that they're setting on top of. Good. So our suggestion is, first of all, let's cut this. Let's do a level 4 that consists of 2 blocks. It consists of a main functionality that is camera and radar, and a redundant functionality that's LiDAR only. And let's have that LiDAR only functionality. Well, of course, the radar fraction is going to say we can do that radar only, and that's fine, right? From the complexity point of view, that's what this is about. We want to have something that doesn't require 36 connections in there, but only 18. And that would actually be manageable within one single company on the bottom path. And then with 2 or 3 companies on the top path, okay, that's fine. But that's a lot simpler, again, because we just taken one sensor out of the equation for these guys. So that's the first thing, cutting the system in half. And by the way, this one down here can take care of your level 0 to level 2. So your upgrade path could be not put a camera in there for a level 0, but put a LiDAR in there. And you're saving money, not on the sensor itself, but on the software that you develop to do it. Right? The procurement guys don't see that. They say a camera costs $80 and a radar costs $70. I don't know, because the development that they need to get this whole system in place is done by their programming, by their software department, and that's not something procurement sees. That's something that you see in total cost of ownership and in the full system. Right? So that's where we want to go. And this one, sorry, I could have done this with radar as well, but for me, the ultimate simplification would be really just cut it down. You know, make one path. In this case, it's camera only. Let's make one path radar only. Let's make one path LiDAR only. But have 2 sensors from 2 sensor sets from 2 companies, put that together into one system, and be done with it. Okay, so thank you very much. Any questions? Very welcome.
But you can stay here to answer them, I guess. Yeah. So here we have the first question: how robust are LiDAR-equipped automotive system in terms of low visibility, bad weather conditions? I add sensor blockage, not being able to clean it, and so forth.
Okay. So fantastic question. I don't have slides to answer them. I can say, so the LiDAR technology that we're using is 1550 nanometers. And most of the other LiDAR manufacturers are using 900 nanometers. Why is that important? Because 1550 nanometers is inherently blocked and resorbed by water. 900 nanometers is not. That seems counterintuitive for bad weather. The thing is, 900 nanometers goes straight through to your retina if it hits your eye. 1550 nanometers blocked by the glass body, which enables us to put out multitudes of the amount of energy that you can do with 904 and still be eye safe. So that's why we get to the ranges of 500 meters in good weather, but we still get to ranges to about 80 to 100 meters for 10% targets in bad weather, and that's really inclement, complete fog. So I guess the answer is by far not as good as radar, but a lot better than camera. And for a camera radar system, basically it's the lowest common denominator that tells you how fast you can go, right? And then due to the fact that we're seeing individual points, that we're generating point clouds, we can actually see how far we can see. That's something the camera can't do. So what we can say is, okay, so as a human, you wouldn't probably drive more than 50 in this weather. With an autonomous system, we can go to 60, 70, 80, not more, not 230, because we can't see that far. So self-diagnosis is something that's very important. Blockage is something that's very important. We do have cleaning solutions with basically squirting water at the glass. And again, our favorite mounting position is what Volvo does, to put it in the roofline, which means you don't have that kind of dirt that you have in front. It's not to say that a bird relieves itself on there, you don't have a problem. You do, but you need to diagnose that and you need to clean it off.
Sure. Thank you very much.
Right. Thank you. That's the only question?
Yeah, I guess that was the last question.
I have one more.
Sure.
Now, I just imagine a 50 tons truck appearing in my rear view mirror. And I would like to know, is it whatever driver who did drive, or a human driver, who did drive already 5 hours, almost fast asleep? Or is it an autonomous car, autonomous truck or lorry? What I would rather more trust, to be honest. So I would recognize. And all these cars today, automatic cars, which are implemented in the traffic at the moment all over the world, Waymo and so on, you can identify them due to the ears on top where the LiDARs are in. So the thing is disappearing, so you can't recognize anymore. Isn't it going to be an identifier of a high-tech car, of an autonomous car, to have these visible LiDARs somehow in the corners on the roofs?
Well, you want visual signal that the car is in
That is
autonomy mode,
another
right?
solution. I know that. This was
Well,
Daimler
that's the
talking about.
regulatory direction right now.
So, I mean, the way that we're looking at it from the perspective of the integration that we do with Volvo, where we basically say, okay, the car has this kind of bump on top. For us, that's an indication of a real world safe car and not just a level 4 car. So we'd like to have LiDAR not just in level 4, but we'd like to have LiDAR in basically everything starting at level 0, just because, you know, again, I realize we're at a level 4 consortium here, and that's our focus. But we're kind of coming from the safety perspective, and we're kind of coming from the idea that we don't want to put a sensor in there that needs to be trained to recognize NCAP dummies. But we want a sensor in there that doesn't care what it is. Could be a trash can, it's still going to recognize and stop for it. Right? And that's something that a camera is not going to do.
Okay.
A radar might do, but not without the camera support. So that's where we come from with LiDAR.
I really love this fight. When we did set up this session, it was clear that this discussion is going to come up. And just from the automotive perspective, we love the redundancy, which is capable behind. So I think it will be a combination of all kinds of technologies. At the beginning, at least, for sure, just to make sure that there's not going to happen any accident or any, whatever the word any means. So they will put a lot of redundancy in just to make sure. And I know the one we are talking about who is speaking on cameras only. I don't think that is a good solution. By the way, they are working on radars as well.
Sure.
So you can see that on the patents. So this is not the solution of the future. So thank you very much for the redundancy in this technology.
Yeah. Thanks for this good presentation. So now it's the last presentation. We keep everything to the last best one. So Miss Huan Sun from Momenta, she's going to present about the scalable path to full autonomy. She's now general manager of Momenta Europe, and I would like to invite her to present. I think I need to do the slides myself.
She will give you the command to move.
Sure. So please.
Yeah, thank you for the intro. Hi, everyone. My name is Huan Sun. I'm the general manager of Momenta Europe. Momenta is a leading global company specialized in autonomous driving technologies. So for today's session, I'd like to share a little bit more of our thinking in how to build a scalable path to achieve full autonomy. It's a really been an honor to be here with some of the top thinkers in the industry. I'm sorry that I'm not able to be here in person, but for this opportunity, I'd like to introduce a little bit of ourselves, and I hope in the future events we could meet in person and get to know each other more. I also noticed I'm this last speaker before you and the lunch. So I will try to be as efficient as fast as possible. Okay, so next slide. Yeah. So Momenta was founded in September 2016. We just had our 5th anniversary. So the reason that we started working on Momenta on autonomous driving is that we have 2 motivations. One is that we are all fascinated with the intelligence, the topic of intelligence. Autonomous driving, we see the topic has 2 types of intelligence. One is perception intelligence, the other is cognitive intelligence. So working to understanding the intelligence and creating intelligence is very fascinating. So it gives a lot of happiness every day that we come to work every day. So this is the first reason. The second reason is that we find our work is meaningful if we truly achieve autonomous driving. And that can greatly improve people's lives. That's a reason that you can see from the slide. We have this 10 years vision, 3 10 years vision. One is in the next 10 years, we want to save 1 million lives. In the next 10 years, we want to save 100% driving time. And in the next 10 years, we want to double the efficiency of logistics and mobility. So our mission is a better AI, better life. With this 3 10 years vision, we wanted to develop breakthrough AI technologies for better life. Yeah, so yeah, next slide. Here, I'd like to also to introduce a little bit more about our milestones and the growth of Momenta and our financing. Since 2016, we have been cooperating with some world-leading automotive manufacturers and the tier 1 suppliers. Right now, our technology is in mass production phase for some mainstream and high-end vehicles. So for example, during the Shanghai Auto Show earlier this year, SAIC pre-sold many vehicles with their new IM brand. That's their new EV brand. So that will have equip our software running on the road beginning of next year. The other product we have is MSD, Momenta Self-Driving. That's for our level 4 deployment. Right now, we have tested in Suzhou in a larger scale, and we are testing in more cities. So we will have a demonstration with one of our partners in just a couple of weeks. So stay tuned. It will be a very good demonstration for these global taxi services in China. So in the future, we will work closely with the partners to develop autonomous driving technologies at a global scale. So that's the reason that I'm also here. I'm right now located in Stuttgart, working closely with some of our partners. So we are fortunate to have a total funding of so far with about $1.2 billion. The leading investors are SAIC Motor, General Motors, Daimler, Toyota, and Bosch. and together with some well-known financial institutions like Temasek and Yunfeng. We are very fortunate and proud, but at the same time feel very humbled with the responsibility given to us by these partners. Next slide. Yeah, our business right now is developing at a global scale. We have a global print. The company was founded in China in 2016, and we have offices in Beijing, Suzhou, Shenzhen, and Shanghai. And this year, we established our European headquarters in Stuttgart. That's to be close to some of our partners. So backed by this global print is actually our technical approach. We call it a data-driven approach. That one we can adapt our technology, what we have deployed in China quickly to various driving scenarios globally at a very low cost. And I'll explain a little bit more in the later slides as well. Yeah. So as we mentioned, our target is always scalable level 4. So we are now looking at enclosed environment or some limited scenarios. Our target is always to have this scalable level 4. So I'd like to spend some time to explain this a little bit more. So we should always, when we thinking about the autonomous driving full autonomy problem, we should always begin with a goal in mind. That's thinking about the end game of autonomous driving. It's a scalable full autonomy and with no restrictions of time and region. So to achieve this goal, the requirement is actually a mathematical problem that we wanted to calculate the safety level of the virtual driver to be 10 times safer than the human driver. So to make it 10 times safer than the human driver, we can translate into tasks like, for example, we need to perform in a test at the level of 100 billion miles of data with 1 million vehicles running on the road for the entire year just to validate at that level. And also the problems of that we are targeting to solve the long tail problem is at the millions of the level. So if we decompose this problem into this level, it comes into this question about what technological approach that we need to deploy. That's the next slide. Yeah, so we are facing such an enormous challenge. So we must abandon inefficient, rule-based, human-driven approach. When we are talking about 100 billions of miles of data, millions of problems, and millions of vehicles, we need to have a data-driven approach. So right now at Momenta, with this technical insight, we are building an automated system that can find and solve problems automatically. We call it a flywheel. That's a fundamental of our technical insight. That's also established from the day one when we were first founded. So it has 3 components. One is massive production data, and second is data-driven algorithms, and the third is a tool chain that can iterate between the data and the data-driven algorithms and can completely close the loop and automate the entire process. So that's how we are building this flywheel, and that can finally implement self-driving at scale with the exponential growth in performance and can solve the long tail problems. Yeah, so next slide. Yeah. So the flywheel is our technical insight. That's the flywheel is our technical insight solution to when we say we wanted to solve the scalable level 4, but how it comes to our product strategy and how we can put it into these real world use cases. So we, based on this technical insight flywheel, we have our two-like product strategy. At Momenta, we have 2 product lines. One is called MPilot, the other is called MSD. So Untitled is this mass production ready autonomous driving software that can be equipped to the series production vehicles. That's similar to, let's say, Tesla's autopilot or FSD's software part. And that one can provide with our OEM partners for there to deploy end-to-end autonomous driving user experience. And the other leg, we call it full self-driving, MSD, Momenta self-driving. That's targeted for the level 4 full autonomy use. That's suitable for 2 use cases. One is a robotaxi, the other is a privately owned vehicles for level 4 use cases. So with the deployment of these 2 products, Untitled can generate a large amount of data for deployment of level 4 technologies used in MSD, Momenta self-driving. And then the technology deployed from the level 4 from this MSD product later on can be the technology flow can later on goes back to Untitled to improve the series production software user experience. So as you can see from the graph, the closed loop feedback that has a 2 stream. One is a data flow, and the other is a technology flow. It's a closer, it forms a closed loop, iterating self-iterating process that constructs a flywheel to make the performance faster and faster. Okay, now maybe we can take a look at the video showing our technologies in action. Yeah, maybe the next slide, we have a video. Next. Yeah, I think a video probably was 1,000 words. I cannot hear the sound. Is that because you're muted? There is actually some background sound from the video.
Genau, dann kriegt sie zumindest übers Mikrofon.
Yeah, great. Yes, this is the test vehicle that we have used. You can see on the right are our model selection results as by some applications, and we based on with our planning. Yeah, there are this structure happening on the road. There are large tentacle is going in the other direction. The agents on the road are not it's following slow. Yeah, maybe we can go back to the slides. Yeah, this one. Yeah. Yeah, so this is a vehicle for the MSD, our self-driving level targeted for the level 4 use scenario. So at the technology level, at the core is our flywheel level 4, which can solve the long tail problems effectively. And it's targeted for 2 commercial use cases. One is robotaxi, we call it MSDRT. The other is MSDPV, so it's a passenger vehicle. And next slide. So as I mentioned, it's a very, how to build the flywheel is a very essential for us to have this data flow and the technology flow to be in a feedback loop. And one of the key components is that to keep the flow, we have to have a unified sensor setup shared by MSD and Untitled. So right now we have this complete sensor setup as cameras and the radars and the LiDAR. So that's it's the concept is easy, but when it comes to the software framework, when it comes to the unified sensor setup, it's actually very very innovative and very it's also an engineering challenge, and we feel very proud that we are able to innovate at this level too. Okay. Yeah, so yeah, so for the second, we mentioned there are 2 product strategy, and for the second we call it Untitled. So Untitled is our purpose-built, mass production ready, highly automated driving software for the passenger vehicles. Our core of the product is called Untitled X. It's include an end-to-end driving experience, including highway, urban, and parking. So maybe we can also directly see a video as well. Yeah, it's in the, I think the next 2 slides. Maybe the slide after that. Yeah, this one. Yeah, so this is one we reported when we were doing the test in Suzhou. It's a previous So this is a scenario that we often see the traffic jam. We are automatically switching the line to have this automated ramp to ramp feature. So we are negotiating, there was a car broke on the road. We are negotiating, trying to get in back to the lane. So it also has a HD map in it, so that you can locate and navigate easily. So this is for the parking scenario. It's using the same sensor setup as a part of the highway in the urban. So not necessary for the additional hardware cost for the OEMs. So the car itself can navigate multiple layers as well. It's an underground parking lot. So on the top right, you can see the pre-built map so that the car also can locate itself. So it also has this perception capabilities, so they can go past vehicles, and also if there are pedestrians, and we can react timely. So it's a valet parking feature. When the user calls for the car you can also go out from its parking slot and pick up the user. Yeah, so all of the all the Untitled features, Untitled X, which is end-to-end user experience, including highway, urban, and parking, It will be in the SAIC's IM vehicle beginning of the next year, running on the road in Shanghai. Maybe we can go back to the slide. Yeah. So maybe next slide. Yeah. So yeah. So as we mentioned, we are working with closely with OEMs to deploy this end-to-end pilot. We also have provide an open solution, which means that each OEM that they wanted to have their own customization for their each of the they have a different driving style, they desire for different functionalities, and they target for specific use cases. So we also provide an open solution with a broad selection of tool chains for the OEMs to easily adapt and easily to cost effectively to customize. Yeah, so yeah, we have seen this valet parking solutions already. Yeah, it's a part of our Untitled product. Yeah. Okay, so so at Momenta, we are very excited and energized to embark on this journey to improve the safety of the roads. And we always say in our mission, better AI, better life. I think it's a very special for me to have this opportunity to share our vision with such a group of audience, with experts, with you guys thought leaders, especially here in Germany, where the car is invented. I feel very fortunate to be able to share what we have done. And yeah, thank you for listening for the presentation. Yeah.
Thank you very much for your presentation. So if the audience has any questions, I would love to.
Yeah, this is Axel Deike speaking. And Soon, I'm sure you are waiting for that question from an automotive guy. Everybody is convinced that AI is a clear solution, but on the other hand, the automotive industry likes white boxes. They hate black boxes. So that is going for the question how to test an AI software package. The automotive industry at least didn't find any method yet. This is why they are at least hesitant to say it in positive words, to put an AI device into a car, which should be accepted, being reliable over, I don't know how many million kilometers. So how to test an AI-driven car?
I also would like to add to your question and say that you mentioned that the measure for safety is 10 times better than a human, and that requires statistics, and it has to be automated driving has to be in use for this purpose to ensure the safety, and this is a fundamental question, I think.
Yeah, did you hear the questions well?
Yeah, I think the second question, the voice is a little bit low, but I think I get the idea. I think they are asking maybe the same fundamental question of how we make sure it's safe, right? How do we make sure it's safe on road, especially for the AI algorithms and the deep learning stuff. Yeah, in fact, we often got this question from our partners in the automotive industry, and we know safety is a first priority for our partners and for the end users. That's for sure. So within our approach, we coming from a background of deep learning, and when our approach for testing is also originated from this, I would say, very statistical and very data-driven thinking. At the very beginning, we mentioned that for the 10 times safer than a human driver, we calculated in a way of what is this human level of safety. Right. So for the on the road, it's not like the human driver is I think there was a slide. Maybe we can go back to this scalable level 4 slide. So the human driver has this accident rate as well. So we wanted to have this algorithm performance level. If we calculate this accident level, we wanted to have a KPI that's 10 times as safer, 10 times safer than the human level. So that's a level that we target. So how to achieve that? First, there should be enough amount of data that can be that can cover all of these corner cases. So if you just test like at a let's say 1 vehicles 1 year, even though you drive the road all over the places, it's still very limited. So when we see this a large number, we wanted to make sure that let's say if it's to be able to validate at a 100 billion of miles level, how many vehicles for how long that you need to test on the road. It's a mathematical question that we calculate. Let's say if a 10 times safer than the human error level, we need 100 billions of miles of data, and which means 1 million vehicles running on the road for 1 year. That's basically that's only that entries the level of you have the enough data to test whether the performance of the system is comparable for human, right? So that's a level that we are targeting, and to achieve that, there should be several different levels. One is that, for the development phase, we understand it's not able to do this in this 1 million vehicles level. For the development level phase, for the development phase, we work with the partners. We have some of our own fleets as well as their own fleets, and to have this first some version of the algorithms that's maybe not level 4 ready, but it could be level 2++. And then with these algorithms on the road, it has all of the sensors. It has this level 4 algorithm framework. It can digest a large amount of data and find the golden data from these large fleets, and then continuously to improve the algorithm. And the algorithm in the background is self-learns, where self-learns where the corner cases are, and also it's a fully automated process for the algorithm itself to continuously to improve. And then it's also and then you deploy in the mode of we talk about shadow mode a lot. You OTA, you update the software, and then you compare what the real world driving scenarios looks like, and compare to your algorithms, and then you keep continuously to improve. And this is approach that's is a step-by-step approach. But at the very end, when you talk about scalable level 4, you have to perform at this 1 million vehicles level to be ready to validate in the test. Yeah.
Thank you very much. Step-by-step approach, I think, is a key issue. Nobody in the automotive industry will put a fully intransparent device, which is, if it's not working, killing lives or putting lives in danger. So we need to learn step by step how to handle that kind of technology. So one final question. I know you did win a contract with GM. As far as I know, right? Yeah, you are smiling, so all right. How do you compare yourself? I think it's a little tricky question, but nevertheless, yesterday I was on the biggest automotive conference here in Europe, and there was a guy from Aurora, you know, Chris Orosan. There was Professor X from AutoX there, at least virtually, with a presentation. And of course, everybody in the industry will accept, yes, AI is the future, with this question mark, as we just discussed. How do you compare yourself in this kind of landscape of AI-driven autonomous driving capability? And I'm sure I don't have a complete overview of all the companies in that market. Where do you stand compared with the others?
It's a very difficult question. I think.
You
I think
can market yourself.
no, I think I don't know. I think the partners can speak for themselves. Yeah, it's always we wanted to provide the best technology for our partners. Yeah.
Okay. You are careful. But what is for sure right is, unfortunately, there is no European company on AI on that level yet, at least, as far as I can see. It's all Chinese or American-based companies. So I would love to see some European company here as well. Maybe there are some who are not on the surface yet, didn't come out yet, but let's hope we have this global fight to find the best technology.
Yeah,
Thank you very much.
Yeah,
just a pleasure.
Just one more comment. So we actually think ourselves as a European company. Right now, I'm fully relocated from China to Stuttgart. I love to
next time.
Yeah,
next time you really should come here to join us. It was a plan. She wanted to come here, but due to whatever kind of other appointment, she couldn't make it. So we would have loved to greet you here. Thank you very much. It was a pleasure. Thank you.
Thank you very much. And we will resume this session after lunch. Thank you, everybody. So we will come back at 1:30 in at 2 o'clock European times. I guess it will be different. Yeah, in 1 hour lunch. Thank you very much, everybody, for attention, and we'll come back to you. Bye-bye.
Bye-bye.
Wherever you are in this beautiful world, which is a little bit out of order at the moment, hope you enjoyed a nice lunch. We did. We had beautiful discussions on the table about the future of L4 and specifically about artificial intelligence, of course, as one of the accepted basic technologies for the future. And on the other hand, the incompatibility, at least with the traditional safe thinking of the automotive industry, is really a challenge how to put that together. But there are more challenges going to wait for us. We need a compatible vehicle architecture. And this is the session, the next session. And Jürgen Neisses from Fujitsu. He is one of the program committee members as well, also one of the very reliable ones. Thank you very much for Jürgen for always attending and helping us to compile, for example, this kind of session here as well. So Jürgen, up to you.
Thank you, Axel, for your nice words. Yes, welcome to session number 3. A difficult one directly after lunch or dinner. Nonetheless, it's a very interesting one. As Axel said, we need to have compatible architectures that everything will develop nicely and appropriately. So we will have a look at this topic from various angles in that session. The first talk will be by Max Turner, automotive network architect at Ivanovia. Max worked for years at BMW and Jaguar Land Rover on vehicle networks and level 3, level 4 vehicles. And he as well has a long time record contributing to IEEE standards. So thanks a lot for participating as a presenter here. The stage is yours, Max.
Thank you very much. Now I just got to figure out how to get to the next slide. Yeah, and talking about standards, I'm actually currently the editor of 802.1dg, the automotive TSN profile. So if you're interested in that, feel free to get in touch. And I want to be talking about vehicle architectures, and we're going to be jumping up and down the abstraction layers here between what kind of vehicle are we building and what kind of connectivity are we putting in there. And obviously, I'm working for a company that makes Ethernet devices, so I'm a big proponent of Ethernet. That doesn't mean that I'm going to be selling you Ethernet like other people sell you a hammer to drive in a screw. That's not the point here, and this is exactly why I want to have a discussion. I think there is places where Ethernet is very well placed, and then there is places where maybe we want to do something different for different reasons. But let's try and get this into a little bit of context. And the first context that we need is definitely bandwidth. Where does bandwidth come from? Where does it not come from? And actually listening to the talks this morning, I now feel a little bad because I've basically missed two things in here, but we'll talk about that on the next slide. And then we go through some of the general architecture concepts. And this is very high flying. We're going to be looking at this from a very high level, but then we're going to be looking at very detailed why some of these have their advantages or where some of these have their advantages and disadvantages. And we're going to dive very down into detail in one slide, which I called the free rider principle. And if you want to see details, there's going to be a link to a paper on that slide, or if you have been to the IP Tech Day last week, no, previous week actually, I gave a presentation with more detail on that. So this is kind of the deep dive. And then after this technical and mathematical deep dive, we're going to go back up the ladder of abstraction, and we're going to be looking at what's actually the difference between a private ownership vehicle and a robo-taxi as far as we talk about Ethernet bandwidth. So back down to the technical detail with maybe some conclusions in the end. First question here is, what does not drive bandwidth? And actually, it's everything that is in the car today, I would argue. If you look at the audio connection, even connecting 5G, I don't know how the 5G coverage in Germany is. Up in the cafeteria where we had lunch, there was definitely none. Controlling a vehicle, well, if you look at what the driver inputs, it's about 4 integer parameters. It's 2 paddle angles and 1 steering angle. And that's how you steer a car. The control communication is not huge bandwidth. And now this is what I basically forgot a little bit is I'm talking about smart sensors here. So LiDARs and radars that basically have the processing at their front end that give back actually not an imaging radar or imaging LiDAR. I don't even know whether that's a term, but something that gives back an object list that does the processing at the front end. All of these do not generate a lot of bandwidth. And even adding them up, I would argue the vehicle that I show you here has a total bandwidth demand of way below 5 gigabit. That's probably already at the very high end. What does drive bandwidth, and what we haven't really seen in the talks this morning, and I think for partially good reason, is cameras. I'm arguing that adding a lane departure warning or some mirror replacement in your vehicle is adding more bandwidth to the vehicle than you had previously, just by adding a single device. So cameras do add bandwidth, and they added hugely. We've seen from Björn, I think, pictures of vehicles with cameras. We're all familiar by now with the 4 surround view cameras that help us with parking. And I used to be very miserable with parking until I gave up driving. We have the idea of e-mirrors, the driver monitoring camera, lane departure warning, my famous MOCLIC. Whoever is not familiar with the term, it's mitigation of child left in car, which monitors the interior to make sure you don't leave your kid behind, which I find weird. I would have rather left my parents behind probably. And then we have something like traffic sign recognition, side view, rear view, and you add whatever camera you like on there. And now we have duplicated, triplicated, 10-folded or even more the bandwidth that the vehicle without these cameras was actually using. And if you look at the configuration pages of German OEMs, they sell they sell vehicles that have all of these cameras, but they also sell vehicles that don't have a single camera. And this is, I think, one of the very special
positions that German OEMs, and particularly the one that lives here in the city where we're now, they like to build the car to how you want to have it. And they're very proud of that. And I used to be very proud of that when I was working for BMW for almost 15 years. We built the car that you order, and it is that car that you own, and that is your car, and it does what you want it to do. And that's a very special looking at privately owned vehicles, I think. It is something that is not 100% shared, I would say, with people at Toyota or GM. I think they have a quite different approach to how you market a vehicle to your customer. Nonetheless, I think it's an important approach, and for me at least, it's been a lot of my history. So one of the ways that we have been building cars in the past, and take this all, again, like I said, we're going up very high in the abstraction levels here. What we've done, in parts at least, is we've built sort of central gateways or a central switch. I'm not even going into the details which communication technology this is. But basically this idea, we bring all the information together in one central point, and we redistribute it from that one central point. Obviously, there is sensors from all four corners of the car, be it the park distance control, whatever. We bring it together and then we distribute it around. Makes communication very simple, makes the configuration of that communication very simple. Unfortunately, the daisy chaining, what you're basically seeing here as ECUs being lined up behind each other, that's very attractive here because you can move that option in if the customer has paid for it. That's obviously the important part. And you can remove it very easily as well. You also have a very nice way of knowing what needs to be powered and what does not need to be powered. And you can basically build this in parallel, add some redundancy if you need that for level 3. And we're going to go into redundancy very at the end of the talk. But actually, from a wiring perspective, this is a complete nightmare. And I started my career in the wiring harness department of BMW, and I would kill you if you proposed this to me. The variance that you're creating with these daisy chains and the wiring harness, getting the wires all to the central point, it's a nightmare. It certainly doesn't scale from the perspective of the wiring harness people. If you look at that business model of delivering the individualized vehicle, what actually became of that is kind of what I would call the domain-based system. Where the scalability now is not across the whole vehicle, but we scale the infotainment domain, we scale the driver assistance domain, we scale the engine, the interior, and we scale them all separately. And then we kind of combine the data on what I call the quote unquote backbone here. How that backbone exactly looks like, I'm on purpose not divulging. This could be one switch. This could be a daisy chain between the domain controllers. There is all kinds of different ways of doing that. Unfortunately, again, in the individualized vehicle, the model of the daisy chain comes back at you. The power control is also pretty nice. You can do it in your domain controller, and adding redundancy can now be done by domain. Seems pretty cool. And actually the wiring harness is probably a little easier managed, sorry, because you're not combining all of the domains into this one central point. Why is this guy always talking about daisy chains? He's talking about daisy chains because from a communication perspective, daisy chains are awful. They get in your way. They are hard to manage. The configuration is miserable, and usually the delay that you get from them is undesirable. Unfortunately, daisy chains are a really cool thing if you want to connect something like microphones that manage your speaking possibilities, your telephone system, speaking from the third row to the driver. If you want to have microphones, daisy chaining them up is actually quite neat. So some people came back and said, well, we want to do Ethernet. We don't want to do anything old-fashioned, but we want to go back to the shared medium approach. And probably a lot of you are familiar with 10BASE-T1S, which is also driven here out of Munich partially. But actually the 10 megabit system is very, very low bandwidth if we even talk about an 8-bit sample width and 24 kilohertz sample rate, then exceeding 10 megabit is done very, very quickly and very, very easily. So again, this whole concept of daisy chains and shared medium do not seem to be the perfect way to go forward. What are people trying to do to relieve that? There is currently an activity in Ethernet in 802.1 in the Nandika group to talk about cut-through forwarding, meaning we're not receiving a complete frame before we forward it, but we actually forward the frame as soon as we know where it's supposed to be going. It has all kinds of issues, but actually in a lot of the examples that I showed where daisy chains are attractive, I think the issues in this here are minor and are actually acceptable. So I'm quite looking forward to having the possibility of doing cut-through forwarding. There is a very new proposal. It's only really down in the grass still, talking about the 46 byte minimum for Ethernet frames today. If somebody still remembers, this comes from the shared medium when we still were doing Ethernet on 10BASE-T in the good old coax cable systems where you never knew which T connector was actually faulty and your whole network went down. That's why we needed 46 byte frames in order to make sure that the collision detection actually worked across the whole thing. If we're talking about a purely switched system, there is actually very little benefit in this 46 byte, no, 64 byte. Sorry, I have too many languages with too much Indianness right now in my brain. So it's 64 byte minimum. Doesn't give you much for actually in that switched network. So these are discussions that are happening in 802.1. If you want to be part of that, do get in touch, absolutely. And I think they can help Ethernet to move into areas where right now other bus systems are predominant. And honestly, some of them are actually currently better than Ethernet at their job, which is why they're rightly predominant. So let's work on getting Ethernet a little better here. Obviously, every one of you has heard and talked about zonal architecture. To be quite honest, when I hear talks about zonal architecture, I always feel a little queasy because usually people look at one particular aspect of it, but nobody gives you the whole truth about zonal architecture. When people talk about the weight, for example, of the wiring harness, or even of the complexity of the wiring harness, most people talk about the power distribution. Very few of them actually talk about the communication lines. Well, they know the buzzword from the power and then they use it for communication, but it's actually a little unfair. Because what a big problem actually in automotive is something like what we call automotive network management. And please don't confuse that with anything that the IT guys call network management. It's something completely different. It's how we turn on and off ECUs, particularly how we make sure that they turn off or do not turn off at the wrong time, and how we make sure that they turn off if we don't use the vehicle. And let's keep in mind a privately owned vehicle is usually operated for less than 5% of its lifetime. We're selling a vehicle that you're supposed to be owning or reselling for 20 years, and it's meant to stand its course for 6,000 hours. If you do the math, 6,000 hours over 20 years is nothing. Yeah, compare that to an airliner, compare that to a bus that drives around a city. It's absolutely miserable. Cars are built to not move as far as the power system is concerned. Zonal architecture gets you a lot of hardware abstraction, not going to go into that. A lot of people are quite happy to have fewer ECUs, have fewer boxes, not have to build as many power converters or power supplies, making them more efficient. But where there is a huge benefit is actually what I have on the bottom, which is software update and actually future-proofing, I would call it. Where we can actually put in more compute, more RAM, more non-volatile memory, more flash memory in order to be future-proof. If I have to spread out my resources for future-proofing over 30 boxes, I'm going to be sure that in most boxes, I'm never going to use the overhead. There's going to be a few boxes where I have way too little overhead. I'm going to redesign them anyway. If I can do all of that in one central point, actually scaling that is a lot easier. Also, software over the air update gets a lot easier if you have two flash banks. If you can do an update into one bank, and actually then your reboot process becomes a question of rebooting from the second image. If you are anywhere familiar with the current update process of vehicle, that's a dream scenario. Yeah, so there is advantages in this, no question about it. I am not arguing that. There's also a few downsides. One of the downsides is that we're bringing back all the information to a central compute. So what used to be a connection between a sensor, the specialized compute, and the actuator is suddenly a network in between. And now everybody keeps asking, well, how much latency does that network add? I used to be connected directly to my sensor and to my actuator. What time am I losing? What's happening here? And a lot of people like myself will go and tell you, well, actually, if you put in faster links, if you use instead of 100 megabit, you use 10 gigabit, a lot of this problem will go away. And that's cool. And I love to sell you the 10 gigabit link. That's what I'm here for. But I'd like to actually give you a better reason to buy it than just to save a few milliseconds. And this is where the free rider principle comes in. And yes, this has a few formulas in it. I know that usually halves the audience, but it's a little late for you to leave now. So just bear with us and look at the very bottom. If we have a high line rate network, this high line rate network will communicate and transport the little stuff, what used to be your CAN, what used to be your I2C, what used to be your LIN, just for free. It will not block the other traffic. There will be no interference between these two, but you have to have the high line rate. This is what we dub the free rider principle. Feel free to refer to the article at the bottom or to my talk from 2 weeks back at the Ethernet Tech Day at BMW. So when do we get actual gains from zonal architecture? High line rate. What gives us high line rate? Well, scroll a few slides back, it's cameras. It is important, if you want to do zonal architecture, please, please, please connect your cameras to your zonal aggregators. If you're building a zonal architecture that doesn't have the cameras connected to the zonal aggregators, you're probably losing out on some of the big gains that you could get. The high line rate, the few hops, the avoidance of daisy chains, and what I've dubbed here, the free rider principle, that you can basically transport all that. I need to turn on the heating in front of my camera. I need to turn on whatever LED in front of for my driver monitoring system. All of that tiny communication just basically gets lost in the mass of your video communication that runs across this high line rate system, and your QoS configuration and your QoS problems become way smaller. There is way fewer points where you need to work on it, and those points have a much easier way of going about it. I've pointed it out at the bottom. This needs some work in the transmitters, in the talkers as we call them, because we need to make sure that applications, or actually boxes, don't completely misbehave. We can't have a camera spit out the whole camera image within a few nanoseconds of the 10 gigabit link. It needs to actually leave a little bit of room, what we call the QoS. Got it. So zonal versus domain, there is huge advantages for the zonal if you can make that work, but it doesn't scale very well because what we heard from Björn before, there is silos in the development, and in a zonal controller, all of those need to come together. So if you compare a privately owned vehicle with a robotaxi, your zonal architecture comes in on the right-hand side because you have many identical articles. The startup time is not your problem. The L4 redundancy you can just add on. It doesn't need to be removed. The sensors on the outside can well be visible. What we talked about before, that some people have these very ugly ears, I think Axel called this, on the car. Well, for a robotaxi, it's cool. Would you buy a vehicle that has these stupid things on top? You probably wouldn't. And the robotaxi is operating way more during the day than your vehicle is. But this here is the slide where I'm going to run out of my time, because I hear a lot of people asking me, oh, I need redundancy in my communication. And I'm going, yes, you do, but for what? And if you look at a privately owned vehicle that needs to go into a level 3, and let's just consider that we might want to have redundancy in the user interface, making sure that in a failure mode, there is no mode confusion. And the driver might think actually the vehicle is in automated mode when it's not. So you might want some redundancy there. You might want to make sure that communication is alive. Björn gave a wonderful picture of the redundancy in sensors. You want to make sure it's different sensor modes. You want to make sure they're not mixed up, they run separately. And actually, the one thing I thought about this morning, again, when we were talking about radars and LiDARs, both of them bring their quote unquote light source along. When everybody tells me they're using cameras, I'm always asking, so how many headlights do you have? What do you do to make sure your headlights stay alive? Yeah. Compute, brake, steering. The last thing I want to go on is propulsion. We need to propel that vehicle. If it's a privately owned vehicle, I think the robotaxi has a lot more options, or might just avoid situations like that. And so, being 2 minutes late, probably already, I come to my conclusion. I think zonal architecture is a perfect fit for what I would call a robotaxi. I am not 100% sure what the business model for a privately owned vehicle would have to look like for zonal architecture to work. I am pretty convinced from my experience that the current model of current German OEMs might be difficult to achieve with zonal architecture. And with that, I'm going to call it a close. Here is my contact detail, and sorry for the overdraw.
No problem. Here we have got one question from Jill.
Yeah, so you're actually recommending two different architectures, which if you take it, reflect it back to the software world and maintenance world, you are requiring different levels of software and a lot more maintenance. Well, so it may be your analysis may be correct to that level of the network. But if you're looking at the whole total cost of manufacturing and ownership, is it still your recommendation?
Well, the question is, are we assuming that this is the same company building these different kinds of vehicles? Are we assuming that a German OEM, as we know them today, is building a robotaxi? Or are we assuming that somebody like Momenta is going to build a privately owned vehicle?
Well, for some of the major ones, at least today, they believe that they will try to compete in both markets. Okay, there is also the question of really what will be the privately owned vehicle, right? We don't know the right answer to that.
And that's exactly the problem. Exactly, this is where the fan hits, no, the other way around. Exactly. And I think this is exactly where this discussion will decide itself. And why I'm giving this talk in that way is because I think that we have way too little discussion about that question. I think we're trying to build an architecture, but we don't really know for what vehicle. And that's why I'm giving the talk in the way I do, in order to raise exactly that question. Don't design your architecture and saying it doesn't matter what I build.
Thank you very much. In Ludwigsburg, Stuttgart this year, this was a hot potato.
I would hope so.
Yeah. The argument is going about weight reduction, complexity reduction, maybe even more important than weight reduction. They talked about up to 30 kilos per car, what is a hell of a lot in a car. You remember from your time.
But you can actually do that with Sono. I agree with that.
Exactly. But I think the key comes from reduction of complexity and system integration costs.
So the question, when
talking about 75% minus system integration costs,
and if
that is
questionable, because if you look back at Björn's presentation, trying to bring in multiple domains into a single zonal controller, if that reduces complexity, I want to see your organizational structure. Thanks so much. Sorry, Jürgen, for booting you out of here. It's so much easier to talk in the room.
No problem at all. Very interesting topics. And just when we might, first, thank you for this really great and inspiring presentation. And what is one outcome which I would say as a question for the complete audience, what would be the next steps and what would be the most interesting user stories when it comes to design level 4 vehicles? Robotaxis, what's the story for the robotaxis? What's the story for an individual owned car? With the changing environmental conditions and regulations, there's lots to do before we deep dive into the technology.
Absolutely. There is a very interesting keynote presentation by, I think, Tony Ziba is his name, from Stanford University, about the future of the privately owned vehicle, which he gave to the DOTs of the US about 3 years ago. I think that might be the one you want to look at.
Great. So thanks a lot. And this 1 minute, which we are behind the schedule, is worth this discussion. Well, the next one, Nick Dimitrakopoulos from Rohde and Schwarz, Next Generation in Network Architectures. So within this presentation, we will extend the topic of network architectures to some technical details and specific network technologies and architectures. In these details, Nick is manager for EE and infotainment at Rohde and Schwarz. His work primarily focused on next generation in-vehicle network architectures, 5G broadcast for automotive, and he is active member of the Open Alliance Group and the Automotive SADIS Alliance. The stage is yours, Nick.
Thank you for the nice introduction, Jürgen. I hope that you can hear me and you can see me. I'm sitting not very far from TÜV. We are in Ostbahnhof. I have to say, I really enjoyed the presentation from Max. Every time I hear his talks, I learn new things. So Max, really well done. It was very educational, at least from my opinion. Okay, so I'm going to talk about the next generation in vehicle network architectures. For those who don't know Rohde and Schwarz, I would say most of people I speak about the company, they associate Rohde and Schwarz with EMC. Yes, we have a big business with EMC, but just to give a little bit of history, that the company is private, owned by Dr. Rohde and Dr. Schwarz, who made their first laboratory after graduating from university back in 1933. And at the moment, the company is present in around 75 countries around the world. And this year, we exceeded 12,000 employees worldwide. I don't know if I am able to switch the slides. I'll give it a try.
You just have to say, give me the command and I will move to the next, okay?
Okay, then the next slide, please. Okay, so today's talk, I will be talking a little bit more about the domain controllers, and I will have a focus on the automotive Ethernet. But just to give a quick overview of different technologies that Rohde & Schwarz is very active at the moment. We have topics like 5G, especially for the telematics. We have the topics of LiDAR and radar that Rohde & Schwarz is very active, and other cool features like ultra wideband that you can, for example, access your car when you are in a close range and so on. So the next one, please. Okay, so just in a nutshell, I want to focus on two things. First of all, it's the automotive Ethernet, and I will just share some use cases, maybe relevant to autonomous driving, which is also the topic of this IEEE event. And also I will talk about the domain controllers. So the next one. Okay, I think Max very well described the situation. So today's architecture, we see what we call it the distributed architecture with many ECUs connected through gateways. And the next platform that the manufacturers are focusing right now is the domain or centralized architecture that you now see in the middle, where you have 4 or 5 domain controllers, so ADAS, infotainment, the body control or the SASE, and so on. And the next platform after that, we expect to see the zonal architecture, and this utilizes high performance computing power. And eventually what we expect to see is, first of all, a reduction in cabling. So the in-vehicle network architecture itself finally has to be simplified. And also we expect to see a much more reduced number of ECUs, because these high processing computers, eventually they will replicate a lot of functionalities that maybe 10 or 15 or 20 ECUs are offering in the vehicle today. So we can move to the next one. And the next one, yeah. Thank you. This is a nice slide from Kirsten Matthews. She has sold this into various events. What I want to highlight here is with today's in-vehicle network technologies, there is a lot of different standards that are available, ranging from high data rates to low data rates. And of course, you can imagine when new developments are coming, and even for domain controller, that could be a challenge. You can imagine a domain controller that has to support a various number of these technologies to be able to connect with cameras or simple ECUs and so on. So the idea here is that at least in 5 or 10 years from now, eventually that we will minimize those in-vehicle networking technologies. And also from our side here at Rohde & Schwarz, we see that automotive Ethernet is a very good candidate to replace some of them. The next one, please. Okay, now I would like to give some examples with the automotive Ethernet. So this is the some trends that we see. Automotive Ethernet started back in 2008 with the onboard diagnostics, where you would take the car to the repair shop and the engineer would plug the Ethernet cable somewhere in the car to do some onboard diagnostics. 2012, we saw BMW together with Technica Engineering. They launched the technology that supports the first, at least, vehicles with 100 base T1 with the parking cameras. This would be when you put the reverse gear, you would see the video data into your dashboard. And of course, what we see now, 1000 base T1 is somehow becoming standard, and many vehicles have already this into their production lines. But what is important and exciting is that the industry is already focusing on the multi-gigabit Ethernet. This is 2.5, 5, and 10. And with that technology, a lot more exciting applications are becoming available for us. So as we move towards the ADAS, I think higher speeds, and also Max mentioned that before, this is very important. Next one, please, Axel. Yeah, this is an example from Continental. They're using the intelligent antenna module at the top layer. This is all the RF signaling. So you have a lot of antenna elements like your TV radio, 5G new radio, V2X, positioning, and so on. And the idea here is to use a microprocessor and convert all this data into automotive Ethernet. Why you do that? Because typically, if you are running a coaxial cable from the telematics unit that you see on the left-hand side into your dashboard, on a typical vehicle, you will be talking about a length of maybe 6, 7, 8 meters. And if you have frequencies that are in the range of 4 or 5 gigahertz, with coaxial RF, you would be dealing with attenuations of maybe 10, 12 dBs. So if you convert everything to automotive Ethernet, actually your losses are 0. And this is also very attractive for the telematics in the automotive industry. Next one. Yeah, we can keep it here. It's no problem. So this example shows basically one application where you can monitor the traffic between two ECUs. This could be a domain controller and, for example, a radar sensor, or a domain controller and an ECU, or two ECUs. Why we do that? First of all, what you see here is that we break the communication using a directional coupler without degrading the signal of automotive Ethernet. On the right-hand side, you see a screenshot using a digital oscilloscope. So the automotive Ethernet technology is a full duplex technology. The traffic is always busy. But what is most important, right at the bottom, you see some statistics. So Axel, I think if you click one more time, this is now magnified. No, okay. So we can turn back one slide. Sorry for that. And the idea here, if you see at the bottom, you have statistics like bus idle, how much data you can put into the bus line, and still you can check how much data rate you have. This goes very well with what Max discussed before, that you could also put the CAN traffic, the lane traffic, because you always have a check how much capacity your pipeline can support. But also for autonomous driving, you see at the bottom of this list of the oscilloscope the consecutive frame error ratio. This means this number should never go above 1%. If it does, maybe there is some communication error for a split second, and while you're driving, some ECUs are not communicating well with each other. This example shows the same principle, where you can again probe into the communication between ECU, that the signal travels through a TSN switch, and you can make again measurements and verify the performance of such a TSN switch. So again, similar principle that you can trigger into certain info frames or MAC frames, of the automotive Ethernet, and you can measure the time of the packets before the switch and after. The next one. Okay, so let's talk a little bit about the domain controllers now. This is a study that is coming from McKinsey for the Software and Electronics 2030. You see two groups of graphs. You see the base case and the accelerated case. I will only explain to you the base case here, just to give you an idea how big is the market in terms of the domain controller. So what you see on the 2020, 90-80% of the ECUs in the car were normal ECUs and only 2% were a domain controller. So this is typically cars with level 2 autonomous driving. What we now see on the year 2025, we have an increase of the domain controller. So from 2% of all the ECUs, it will be 20%. So this is typically a vehicle with level 3 going towards level 4. And what we expect to see on the 2030, and this is also in line with the zonal architecture, that 43%, almost 50% will be the domain controllers. And this is now, yeah, we can go to the next slide. A breakdown of the different domain controllers I mentioned. Of course, the ADAS and for autonomous driving, this is one that has a lot of investments and a lot of work, a lot of software, a lot of value. And this is the domain controller with the most data capacity requirements. And also the infotainment and connectivity domain controller, this is also a domain controller that will require probably most of the data rates. Okay, the next one. Yeah, and I mentioned, of course, things like a lot of data rate, especially cameras with high definition, even 4K in the future will require a lot of capacity. Now, this is an example coming from NVIDIA, the Pegasus, a typical domain controller with many CPU cores that runs different technologies. And I have highlighted here some of them in red. Things like low power DDR4 memory. These are technologies that a computer engineer is very familiar with, but when we're talking about automotive engineers, maybe these are new technologies. PCI Express, this is also now important, and of course, the first generation will use PCI Express Gen 3, with upcoming architectures also using PCI Express Gen 4. And of course, you have at the front, you see some connectors there. These typically support automotive Ethernet. Here I have highlighted 100,000 base T1, multi-gigabit, and maybe also some SerDes, especially when we're talking about connecting camera and displays. When it comes to testing, you have different things that you have to really challenge yourself. For example, power integrity, EMI debugging, you have a lot of different frequencies. Of course, you have to verify all the connectors because this domain controller has to be connected with third-party products like automotive Ethernet, MIPI, whatever this might be, also PCI Express Gen 3. And of course, when you are on a R&D stage and you are designing these boards, time domain reflectometry is very important to make sure that you have a good step response on your signaling, traveling from vias and to the PCB and so on. And basically, you can do most of these things, including the power up speeds and switch over redundancy measurements with using an oscilloscope. So we can go to the next one. Thank you, Axel. Yeah, this is an example now on, I mentioned PCI Express. This could be a new technology for automotive engineers. Here, typically, you would have some measurements like looking at the openness of the eye diagram. This is what you see now on the left-hand side. You can also do some histogram analysis on the jitter. These are these pink little mountains that you see on the picture on the left. And on the right-hand side, you can do more detailed measurements like advanced jitter, where you see the distribution of different jitter components that could happen on those high-speed digital interfaces like deterministic jitter, random jitter, and so on. In addition, with the same tool, you can do things like bit error rate Bhattacharya curve. So this is now what you see at the bottom of the right-hand side screenshot. And also you can have a look of the step response, which is a really cool tool, especially for R&D engineers, to make sure that your signal does not go through any challenging impedances, for example. The next one, please. Yeah, talking about Cerdes, today off the shelf you can buy Cerdes products that are typically running on GMSL. This is a Maxim proprietary or Apex. There is no standardization because typically these are standards where you would get the transmitter and the receiver, so there is no need for any compliance. Therefore, you would typically just do a simple jitter or eye mask testing using an oscilloscope as a tool. But the good news for the industry is that the Automotive Cerdes Alliance with the Motion Link, this is now a Cerdes technology that can run either on single twisted pair like the Automotive Ethernet or coaxial that supports speeds up to 16 gigabits per second, is verifying specification and compliance. So different products from different vendors can have, let's say, interoperability and work together. So the next one, please. Okay, and the last slides, I want to show you an example of how we can measure the time for autonomous driving. I think maybe you have heard also that some figures in the range of 50 milliseconds is good for autonomous driving for the sensor to the brakes. What you see here on this diagram, you have the sensor part where you have the GPS, the camera, radar, LiDAR, whatever this could be. In the middle, you have the processing. This could be done by a high performance domain controller that does the sensor fusion. So it's aggregating all the data from the sensors. And on the right-hand side of the slide, you see the actuator. This could be your steering wheel. It could be your brakes, for example. It could be your airbag. And always the question is how much time it takes from the moment that a radar object is detected until the brakes are applied, just to give you an example. So how can we measure the time? And the following 3 slides, I'm going to just give you a simple example using a 77 gigahertz radar sensor. So what we have here, of course, it's ADAS application, so it's safety critical. We are going to measure a radar chipset module. We are going to trigger the RF radar object, and we are going to measure the latency using the Automotive Ethernet or CAN. So let's go to the next slide to give you a better view of what this setup looks like. So the DUT that you see here on this diagram is the radar module. And we are going to use an oscilloscope to measure the RF interface, the power consumption of the radar module, but as well as the bus interface. So this is the setup we have. What I want you to steer your focus on is on the top left-hand side. This is an example now using the Texas Instruments 77 gigahertz radar. At the time I took this picture, we did this example with CAN-FD, but the same would apply with Automotive Ethernet. And here you can see also the NXP radar chipset that can support this technology. We are using the scope for different reasons. First of all, we are going to trigger the radar pulse. So we are going to trigger this radar object that will appear on the sensor. So we know exactly the time where the event occurs. We will measure the radar signal on the RF domain. We will measure the decoded bus. At this example is CAN-FD, and we will also measure some power consumption. And on the right-hand side, we have the SMA signal generator. Basically, this generates the radar signal. So what you see here, actually, if you click just once, fantastic, thank you very much. On the left-hand side, you see the chirp sequence of the automotive radar. This is common for those engineers who are familiar with radar technology. And then I have highlighted an envelope of the chirp pulses that you see below this window. If you click one more time, Axel, thank you very much. And one more time. Okay, now on the right-hand side, you see this is the CAN-FD bus decoding. The light blue line arrow at the top, thank you there, it's where we start triggering the radar module. And there you will see that there is a small voltage drop. This means that the pulse is coming in, this radar module slowly drops the voltage, some millivolts, maybe you see a little curve, and then it starts back up to the same voltage, and then CAN messaging appears. So we are zooming into the CAN, and at the bottom here, we can decode the CAN symbols, and we can measure very accurately from the start of the trigger to when the first CAN telegram or symbol came out from this radar module. And you see here an indication, the trigger to frame 9.5 milliseconds. And this is basically, at least for this radar module, the end-to-end delay, which is about 10 milliseconds. So when you apply this principle, you can do the same when you have your Ethernet network that Max also mentioned, when you have different signaling. Maybe this signal has to travel through other domain controllers and some other ECUs. But by probing to automotive Ethernet or CAN or any other in-vehicle network signal, you can very, very precisely measure the time and verify the performance of such an in-vehicle network in the physical air. And with that, I would conclude my presentation. Thank you.
Thank you so much, Nick. Very interesting deep dive into the details of the networks, the architect, extending the architectural principles which Max outlined and illustrated. So this gives a more precise view how we could go hands-on with that stuff. I don't see any questions in the chat. Are there some questions in Munich?
Yes, I got one. Nick, if you are consuming just by transferring the signal 10 milliseconds already out of the, thought to be understood 15 milliseconds total time, that means you are giving the fusion box only 5 milliseconds. That's not a lot.
You don't give 5. I think the total delay, I think, is 50 milliseconds, not 15, 50.
Okay. 50 is good enough. That's long, 50 milliseconds.
Well, maybe somebody says it's less, but I don't think it's written in stone. Maybe some expert in the audience can verify that. I think 50 milliseconds, it's at least much faster than the human brain.
Yeah, of course, yeah. Okay, another question goes in.
At least from my brain, it's faster.
Yeah. I'm a little older. My brain is much slower already. Nevertheless, and another idea to speed me up may be to use plastic fiber. I did see it on the chart of Mrs. Kirsten as well. What do you think about connection by light via fiber plastic?
I personally, without expressing the opinion of Roden Schwartz, I think this is very challenging, because when we're looking on these cables in vehicle networks inside the vehicle, there is a lot of bending. There also are vibrations, so I'm not sure how the optical will behave under these conditions. It can work when you connect, let's say, a domain controller with another domain controller that are maybe sitting on a similar level, and you have a straight line or minimum bending. But having a full vehicle with opticals, personally, I think it's a no-go.
I'm not sure about that. The BMW E65 used the MOS bus, which was on the chart as well. And I was a project leader at that time. So thankfully, we never experienced any problem
with the
And it
connections.
didn't die because of the optics.
It doesn't
Yeah,
die because of optical problems. That is exactly the right statement Max just
Yeah.
made.
Yeah, thank you, Max. Yeah, I think most we will not see it in the future platforms.
Yeah, that was a political issue. That's not a technical issue. It was just politics.
I want to stay out of that. Thank you.
Thank you very much. Jürgen, your turn.
Yeah, just one brief remark. The world of security and safety lives from technical and organizational measures, the so-called TOMs. So we always need to have in our mind all these organizational and thus also political measures besides just technology. So unfortunately, it's not just so nice for us who we are more or less technology driven, but we need to consider this. Well, the third speaker of this session is Christoph Schulze. He is project manager and technical lead at TT Tech, and he will present on a safety architecture for autonomous vehicles. So, Christoph, please go ahead.
So good afternoon, everybody from Vienna, just a little bit east of Munich. As you mentioned, Jürgen, I'm working for TT Tech here in Vienna, but today I'm speaking to you as a representative of the Autonomous. The Autonomous is an endeavor at TT Tech Auto, a platform to unite all of the key players in autonomous driving. And I will, in the upcoming minutes, I will tell you a little bit more about the Autonomous, and then I will come to the topic of our working groups that we would like to found in the upcoming months, years respectively. And in special, I will tell you a little bit about our first working group called Safety and Architecture. I'm just having troubles here. How can I, do you see my mouse now?
You just tell me to move it.
Okay,
just
because I saw that Nick was able to use a laser pointer. So I was trying to reproduce this option, but anyway, I think we will be fine, Axel. So if you could please go to the next slide. Yeah, this is the agenda for today. I already summarized it for you. So first of all, I would like to tell you a little bit about the Autonomous, then the streams we have within the Autonomous, and then come to the working group on safety and architecture. Next, please. One more, yeah, exactly. So what is the purpose of our initiative? As you can see, I think this is a very generous slide to start with. We are facing multiple challenges in context of autonomous driving. So of course, there is the challenge how to build an architecture that is safe, how to deal with artificial intelligence, the topic of cybersecurity, regulation and legal issues that need to be solved, subcomponents like sensor fusion that need to be developed and worked on. And we are convinced that those challenges cannot be done by one player or one OEM or one company alone. We are convinced that collaboration is the key to success here. Next slide, please. So what is our vision and what is our mission? The vision is that we want to change the way that the automotive, transport and wider mobility industry works. Our mission is to solve the biggest safety challenges in the autonomous mobility industry by enabling collaboration across the world. Next slide, please. How are we changing the industry? On the left side, you can see the current approach, how solutions are brought to the market. So usually there is an ecosystem around an OEM with all of the tiers and the sub-suppliers that build something like an ecosystem, a cooperation network. And each one of those networks, corporations, develops individual solutions, sometimes being very different from each other. We think, or we are working on building a single ecosystem involving all of the key players. So this means not only the OEMs, not only the tiers, we also want to incorporate or to have inside our initiative standardization bodies government bodies, academia or near academia, regulators, and also insurers. And in this single ecosystem, we want to work on global reference solutions that will then lead to different implementations by the different technology providers. This might seem a little bit blurry to you. That's why, next slide, please. Okay, next slide, please. That's why I would like to give you, first of all, an overview on the different streams that we have within the autonomous. So we have two major streams, the event stream and the innovation stream. Let me start with the event stream. So we have the autonomous main event, just happened end of September in Vienna in the Imperial Palace. I think it was an amazing meeting that we had. Actually, I met Axel there because I was hosting a workshop, and Axel invited me to present today. So here I am presenting to you about our initiative and about our working group. And besides this yearly main event, last year unfortunately did not happen due to COVID, but we want to do this on a yearly basis. We're also hosting chapter events that are focusing on selected technical topics. You can find, if you're interested in further information there, you can find links and reports on theautonomous.com. But today I would like to focus on the right side here on the innovation stream, and especially on the working groups that I will tell you a little bit more in the upcoming minutes. Next slide, please. So let me start with a very rough overview about the automotive development process. This slide needs to be read from bottom to up. So what do we do in the beginning before we start developing anything? We think about the requirements. What does this thing need to do? What's the behavior of the system, and what are the criteria that a system must meet, especially concerning dependability goals and other criteria, like, for example, regulatory criteria. Then we think about next step we usually do is we think about an architecture. How can we break down this problem that we have described by its requirements? How can we break down these problems into smaller pieces, maybe sometimes easier solvable pieces? So it's somehow a plan how to create the big problems described by the requirements. As soon as we have, let's say, come up with a solid plan and a well thought through plan here, we think, how can we design the individual components? What shall be in there? Also think about how shall they, for example, differ between the different architecture components. Can we use the same software or hardware component inside this inside different architecture elements, or do they need to differ for reasons of sufficient independence, for example? And if you have come up with a design, of course, the final step is to do the final implementation, both on hardware and software side. And next slide, please. One more. Yeah, exactly. So the status quo is that most of the relevant standards, I would not say all, but most of the relevant standards are focusing on this requirements layer that is focusing on what we want to do or what shall be done. But this how layer, including architecture, design, and the final implementation, is usually subject to individual solutions, as I have already pointed out a few minutes ago. Next slide, please. But there are also counterexamples to what I just said. So, for example, there is this EGA standard that was a joint effort of the major German OEMs, and it was focusing not on the requirements level, it was focusing on the architecture and design level. And I think it's a broadly a very famous example for cooperation in the design and architecture layer. Next slide, please. So where do we see ourselves here? Where do we see the autonomous? So first of all, let me maybe start with the graphics on the right side, this umbrella, where we see the SAE level 4 autonomous driving feature and the challenges or the potential future working groups we see underneath. Those is basically reflecting what I already said in the beginning. So we are focusing here on architecture, security, regulation, AI, and sensor fusion. And the main level of in the autonomous in the automotive development process that we want to address is this architecture layer. So we would like in these working groups to develop reference solutions for the architecture layer. And as it is indicated with this little turquoise box here it says alignment with standards and relevant organizations. This is what I'm doing right now, yeah, because I'm presenting to you what we're doing here and what the autonomous is about, and especially what we want to do in context of the working group safety and architecture. Next slide, please, Axel. So as I already mentioned, a short summary before we dive deeper into the specific working group. Our focus is to come up with recommendations, best practices, guidelines, and reference. Here it says specifications. I would say reference solutions for certain problems to be addressed within the working groups. Click. The first working group, as I already mentioned, is focused on safety and architecture. And our main goal, here it is just written in one sentence. I will give you a little bit more insights on the next slides. Here it says define the state of the art in safety architecture for self-driving cars for SAE level 4 and potentially higher. Click please, Axel. Yeah, and the output is technical documents, reports that shall, as I said on the last slide, be aligned with the relevant standards, and those documents or this report shall be released, of course, at the end of each iteration of the respective working group. Next slide, please, Axel. Yeah, and now finally, I have announced it already twice, I think. Now I will come to the interesting part, the working group safety and architecture, and what we plan to do there. So let me start the presentation by giving an overview on who we are. This picture was actually taken in a hybrid meeting that we had in Vienna end of September, the day before we had the main event of the autonomous. And we have, I would say, a very good working group setup. We have, because we have, let's say, I would say all the key players that we need. So we have 2 OEMs on board. We have BMW and Audi, respectively CARIAD. On the semiconductor side, we have Infineon, NXP, Denso, and ARM. On the tier side, it's Core AVI, 5, us, TTH Auto, and Base Labs. And on the academia, near academia side, we have the Technical University of Stockholm, Fraunhofer in Kaiserslautern, and the Austrian Institute of Technology. And as you can see, this was one of the meetings that we had, where actually in this meeting we aligned on the scope that I will present to you on the next slide. Before I talk about the concrete scope and the sections of the report that we want to produce, I would like to tell you a little bit about the overall goal. As I already mentioned, we want to find one conceptual architecture for one reference feature. This reference feature shall be level 4 highway pilot, because we think that this level 4 highway pilot will become highly relevant for the OEMs in the upcoming years. And we think that level 3 feature, we see different opinions on the level 3 feature in the market. Let's call it like this. That's why we decided to address a level 4 feature. This conceptual architecture, so conceptual in this case means that we describe the system not by concrete hardware or software, but we describe it by what it shall do, what it is intended to do. And the way we want to base this conceptual architecture on is on so-called fault containment units. As you can see in the bottom right here, abbreviated, it is FCU, fault containment unit. let me briefly explain what a fault containment unit actually is. A fault containment unit is a unit that fails independently from all of the other units in the system. So this means if one of the units fails for whatever reason, it does not corrupt any of the other units. We know, of course, that there are, let's say, limitations to this independency. Just think of the case of, I don't know, a big rock falling onto the car and destroying everything. Then it will not be possible to have this complete independence. But of course, we try to, or we want to have those FCUs fail as independently as possible. And the idea is to define in this context of sense, think, act general approach, to define a structure for the think layer on a conceptual level based on fault containment units. We want to start the activity by collecting relevant ED use cases. Yeah, as I already said, it will be a level 4 hyperpilot, but there might be certain or different details of the AD use cases when it comes to what does the ODD exactly look like, what do the weather conditions exactly look like. That's why we would like to start with a collection of the relevant use cases and define one of those use cases to be our reference use case, indicated in blue in the graphics you see on the right top. For this reference AD use case, we want to collect different conceptual architecture ideas. Here it is called proposals. And any working group member is of course is of course invited to contribute his or her proposal here. And we also want to look into what other standards, other activities out there are proposing concerning such a conceptual architecture and consider them as one of the candidates here. In the end, we want to choose one of those proposals to be our reference architecture for the chosen reference AD use case. And as you can see, there is also a feedback line drawn here to the additional AD use cases, which means that we want to evaluate if the reference architecture would also be able to match those additional AD use cases, or if the architecture, the reference architecture is not, let's say, applicable for those additional AD use cases. As I mentioned, the final outcome of our working group will be a public report containing 3 sections plus appendices. And this report will be produced in an incremental way. So we will work in let's say, in an agile way. And by end of 2022, I will come to the timeline in a couple of moments. We want to have this report ready. Next slide, please. As I already said, we want to consider goals, issues, and concern that must be considered when designing a level 4 system, an SAE level 4 system. And we want to look into a set of architectural solutions and evaluate those architectural solutions from different vantage points, like, for example, achievement of dependability goals, hardware and software, cost and effort, validation effort, and so on. Click, please. The first section of the report will contain those reference use cases. We want to talk about the dependability goals, the KPIs, and the matrices, very important, how to actually measure in the end that I have found a good solution. And of course, there needs to be some kind of assumptions and coverage discussion to build a common ground to start from. Click. I would say the heart of our report, the section 2, we want to discuss or bring in all of those architecture proposals, do a critical review and comparison, and come up with a choice of a reference architecture. Click. That is actually supported by section 3, because section 3 shall be the basis for the choice of the reference architecture. Here we want to build up a safety argumentation. We decided not to call it safety case because safety case is very much dominated by the ISO definition. But we want to use elements actually that can be used to build up a safety case, like, for example, formal verification, SAL models, Markov models, and means like this. And we also would like to, in section 3, to consider to consider topics that would be relevant if we would, let's say, map the architecture to concrete hardware and software. Click, Axel. In the appendices, of course, terminology, very important topic, architecture scalability. I think this, especially for OEMs, for reusability of components of the system, scalability is a big topic, I would say. From the vantage point of a level 4, it's more maybe a downwards scalability when it comes to the SAE level, but there are different dimensions when it comes to scalability. And we would like to cover those aspects in the appendix. And we also would like to talk about the validation and certification goals there. That, for example, if we find an architecture that reduces validation efforts because some parts of the architecture are more or less static and others are not, yeah, we might be able to reduce the validation efforts for the whole system. Click, Axel. Potential later topics is socio-technical safety concept and non-passenger vehicles. And out of scope, click, is do we see the sensors and actuators themselves to be out of the scope of our activity. And we do not want to talk about particular hardware or software, so we don't want to talk about specific chips or specific hardware design, and we don't want to talk about specific algorithms that shall be used in the different fault containment units. Click, Axel. But there are a couple of topics that we see, as you have seen in the earlier slides, that we see for potential parallel working groups, especially security is a very important topic. So we decided to purely focus on safety here in this working group. But we know that there is a very close, of course, correlation or tackling overlap between security and safety. But security aspects shall be covered as part of a parallel working group. And also artificial intelligence shall be part of a parallel working group. And by the way, we are already working on defining a scope for such an artificial intelligence working group. There's nothing I can tell you yet, but we are in contact with different players here. And I hope that we will be able to announce the kickoff of such a working group within the upcoming months, I would say. Next slide, please, Axel. I think this is already my final slide for today. I would like to give you a little bit about the timeline. So as you can see, we're still in iteration number 1. So we are working on report increment number 1. And another maybe organizational aspect that I would like to mention is that we are working under an IP policy. So in general, we are an open, or all of the autonomous working groups are open to everyone. But the requirements to enter is first of all a membership agreement, and then this IP policy. We think that this is very important to enable our members to bring in their IP, to share their thoughts without any strategical restriction, let me call it like this. That's why we have set up an IP policy. And actually, the deadline for the IP policy is next week. And after that, we will start actually working on the architectural solutions and doing this critical review and comparison that I described earlier. There will be 3 report increments, as I mentioned. And for December 22, end of next year, we have planned to release a public report that will then be aligned with the relevant standards. Click, Axel. And I would like to finish my talk today with a picture of the autonomous team. You might know one or the other from the team. I'm standing in the back there, and click, Axel. But this, I would like to say thank you, and I'm very much looking to your questions, if there are any. I didn't check.
There are no questions from the public yet, but of course, I do have a question. And Jill, you got the first right.
Yeah. So the SAE is working on reference architecture as well. The document is called J3131. In the spirit of the autonomous of collaboration, are you collaborating with them?
Yeah, so I know Daniel Bartz. Yeah, we are in contact. And actually there are conversations ongoing with SAE J3131. And my way of my idea is to have one of those. So I have seen the draft from Daniel, and I would consider his proposal to be one of the candidates that shall be discussed within the working group.
Very good. Thanks.
Christoph mentioned this meeting in Vienna, the autonomous or Congress almost, and that's where we picked this issue up. I was there with John Tintinelli. John Tintinelli is a representative of SAE in Europe. And of course, we discussed this immediately with Christoph. This is how the whole initiative came up to be talked about here. And I can only really wish you all the luck on the earth, Christoph, that this initiative, which is started, I think, mostly by Ricky Hudi and George Kopitz, TT Tech. This is one of the ways to come forward. I hope you are going to get more OEMs online. I hope how difficult it is. As architecture, the word is already difficult to swallow. And to implement different structures in the automotive industry over time, of course, is very tricky because not all the cars are changing at the same time. So it's not easy, I know very much, but I can only support it. And whoever is listening here from the OEM side, I would love that many OEMs are going to overrun you with applications or questions, at least, to work with you, Christoph. Thank you very much for that.
Yeah, thank you, Axel. I think this is might be a good occasion to announce that, of course, if anyone here present is interested in joining us on our journey, no matter, let's say, where he's coming from, what's the technical background, please get back to me. We are really looking in having diverse approaches or diverse backgrounds in our working group to, let's say, get one common understanding. As mentioned, first working group will be on this architecture level, but we have plans for the future as well. I was talking about artificial intelligence. I was talking about security. So there's more to follow. Yeah. And actually, Axel, I think you were sitting in the workshop in Vienna, and it was so unusual after almost 2 years of COVID to just stand up and walk to the people. And you said, "Come with me. I'm gonna introduce you to the guys." Yeah, and they were in the next room. Yeah, and this was, I think, very unusual in days like this.
Yeah.
Hello.
Just a question, and Jürgen, forgive me, just one content side question, Christoph. When we are talking about architecture in the classic sense, usually we discuss boxes, units, ECUs. And from our discussion, I understood, of course, that this is not the case here. We are talking about a virtual architecture, including software and so on. Maybe you would like to elaborate a little more on that.
Yeah, so I think this is true. I think this concept of cold fault containment unit, or this concept of conceptual architecture, is not talking about hardware. It's not talking about software. It's actually talking about the functionality that it shall do. So, for example, there might be one fault containment unit that is supervising the plans of another unit. Yeah? And the level we describe those fault containment units is on the requirements level, saying, okay, there is a fault containment unit that shall receive input from another fault containment unit and send, let's say, the result to, again, another fault containment unit. So it's describing the system on a functional conceptual level, but it's not talking about how does it actually do it. Yeah, what is it a separate ECU? Can it be integrated into or can multiple FCUs be integrated in one ECU? For example, is one of the the topics we do not address here. Yeah, and we also do not talk about, for, let's say, coming back to the example that an FCU checks another FCU, we do not talk about how does it actually do it. Yeah, what are the requirements of the software in this unit? Does this somehow answer your question, Axel?
Yes, I was more targeting that you are going to explain to our attendees. I don't have to understand it anymore. I only want to support you with this initiative. Really, I love it. And it's coming out of my heart that the automotive industry is going to work and more going to work on this issue. We just discussed it on the lunch table as well. I really don't understand why we should reinvent the wheel 5 times in Europe or 3 times with 3 big automotive manufacturers here in Europe with using Stellantis, Renault, and so on, and worldwide another, I don't know, 10 times doing the same thing, and all of us fighting against the lawyers in America finally, or whatever kind of technical issues and so on. So I really love working together. Please get it going. Greetings to Ricky, George, and whoever is standing behind. I am fully in support.
Thank you, Axel.
Well,
Jürgen, sorry, I interrupted your moderation, but this is so close to my heart. Okay,
well,
sorry.
as you know, as a guy working on the Horizon Europe topic, I'm also fond of collaboration. Nonetheless, Ike Furkan has a question, and I guess he should
have
the opportunity for it.
Yeah, thanks a lot for this. So I have a quite fundamental question. It was mentioned that the safety and architecture group and the safety for machine learning topics were separate, going in separate paths.
Mm-hmm.
Now, what I think is there is known limitations to safety evidences of machine learning based blocks.
Mm-hmm.
This is a topic which is currently under research. So now there is a dilemma I see here for a topic which is currently under research and answer. We are trying to standardize things. How do you see this topic?
I think it's a very valid point. I think this let's say there are limitations to AI, especially when it comes to safety and also when it comes to explainability. I think this is always in the context of safety a very important topic, because if something goes wrong, you might be asked to explain what you did and how you did it. And AI has its limitations there. And I think this is a very valid point, and we want to address those questions inside the working group on safety and AI. But for the safety and architecture, we want to build the basis for this by saying, okay, here we have a fault containment unit. In this fault containment unit, let's say in FCU number 1, we are allowed to place AI, in FCU 2 not, and then FCU 3 only partially, for example. We somehow define, let's say, a concept how to host artificial intelligence, neural networks, whatever there is actually. And the concept that we develop in the architecture working group is actually designed that such a fault containment unit might fail. It is allowed to fail without corrupting the whole system. And if we place, let's say, it wisely, then we have built a good starting point from top down to then think about, okay, now we know in this fault containment unit we are allowed to use AI. What can we do now to make the fault containment unit as safe as possible? But this shall then be addressed in the corresponding working group. Does this answer? Yeah.
A quick follow-up on this follow-up question. So if I got it correctly, you see it's like a breakdown of systems engineering approach, like you have a very abstract specification of safety engineering in the safety and architecture group, more or less. And in this special interest group or specialization group for ML, you will have maybe methods for this, which might be still in research somewhere.
Exactly. I think you summarized it exactly like I very well.
Okay,
Yeah.
My last follow-up question. What are the expectations of your stakeholders or participants about the second working group? So what is the expected outlook where this problem can be solved in the timeline in the next few years?
This is a good point. And actually what the timeline I have been showing you today is only applicable for the architecture working group. In context of the AI working group, we don't have it yet. We are in discussions, and what exactly where you put your finger on is exactly the topics we are discussing at the moment. What do we want to do when? What should be the scope of such an activity? And I can only invite you, if you're interested in participating there, please get back to me. I don't know I don't know which company you're working for, but if you're interested, I'm happy to discuss with you.
Okay, thanks a lot. And I need to leave now. Thanks a lot for your answers and have a nice rest of the day. Bye-bye.
Thank you, Christoph.
You too. Yeah, thank you, Jürgen.
Yeah, thank you, Christoph, for the nice presentation and the question and answer session. Very interesting, especially the last part and AI, safety, security. There are lots of, well, to be solved issues. Nonetheless, the final presentation will be held by Cheng Wan of Geely and Jan Botau of AVL. They will inform us about the state of autonomous driving at Geely, which is a very interesting topic. Well, we will see some real solutions, I guess, and happy to listen to you two.
Yes, hello.
Yeah.
Yeah, thank you. I hope because I have updated the slide a little, is that possible that for me to share the presentation also with the actual stand?
Well,
you should see it already. It's the latest version.
Yeah, because I have had also other videos, but it's due to the big size is not updated. So is that possible to
sorry,
let me share the monitor?
Yeah, I'm very sorry, but that came too late. I couldn't correct that failure anymore. Sorry, Cheng.
Okay, no, then let's.
Because this overall PowerPoint is about 3 gigs huge.
Okay, sorry. No, it's okay.
Sorry.
Yeah, we can handle it. It's okay. Thanks.
Okay.
So, dear colleague in Germany and also the guests from the monitoring, nice to meet you here. I'm Cheng Wang from Geely. And also, I want to present some one topics today here with the colleague Tao Zhenbo from AVL in Graz to reflect our thinking regarding the challenges towards airflow systems. And we want also to show what is the big challenge we see from point of view of the OEMs for airflow system development and what we are doing now for this. Please, next slide. So this is just this first slide to show generally, but the one thing here to mention is very clear. The case, the 4 new strategies and trends in automobile mobile are moving fast, especially I can feel it really in China. I have been back to China for 3 years. In the last 3 years before, I have been in Germany for a long time and worked for also on very famous OEMs. but interesting for me also to experience direct development in the last 3 years in China, what regards electrification and autonomous driving here ongoing. And the colleague from Momenta has shown some great result, what they have done in China. So please, next slide. Good, some movement in the world, but generally we see 3 years ago, there are 3, let's say, different approaches. The first one is about robotaxis, and a famous player is the Waymo from the USA. And the second approach is like some OEMs had tried to introduce level 3 systems with full redundancy, step to achieve or to get closer to the level 4 world. And also Tesla play the third strategy with so-called level 2 plus systems. This is the strength, and we can see also these 3 strategy are also landing and implemented in China in different with different OEMs. Please, next slide. Next slide. Sorry. Yes. We want to also mention that as history that the autonomous driving doesn't come just from the beginning of the 18th. Like Professor Dickmans has developed an Daimler car in the highway. It existed already in 1939. The first World Explorer, as the left picture shows, this is the picture from that time. And at that time, the American think about a traffic system in future with fully automated traffics. And on the right side is also a very famous pictures. I think also Europe that is an AD picture from the middle 50 from America to see how should the people have in the highway in, I think this is foreseen to 2020. Next slide.
Cheng, just to give you, I think that picture is from 1952. As far as I am informed, it was Chrysler, I think. And they believed in a cable or something in the middle of the street where the cars should sense the cable and follow to the line.
Yeah, I get the point that they try to use the magnet streifen in the highway.
Something like that. Okay.
As a key. I mean, this is some way we to try to achieve the autonomous driving. Yeah. Mm-hmm. Next, please. So the famous project we know this is from this is Professor Dickman's car in the highway. From the 1805, which has already enabled an autonomous driving with 113 kph. And also the most result comes from the Dapper Challenger and the Urban Challenger at the time. And then please, next. So after that, we see a lot of result. I just one thing I want to respect all the let's say technology pioneers. They have shown a great result in the autonomous driving areas and enable that we moving and try to moving these topics and technologies in the serious product. Yeah, but anyhow, we have seen a lot of good technology and also very good car. But we still don't have such cars on our public roads. And I think that's the reason why we sit together today here and discuss about that. Then based on that, I come to the next topics, why we have so many challenges. And additional to mention, there's always different opinions, like Elon Musk and also Gilbreth in 2017 announced come this closer or we are still far away? That's interesting questions. We want to find it out. Yeah, please next. Good. I come to the parts to see, try to show our experienced challenges from different areas. So I think a lot of things have well described and explained from expert from different areas from the last two sessions. And also I'm glad to hear from Björn Gisler, my former colleague, for his toy LiDAR technologies, and also colleague has also shown some toy technology for the radar systems, and also from point of view of architectures and communications, as we heard and learned just now. So, but from, if we try to formalize what are the key technologies, we still have no really solution to that. This is the first thing. We still have no solution how to really describe and control the corner, all the scenarios, especially how to figure out the corner cases and how to control the corner cases. And secondly, the second issues what we see is, I think that's also the discussion what we have just 10 minutes ago regarding we see a lot of data-based and AI-based algorithms are used now in our level 4 system, or are intended to be used. And but like such black box, how to really verify and validate it to show that it's controllable, which is the basic principle for the vehicle development, is still a very interesting open issue for us. The third thing was really well discussed in the last, let's say, 8 years regarding perceptual reliability. We have begun the work on that in, I think, in the year 2012. The time we find that, okay, our radar and our camera system are really not reliable as what I think. Even that time, the functional safety ISO is already announced, but it doesn't help us for this topic. So based on that, the people sit together and work out a new standard for the functional functionality, what we is well also known as the sortives. But we still have not well validated the solution how to ensure the perception reliability, regardless how many sensors, cameras, LiDARs, and radars are mounted in the car. How many is enough, and how to really fusion the information together to make the information reliable enough. That's the question we try to figure out. And last thing is, okay, how to validate and verify the whole system design, and also validate the whole product, and especially the safety. Okay, next. So safety, this is clear. I think for all the guests today here, this is not only about one safety. We are talking about many safeties, functional safety, and also the intended functionality safety for the sortive. I think Mobile has also introduced one very interesting approach, like its RSS model, to deal with not only a single autonomous driving car, but also to deal with really traffic, namely how should a cognitive or a full autonomous driving car works with the other traffic participants. And should we need also think about a new traffic rules for them? I think this is well described in the RSS model, and also from my point of view, is still well deserved to think about it. And more and finally, cybersecurity also playing a more important role in this area. And one thing to mention also, functional safety. The people think, okay, we already have SLD system, like in the brake and steering system. Why is SLD so difficult? We can also make an example here, because different safety goals result in a totally different technical cost to realize a safety goal. So for example, if we just avoid for human driver, his steering is always controllable. So we just needed to limit the tokens by the steering system, and we can achieve this system with a very simple SOD algorithms. But if we try to realize this safety goal for a full autonomous driving system, it could mean a full redundant L4 system design, which means a huge system cost and development and complication. That's one thing also additional to mention. Even for the same SOD is for L4 system, it's quite difficult and complicated than normal SOD system. Next slide, please. Thanks, Herman. And if we come to the next, if we have a good fine solution for our level 4 system, and we believe that this kind of system design and development could enable a level 4 car. And from traditional point of view, we need to think about how to validate it. If I take a look about what kind of methodology are introduced in the functional safety, we see basically we have requirement test for injection and back-to-back test. But if we needed to think about deploy such kind of test methodologies in a full redundant L4 systems with different sensors, algorithms, redundant domain controller, and so on. And what could mean a huge cost, which plays always an important role for the series product. This is also one solution we need to find. Please, next slide. And because of that, and validation target for the L4 system to find. Why? This is well described in the project Pegasus, as the picture shows, that traditional vehicle validation is all regarding how to enable the vehicle, namely the let's say mechanic and also liquid system are controllable by the driver, human drivers, but is not considered to be used to evaluate how the capability of the driver. And for L4 system, it's clear our intention to replace the driver with a technical systems, and how to evaluate his sensing capability, his thinking and decision capability, and also action capability. And as a whole system, this is still open. There are some approaches, like we want to use how many traffic fatalities will be caused by the human driver. And if we could achieve to that, it could be an acceptable goal for us. But we have to make a rough calculation. If we want to achieve an, let's say, a safety rate, what could be achieved by a human driver, we need the car to drive at least 4,000 times around the world. Yeah, this is the kilometer we need to collect to reach the detected rate. So this is also a thing, and even that we cannot coverage all the weather conditions, or the road conditions, or the situation conditions, which we cannot really well describe. So how to validate it with a meaningful validation target is still an open issue for the OEMs. And I have
Can you hear me still, Rosie? Something is broken down.
Yes, I can hear you.
Ah, so it's
Yeah.
not from us here. So it's Cheng Wang's China problem somewhere. Okay, then we can only go ahead just to show his voice, but I can't put any comment on it. Ah, he's coming back. Cheng, I hope you are back. Looks like we got a system problem somewhere on the long way between China and America and Europe. Yeah, we are really global here. Presenter is sitting in China. The PC runs in Germany. The Zoom sessions runs in New Jersey, I think so, in America. So we are really international. Maybe I should talk German with Cheng Wang. He understands German very, very much, very well. He worked here for many years, 10 years or so. German is good. Looks like he's not coming. Ah!
Probably going to dial in again.
Okay.
He's there. But no
Cheng,
audio.
I hope.
I love the traffic light. Wow, that's crazy.
Yeah, these are the crazy traffic conditions. Left, top left. This is what the Asian world has to manage. This was exactly what I referred to, what was shown yesterday by AutoX. They maneuvered through such kind of catastrophe with an autonomous driven car. But winter is also something very challenging still. Camera doesn't work really anymore under winter conditions. Hope the LiDAR and the radar section here will help a lot.
Try that one.
Yeah, that's also a good one. So this really shows.
It's joining again, Axel.
Okay. And of course, just to look to the kids here, the biggest problem in the whole loop is there are going to be so many human drivers still in the beginning, and they are reacting differently. Not predictable. Never know what they are going to do specifically when we are talking about kids.
So, hello, hi.
Okay, take over again. We just left your picture slide here with all the different traffic conditions. I made some comments.
Yes, yeah, I think I try to shut off my videos. It could help maybe stabilize that. If it doesn't disturb you, and yes, thank you for take over that. I have also called the American agency because maybe I think they have stopped my video transfer from China. No, yes, I'm back. So the situation disaster. So I think Byung has left at it. Yes, that's what also I have to laugh and think about. That's the big challenge for layer 4 systems. And do you know what I think about the most challenges? The most challenge is not only about the communication of the world, but also about the limitation of the engineers. Because I can also remember that because I have never been in America, and one time I have seen the highway in America, I have realized the America has used the magnet points in the highway to use as the barrier from different lengths. This is totally for me not to understand and imagine. And I think it's also there are some very interesting scenarios so maybe you would like to see in China. And even since I'm based now in Shanghai, I cannot imagine what is the situation in China West, because they have also very interesting highway. So the situation is complicated, and also this very challenging for our engineer to think about all the challenging situations because they are not able to be to anywhere of the world. Yeah, please next. So what's the solution, what we are thinking about? So yeah, I think we have heard a lot about, okay, AI data driven. Yeah, it sounds very good. And for sure, AI data driven development are widely used now in automobile industry. And what are well known is now for the autonomous driving function development. But what we want to introduce it is not only to use AI in the software and algorithms development, but to use AI and data-driven approach for system development. Please, next slide. So this is traditional definitions page. What is AI? I think I love this description very well, that AI is to make a machine behave like human. This is very simple. So what does it mean, an AI-based system development? That means we try to make the system, let's say the machine make the system development like human, yeah? Because we have announced and introduced there are many challenges for the L4 system development, and this causes a lot of complication, which is over the limitation for our engineer and engineer teams. So that's the approach from point of view OEM, because the major task for us is to make the system design and finally validate the system. And we do hope that AI and the data-driven system development could help us to make it efficiently. Please, next slide. So nowadays, I hope it could be worked by click. Left side, we show a traditional video development from point of view of the use case till the final product validation, step by step. And on the right side, we try to make the simplified, namely, we need a fully automatic system requirement generation. We need an automatic code generation. We need automatically full coverage verification, and finally, and validation in iteration to make the result, and also hope to make the system improvement automatically. If please, if you could do the click, I hope. Yeah, I try to show some why we want to do it, because we need more than 100 engineers to make a function development only for the system development, and it to realize on it, it would take from 18 to 24 months. This is already much quick than in before, but even not enough. So what we do hope to use a full automated AI-based development with very less human or engineer support, and
Looks like Cheng Wang got a connection problem again. I'm sorry for that. Looks like internet still is not reliable enough to go to China. What he's trying to say here, obviously, is that there's a big problem with the traditional remodel, which the automotive industry loves and learns hard. The reliability of a vehicle today is really good in comparison to 20, 30, 40 years ago. And this is not only due to the remodel, but definitely something the industry learned very much. But with AI, this is a problem, obviously. That was discussed in the conference yesterday and the day before as well. Let's see, if there are waterfall models and all kinds of scrums and whatever behind trying to solve that. But within the traditional engineering approach of the V model, difficult. The boss of the automotive industry, he will always love a final date, and he wants to know what's going to be in the car at the final date. When you have a Scrum model or waterfall model, you never know what's going to be in at SOP.
So I hope I'm back now.
Yes, you are back. I just built the
excellent.
bridge of the complication. Go ahead.
So you must, Axel, would you like to kindly remind me when I was stopped? Because I have no idea. Hello?
It was
Sorry,
more
you stopped after you're explaining the amount of engineers and the time, which is faster already.
Okay.
But the last word
okay.
we could hear that it is still too slow.
Sorry for that. Okay. We need a more stable connection, I see, next time. But okay. Yes. If we can go to the next slide, I think I just want to mention nowadays we need more engineers and more duration for untraditional system development. I think Axel has explained is much better than before, but I think it is maybe to make to cover all the complicated world. We need a much rapid iteration. Yeah. So one thing the goal for us is to use less engineer to support such systems and make the system really to make this iteration full automatically and could be updated in very short time. Please, next slide. How should we do that? Axel, would you like to please click on it? I think this is a small animations. So basically, we begin with a function development with a use case. And in the use case, we generally need to describe what kind of scenarios should be controlled by what kind of function. Yeah, that's what we try to list. So if we get this input, this must be defined through our chefs, yeah, because they want to have some kind of airflow system. So we hope this kind of system will, based on that, automatically make the system requirement generation based on the described and defined scenarios and vehicle control models. And this should be, and after we have all the system requirements from system, from subsystem, even for of the software level and different levels. And this kind of fully tricked requirement must be linked with an existing autonomous driving algorithms. And based on that, it will be a function automatically generated. I think my colleague Björn Gisela has also make such kind of assumption in this in his EB tools. And based on that, generally, based on the described things, we can make a full coverage verification in simulation world. And this is well described also, I think, and used in different companies to using simulation to make all the possible functional tests and also software tests. Yes, next. And finally, we needed to an automatic evaluation and analysis to identify what is the problem for functionality in what kind of scenarios. Here we have some benefit with this kind of virtual AI-based and also systematic-based approach. Namely, we can easily enlarge and invite all the parameters in all the scenarios to make the function easily to be tested in different scenarios to see whether our function is or works not only in one lane situation, but also in multiple lane situation, for example. Okay, next, please. And based on that, we will try, then the benefit from this approach will also help us to make an systematic scenario generation, which will result in a full coverage test case catalogs. For sure, we have a standard which was introduced in Assam. We can use it to, I think there will be also a presentation in the following session from the 45. They have well described tools to develop that to describe the scenarios automatically. And based on that, we have also make some POC project with the AVL from class using their let's say multi simulation tools to enable to test, evaluate all the perception, decision, and also controlling maneuvers for an autonomic function in an simulation world in efficient way. Please next. One thing we just want to introduce, if there's more interest on that, please maybe contact with the colleague Jimbo Tao from AVL. They have developed these tools with the data from us. And for example, we have got some basic scenarios which recorded by Chinese scenarios, and they have a semantic configured tools, and they have development and semantic configuration tools which allow for enlarge and expand all the possible traffic parameters and to evaluate the function in really very large scenario domains. Yeah, please next. So that's what the last slide I want to show, and the videos here.
Sorry for that. That doesn't run.
No, it's okay, except but that's the final slide from my presentation. But maybe if I could summarize that in this 3 sentences, we do see that the big challenge for the airflow development is a huge systematic complication, not only in the sensors, in the reliabilities, in the safeties, but also in the responsibilities, shiftings, and so on. So we do see an AI and a data-driven approach could help us to reduce the systematic complication. This is not only for help us to enhance the sensing reliability. We can also try to use that to make a fully automatic system design and validation. And I think we do think this is also very important for us, and especially also for the OEMs. Thanks. That's all about my part. Yeah.
Thank you so much. And well, due to these internet disruptions, we have a bit stretched the time. Nonetheless,
15 minutes more to the coffee break, and I would think we come back at 4:30.
Okay, so no additional questions there?
Yeah, I got one thing, you mentioned, obviously you worked in Germany, so your thinking is trained by German automotive engineering.
So it's clear.
Yes,
Yeah.
that's clear to see. And you mentioned quite rightly perception reliability as one of the key issues for whatever kind of algorithm, to say carefully.
Yeah.
How do you measure predictability, reliability in terms of AI? Obviously, everybody will go for AI, but how do we crack this big nut of non-understanding and non-measurability on AI?
From my personal point of view, because nowadays we have a much better sensor set we could choose. I think Byung has also introduced some approach in his slide, and it's also for us is very, let's say, it's luxury for the vehicle developer. Now we can for example, have more than 4 leaders, more than 10 cameras with high resolution and more car radars. This is I think from the point of view of the conceptual redundancy, also for the performance, what we want to achieve is the best sensor maybe is already exist. And there's 2 things what we need to figure out. The firstly is I think there's a lot of approach to think about what kind of fusion algorithms should be used to fuse all this kind of multimodal sensor information together to make a better system understanding. And this is also some very good algorithms with low-level fusion algorithms, which works well. I think this was also a little introduced by Momenta in his slide. But whether that's good enough, and there's also an approach, I think, with
Now he's gone again. Okay, it makes a lot of sense. Redundancy on the sensor side, of course, is a relatively easy and proven solution within the aircraft industry as well as in the automotive industry. On the algorithm side, okay, I would have loved to hear his comment. Let's see. I think we always have to find a solution still. Okay. Jürgen, thank you very much. It was a pleasure seeing you. Due to the internet breakdowns and so on, we shift the break for 15 minutes. So Central European time, we will be back at 16:30. Thank you.
Thanks a lot.
We are back. We are back. The last session, approaches for verification and validation. And I can only repeat my question: how to validate and how to do verification and validation on AI. I think nobody knows yet. But Hermann, you might know, or at least you might have the right people online to give us the right answers. Please take over.
Hello. So we are now coming to the last session, approaches for verification and validation. And I wanted to go to the next slide. Okay, so we have 4 distinguished speakers. So verification of validation. Eventually, everything has to be safe. Autonomous vehicles have to be safe. And it's not straightforward to verify and validate the safety. And safety, of course, has to be secured. And we already mentioned AI, black boxes, they have to be safe. It's not trivial to verify and to validate. And we will start with Michael Woon from Retrospect, followed by Pauline Xu from Qatar, China. Thank you, Pauline, for joining. It's already quite late in China. Continue with Gil Amit from Fortilix, Israel, and then conclude with Huai Peng from M-City in the USA. So the first speaker will be Michael. Michael is a co-founder of Retrospect, and I understand that he worked for GM in the past and also for a functional safety company before founding Retrospect. And he will talk about excessive risk-free path planning. So Michael, the floor is yours.
Thank you, and good afternoon, everyone. It's really wonderful to
see people again after so long. It's I certainly wish I could be there in person, but just having the opportunity to be in the same conference together has been really wonderful. And I mean, the only thing that could be better than that is to talk about these topics that are really near and dear to our hearts. So please go ahead and go to the next slide. You can see by the title of the talk that I'll be talking about risk quantification in automated driving. And I think everyone knows that safety is a pretty key topic in autonomous vehicle deployment, particularly for commercial level 4 autonomy. It might be the biggest hurdle right now currently. And as other people have mentioned in earlier talks, there's a lot in safety still to be discussed relating to the architecture, making sure perception is robust, planning and execution, et cetera. But this one is a really one of my favorite topics, which is talking about the risk and quantifying safety of the driving behavior, the driving maneuver itself. If you go to the next slide. You can see that there are a number of goals here that I'd like to cover. I don't want to go through each one. You can just kind of read that on the screen. But let me just give away the ending. Okay, so the ending and the main takeaway of my talk today is that really the solution is to have continued open dialogue about this. This is how we're going to solve the safety problem. Open dialogue is the solution. Open dialogue is going to bring about the necessary understanding and also make opportunities for errors to be found as we're able to express our ideas openly. And again, this is to everyone's benefit. It's also to our own individual benefit as well, that we get that feedback when we have that conversation with others who have a different perspective with us. So again, the one takeaway and the conclusion of my talk for today is that we need more open dialogue, and that is what's happening based on the wonderful presentations earlier today. We can see that is taking place. And with that, yeah, we can go on to the next slide. And first we want to do is we want to define risk and just talk about that for a moment. So what do we mean by risk in automated driving? You can go to the next slide. The way we pose the problem as we started to tackle this a few years ago was we wanted to imagine a scenario, a simple one that's shown, there's a vehicle with a straight velocity, and let's say a pedestrian suddenly appears. There's ways we could think about the subsequent behavior of the vehicle. And if we change that behavior, or we change the proposed trajectory, for example, there could be greater or lesser risk associated with that. For example, the car could brake at maximum force. The car could turn as quickly as possible at maximum steering rate. It could do some combination of the two. It could swerve to the left, but if it's too close, is that too risky? If it's too far away, is that also risky due to the tractive effort? So that's really what we wanted to try to identify, is if we make a minor change in the behavior or the trajectory, what minor increment or decrement does that make in the overall risk of the driving behavior? So that's how we originally phrased the problem. We can go to the next slide. And what some of the uses for doing a risk quantification, for example, if we have a trajectory and we have some evaluation of risk real time, we can do behavior and scenario identification. Again, we can characterize one scenario as being more or less risky than another scenario. And we can repeatedly evaluate this. It's not subjective to, say, a particular region, but it's objective. If we're an autonomous vehicle developer and our job is to come up with the optimal trajectory, we can incorporate some sort of a safety risk quantification into our optimization algorithms to develop the right trajectory. And that, this basically comes down to cost structuring among the other various trade-offs that you may need to consider. Another form of this would basically be to put path planning constraints in place. Maybe we want a constraint in which we say we'll never exceed a certain amount of risk. And the use case, the final use case I'll mention, which is really most important for retrospect in our organization, is safety monitoring, which in effect is actually a combination of those three that can be done in real time or post-processing. It's sort of looking at the sensitivity with respect to the constraints, or the stability with respect to the constraints. You can go to the next slide. And this is sort of represents potentially all four of those use cases that I just described. For example, if you have an autonomous vehicle in the lower left, you could come up with an optimal trajectory, such as that green line in that low risk space indicated by the light blue. You could represent a constraint, such as the constant red line risk constraint. And that's shown sort of as a red boundary that the trajectory can never exceed. And we can monitor the environment and characterize the environment. So this is the type of questions that we wanted to answer. And this is what we're going to talk a little bit more about today. You can go to the next slide. You can go forward one more. So obviously, skipping ahead a lot here, it should be no surprise that velocity, of course, is the key factor. It's where all the energy comes from when damage is done that causes injury to humans. And we're actually just going to specifically talk about collision risk. I didn't really mention that before, but as you can kind of tell, it's very intuitive that collision risk is the most commonly assumed risk when we talk about autonomous vehicles. There are many other types of risk, but again, I just want to emphasize that we're only going to talk about collision risk, and that's why we're talking about velocity right now. So you have a closing velocity, which is relative speed of how fast two objects are moving towards each other or away from each other. If they contact each other, that would be an impact velocity. You can go forward one more. Depending on the you can go forward one more, please. Yeah, and depending on the collision characteristics and the mechanics, the masses of the two objects involved, you could estimate or calculate a change in velocity, a delta velocity of the individual actors that could be potentially involved in a collision. And then that final, one more click, please. And then this will get us the probability of injury. This is a kind of well understood field for decades in accident crash reconstruction, where researchers have identified likelihood of various types of injuries that occur based on the delta velocity or impact speed, et cetera. And so this is how we can actually get to that actual risk, where we have a likelihood or percent of a type of injury occurring. That's really the units that risk are quantified in at the end of the day, is likelihood of a type of injury occurring. We'll go forward. So here are the major challenges, and what we're going to talk about today is I'm not going to give you all the answers. I'd love to be able to give you all the answers, but I really this is meant to be engaging and for you to kind of think about and kind of own and talk about some of these problems. So the first major challenge, if you can go forward one more in this sequence, is I mentioned different types of injury types. For example, we have probabilities of a slight injury, a serious injury, or potentially fatal injury. And one of the biggest challenges that safety engineers and ethicists, et cetera, have to deal with is, how can we potentially combine these things? Is there some sort of weighting system that we could come up with that optimally sort of combines these? Another question is, do we need to even combine these? Right. So that's really a question. Can we come up with 1,000 bruises equals 10 broken arms, and that equals 1 potential fatality? I don't know. That's a very difficult one, and one that is sort of a stumbling block. The next one here is combining risks related to injured persons. Should there be some sort of recognition of multiple risks if more people are involved? This is very similar to a trolley problem, perhaps. Again, there may not have to do this, but this is a question that folks have to wrestle with. And finally, the third case, if it's known, for example, we have a driverless delivery vehicle with garbage or with delivery boxes, and it's known that it is potentially going to collide with a tree, and there's no other humans involved, therefore there's no probability of injury. Should we come up with some sort of a pseudo risk metric or risk metric? Should it be
should we recognize dollars and the value in that risk metric? How would you evaluate this, for example, if you were a local authority and you had an autonomous vehicle operating, would you have rules and regulations on this type of operation or risky behavior? Moving on, thank you. So how do we capture these kinetic energy predictors? We can move on to the next slide. One more, please. So just to talk briefly through a couple of these, very common, I mentioned closing velocity, right? That is sort of the common denominator that precedes sort of all of these potential injury scenarios, is the closing velocity, and very commonly recognized as the time to collision as being one of the sort of KPIs or key metrics here. So time to collision will help us separate, for example, the difference between the parked blue car in the upper left, number 3, and the oncoming car, number 110, on the bottom relative to the black vehicle. That time to collision helps us show that, hey, there's a much more urgent situation here between those two objects. You can move on. Thanks. These next two, what we see here is limitations when it comes to time to collision. So for example, in the scenario where the two cars are turning concentrically to each other, if you calculate the minimum distance and the velocity, you get very, very low time to collisions. Usually we've seen in naturalistic data, certainly less than a second, probably about half a second on average in these types of maneuvers. And that seems incredibly short and incredibly risky. And in other cases, such as the pedestrian on the right that's about to approach what is a crosswalk in that case, there is anticipation by the other road users of the coming potential dangerous scenario. And so they start to do some early mitigation, slowing down just a little bit, being a little bit cautious. And what that does is that actually limits our ability to quantitatively sort of see, what is the actual closing velocity or potential time to collision. Those kind of go to infinity. Moving on to the next slide, please. And so one of the things that we're working on sort of as a latest solution to this, and I know others are as well, is the recognition of how easy is the scenario to control. And so this is an example where we're just taking what is the ego vehicle's velocity and recognizing what would be the minimum necessary braking deceleration in this case. You can move forward to the next slide, or the next frame here. Thank you. Similarly, we can also look at lateral control, and if we wanted to, we can even combine these. Lateral control has a couple of components, but if you click one more, we can combine these to show that there is that inner circle is showing that there is some minimum amount of necessary traction effort necessary to avoid the collision, and we can characterize that and use that to help sort of qualify some of the more urgent critical time to collisions and some of the less urgent ones. These are ways that help us kind of sort through and filter through the data that we see. We can move on to the next slide. But this really leads us to a necessary component, I believe, that's going to be not inside the vehicle, but outside the vehicle in terms of our ability to universally sort of comprehend and assess driving behavior, is sort of an understood predictive model. And this is something that actually all of us intuitively have as humans. We can all go out and look at a traffic scenario, and we immerse ourselves in that traffic scenario. And if we see things transpire and we suddenly kind of hit the pause button, we all have an intuitive understanding based on kinematics of how things are going to play out over the next few seconds. There's really, a very high amount of confidence associated with that. And we can also say, you know what, I know what's impossible to happen as well. So I think a predictive model is a necessary component to universally understanding and quantifying risk. So some of the questions here is, if we want to extrapolate based on known and existing data, what's the appropriate method for extrapolation? What's the appropriate data accuracy? You can move forward. There's actually a few more here if you just want to click, I think, 3 more times. Yep, that's good. Again, you know what, in order to anticipate the time horizons that are relevant for decision making, we're usually looking at around 5, 6, 7 seconds, even in low speed urban scenarios. That's about the minimum amount of predictive horizon time that we need to be able to anticipate potential collisions in which a change in behavior would be necessary. So how to accurately predict out 5, 6, 7 seconds, or I should say reasonably predict, we have to make some assumptions. And what happens if we make those wrong assumptions? Do we need to incorporate certain contextual information, such as the road conditions and the infrastructure, crosswalks, et cetera? We've seen a lot of dependency on crosswalks. You can move forward here. One more, I believe. Yeah, so the problem is that too much context will make the predicted risk look too good. If we make too many assumptions, if we have too much information and we plan out everything in advance, then everything is going to go well based on our assumptions that things are going to go well. And that may limit our ability to see actually bad behavior that we'd want to pick up. Likewise, if there's not enough context, we may generate too much noise, and we may have something that's producing too many false alarms. So our recommendation here is use the minimum amount of information first in order to distinguish the good versus the bad, and gradually layer on slightly more context or information as needed. Next slide. And you can click it 2 more times. What these all represent basically is, at the end, we're saying if we go back and revisit those scenarios, we can make some claim about the controllability of that scenario now, using a combination of instantaneous controllability margins or predicted controllability margins. We can make some claim about how likely we think or unlikely it is to control against the anticipated risk. Next slide. Yeah, and I won't go line by line here. This is somewhat evolving, but this is sort of represents our latest methodology. At the very top, of course, we have to recognize, actual risk. If a scenario shows a collision, we do need to estimate that. Again, that's a very well-established field in science. But as we go down through these layers, we make sort of alternating trade-offs in which we assert there's a likelihood of injury, but then we condition that with a probability of avoidance or of unlikelihood. And then at the final case, we do make some assumptions in order for us to look at both worst case and best case. We do look at a likelihood of if there was some avoidance potential. And one of the ones that we see the most often is that pedestrians can often avoid the injury if they simply stop walking, or a cyclist can avoid the injury if they simply just move slightly. But there may be some rules that are more contextual about the expectation of a vulnerable road user to yield in certain cases. And so if we're always expecting, it's very easy to control because we expect that vulnerable road users will always yield, we may need to condition that with some likelihood of happening. Maybe in certain cases that is acceptable to consider. In some cases that may not be. Next slide. And finally, if folks are familiar with ISO 26262 and our initial hazard analysis, the methodology we're proposing is somewhat similar. We might start with what is the worst case maximum potential. Let's all agree on that first. Okay, there's this much closing velocity, there's this amount of mass, there's this amount of potential injury that can occur. Then we look at how controllable is that and how likely or what is the probability of that scenario playing out. And again, that helps us look at the worst case and best case. One more slide here, or one more click, excuse me. The key situation, again, if we're familiar with 26262, is that this is for the current given scenario. This is very different than when we do analyses at our desk and we say something like, 1% of the time pedestrians suddenly step out in the middle of traffic in the middle of the road where there's no crosswalk. We may be able to say that. We may have data that claims that. But what we're talking about is now the vehicle is actually in that scenario and the pedestrian is actually stepping out in the road. And so given that that's a 100% fact, could still do an analysis to figure out under these conditions, what's the worst case, what's the best case, how really dangerous is this particular situation now compared to some other situations. So that's the key takeaway there. Next slide. So the implications for the developers, the testers, and the regulators. I'll talk about this for a little bit. On the next slide, you can probably go ahead and hit it a couple times. Thank you. Yeah, so for the developers, the number one implication is be prepared to have to explain your methodology for how you evaluate risk. Okay, you developers are as familiar and much more familiar than some of the problems I just listed here. And also make sure to incorporate real-time risk monitoring in all your data so that you can capture both critical events in which you exhibit both good behavior as well as bad. You still want to be able to capture that critical event, and then use that to your credit. If the vehicle behaved well, you want to preserve that and get credit for that. And if it was bad, you certainly want to keep track of that to mitigate your operation and improve things. For testers, you definitely want to find ways to exploit difficult to predict scenarios. Certainly think outside of the box in terms of white box or black box testing. Think, out of this world, unrealistic in a sense, because if you can focus on identifying the autonomous vehicle's breaking point at which it's recognizing that it's not able to comprehend the risk that it's thinking, that gives you a tremendous amount of objective data about the safety of the autonomous vehicle. For regulators, it's not just the developers. I think regulators too have to be prepared with their own risk quantification methodology. They need to have their own way to think through some of these problems that we've outlined here today. If they are truly intent on actually enforcing and holding developers accountable under certain situations, they need to have that ability to at least, kind of bare minimum, evaluate, at least the superficially observed behavior, if not actually be able to analyze some of the internal data that the autonomous vehicle may have in the event of some sort of a incident. And then, of course, encourage independent evaluations from developers. Final slide. And you can click, I think, one more here. Yeah, so again, I told you at the beginning, overcoming the challenges is encouraging open discussion on the subject, especially before commercial operation. I think state agencies and authorities, rather than say, hey, pay us $100,000 and we'll give you a license or some method like that, right? Show us a bunch of paperwork, pay your fees, and then you can go on the road. I would say this, why don't you put a team together, publish a white paper and make it publicly available how you quantify risk and define risk. If you can do that, then we'll let you operate on our roads. So with that, I would look forward to questions, and thank you for your time.
Thank you very much. So I do not see a question in the chat. Are there any questions? I have a question. So, the question is, so this sounds very much like a concept, and have you made already the next step to implement an algorithm or for path planning, or where do you stand? And open discussions on the subject. So this sounds like engaging in a standardization committee on the subject matter. So like for example, the IEEE P2846.
Yes. So to answer your first question, like where do we stand at retrospect? Well, we're happy to engage in forums like this and disseminate as much of the latest information we have. We do have open access; anyone can use it. Our current open level of risk analysis. You can go to our website and upload some scenario data and get a printout of how we calculate the risk line by line. We would love to eventually make that open source. To be frank, we think that's the most way to gain confidence, and frankly, that's probably the quickest way to get the safest solution. As far as standards go, we have many standards, as you're aware of, and I think there's a lot of formulating about the approach and the problem. And what would be really valuable at this time is if there was more, I think, open implementation available for people to kind of get their hands on. And so that's probably what we're most focusing on, if that makes sense.
Thank you. Are there more questions?
Yeah, I have a basic question. As far as I understood your model, the idea is to change the software or prediction model or whatever, and to see the reaction of the system to go into better direction or less good, whatever. Another idea of applying your method could be as well to take one car made by company A or B or whatever, and another car by another company. Of course, not the real car, the model, the digital twin of it, and then to compare which car under a wide range of different risk scenarios performs better. Is that something you are targeting for, or is it too much?
Oh, absolutely. That would be ideal. I think that would be fantastic to do a sort of a independent benchmarking, perhaps. I completely agree. Yeah, we would love to see that.
Something you did think about already, or did you try it already? It's of course, I know how difficult it is.
Yeah, no, we would love to do that. I think that's really our goal with making the initial sort of scenario analyzer open, so that anyone can try it out and just see how that works. Yeah, I think we would have to talk with the right collaborators to kind of procure the right vehicles and decide what type of scenarios we would like to do a risk analysis on first.
Would be a wonderful model to reduce the amount of sensors, for example. Is it really necessary to apply another camera and another LiDAR and another whatever? Does it do anything really in terms of predictability or to make it better? Okay, sorry.
So there seems there are no more questions, and we are. It's 5 o'clock. So thank you very much.
12 o'clock.
Thank you very much, Michael. The next speaker is Pauline Zhu from Qatar in China. So Pauline, are you with us?
Yeah, Herman, hi, can you hear me?
Okay.
Switch.
Thank you.
Good.
So, yeah.
All right.
Pauline, and I just wanted to say a few words about your role. So you are a senior technical supervisor of Qatar, but you're also engaged in standardization quite much. So as a secretary and expert in ISO TC22 on test scenarios for automated driving systems. And you also lead the work package or the working group 1 in the IMTS about test scenarios, definitions, and harmonization. So with that, the floor is yours.
Thanks, Herman. Good afternoon, everybody. I just want to, before I just started this part, I just want to apologize a little bit in advance because as Herman was introducing, I have multiple hats. Unfortunately, for this is more about another perspective or even another part of the things where Qatar does a lot, which I was involved. I am involving as well, but then this is a little bit different from what I normally speak of. So, but I will try to walk you through in this direction. So this kind of presentation a little bit different from what I normally will do to everyone. So we can jump to the first page. So because in this background, I was
sorry,
Yeah.
could you fix your camera? We can't see you. Only.
Okay, that's better.
Oh, thank you. Yeah, that's
Good.
perfect. Thank you.
Yeah. So as you can see, this is I want to do a little bit introduction of Qatar. So my team, it's called the Automotive Data of China, and basically we're focusing a lot of different type of data. So for example, there's carbon data, ecology data, and market data as well. My team focusing a lot on simulation data. That was the core part of our business. And we go to next page. So in general, what we actually been involving a lot is that the cases of this is our business on intelligence vehicle business. Yeah. So we have basically, you can see, is a huge team. So I think in general, this covers about like 300 employees in my company. And the reason why this is so huge, like also where the reason was because in the autonomous driving system, or in the autonomous driving world, there's a lot of requirements in China. Then so trying to get everyone involved, it is very much needed, a very huge platform. That's why where the AD chauffeur was actually been built. So if we go to the next page, so we can take a look at what's actually been the status in China specifically. Right, just I think this a little bit lag on my computer. Okay, so let's go to the next page, please. So in our cases, because you can see Qatar has covering a lot of different kind of areas. So it's a little bit different. So the background in China, I would say a little bit more on this, is that it's very much in a conflict. So Qatar's majority of the business on the in the robustest, like old-fashioned way of testing. So there's like a lot of people doing vehicle dynamics, testing and proving grounds, etc., etc. But on the other hand, China does having a lot of people working from a new perspective, unfortunately. So as in what I meant is, it's like two different kind of, two different kind of sides. So one, people came from the traditional testing, play a very strong suit in Qatar. And the other side is like, there's people in my team, mostly are people do like research on, machine learning, deep learning. They can every day they do tuning a neural network, etc. So those are two type of people, and that is one of the conflicts actually being existing in this world in higher level autonomous driving, because it's like you have two different kind of things in way of tackling the problem. One is pretty much rely on a very solid train of thoughts or very solid method testing, and the other way is like you let the data flow. Which leads to new problems, new issues, and also new ways of tackling problems. So we go to the next page. So what do we realize, especially because my team focusing a lot on the data being collected, is that there is a huge advantage by if you're using data. So the methodology behind this is very simple. So most of the time, what do we use the metaphor is like, we always have a prior knowledge. I can write down a lot of requirements, or actually a lot of things to be tested before a test actually being started. But then, once you see a lot of data, when you have a lot of experiences, that you have beyond the prior knowledge is more important is the actual distribution, or actually the actual data lodge of testing are actually done, system. And then that's what happened. Then you have a better understanding of the prior knowledge, go to the posterior knowledge, and you end up with actual better understanding of it. So what does my team actually trying to value is basically, the middle part. We're trying to build a platform in China, and they're trying to basically enlarge the middle testing part, which simulation play a huge role. So the current trend in China, well, in general for this kind of cases are actually, so China actually using a lot of a lot of government money actually building a lot of infrastructure, so proving ground, etc. But also they do a lot of data centers, so they do build a lot of servers, and there's a lot of supercomputers, for example. So for example, in my city, there's like 2 supercomputers like centered. You actually have massive computational power. So once they have that, then the OEMs in China start to realize, okay, literally every single OEM in China has their own servers and have a lot of computational power. But then they realize, what do you use for them? And that's where simulation came up. And we realized, by actually utilizing all those power, there's something we can do a lot in simulation. So that's why AD Chauffeur was being introduced in car. Let's go to the next page. This actually brings us to why we're actually quite linked to a lot of global participants are actually global partners, because we realize the advantage of this is a lot of things. We can do this, we can learn from the others, and we can basically try to cover a lot of things in simulation. So advantage is basically we can do a test over and over again. There are many ways of doing so. For example, one team and my team actually are focusing a lot on A/B testing. They just twist a little bit of the parameters and see what's different in different cases in one way. But in general, I think most of my team members actually agree pretty much on scenario-based testing. So they either thinking, with their expertise, came up with corner cases, building all those up and trying to feed them to the system and try to find the vulnerabilities of the system. And in the other way, we're trying to throw them a lot of data, trying to let them learn themselves a bit more than trying to do that. So for example, Michael brought up a little bit about, we're doing prediction of the trajectory a little bit. And I think, I think there was a team in Qatar actually doing this by just feeding the computer with different kind of, many different kind of trajectories, try and see if it can try to having a better, a more accurate prediction on it. So that was something they're doing a lot. Then that's one major area because of this computational power. The other one is, Qatar also do a lot of, proving ground testing. Then there's a lot of things saying, hey, how realistic the simulation testing are. And there's many kind of comparison being done. Then we're having a bunch of data on that and trying to see we can implement it in simulation. And also that requires a huge platform that actually can get it done. So that's the 2 major parts where why this AD Chauffeur will actually be started with. So let's go to the next page. So in general, that's where we decided to throw this kind of platform and actually pretty much in the service for most of the Chinese customers. And in general, basically we're trying to cover everything as much as possible. But it's a huge work. So people are doing a lot of dynamics, sensor modeling, algorithms, scenario editing, which is actually where my focusing on pretty much on reorganization, fuzzy testing, virtual test simulation. And then we're trying to involve all those kind of mapping companies as well, 3D reconstructions, user support, real-time evaluation. So that's what actually most of the this basically wrap up in this is the whole thing where the whole the industry in China where they're actually focusing a lot on. And in each part, that's where we're having this connections for all the people who knows me in person. So we go to the next page. It's basically we can talk about what actually being specifically in this platform. So the AD Chauffeur is the products we're actually providing to most of the companies in China. So they are basically focusing on 3 different layers. So we do a lot of things in data processing. So I think I've been talking to a lot of customers, my personal customers, like like the new ones like Neo, like Exponent, etc. They keep saying, we do have a lot of data, but most of them are garbage in and garbage out, right? So the problem is they need a very good tool to actually clean the data up. So I think if you look at what we've been doing a lot in different level on international levels, it's basically we keep saying where data is from, because every day I see data from from many OEMs, and we're trying to clean them up. So that's been like that. That took like most of my energy. So we're providing tools for them. So there are labeling tools, there are cleaning tools, there are actually managing tools, and processing tools in general. And to be honest, it's beyond those tools are actually a service to everyone. But at the end of the day, it still requires a lot of manual work in general. I think we do hire, but that's a good thing about China. We had to have a lot of people who actually can do this kind of processing as well. So there are, I think there's more than, a few 100,000 people who are actually been supporting us doing the data labeling manually. Then we starting to building our, first round of data, database in general. Then once we have that, the thing where actually the AD chauffeur was pretty much focusing on is how we implemented it in simulations, right? So my focusing pretty much on, formatting them, fitting them into different kind of simulators, and then providing, testing results and, trying to do that. And then there are other engineers working on, how to editing them. So that part is basically trying to either draw the trajectories for the vehicles, trying to replay the scenario actually being collected, or, in general like that. Then trying to match up with sensors. I think the expert from Geely mentioned, there are different setups for different sensors. I think every day I see like, dozens different kind of sensor setups. So they do a lot of things on that. Then, there's a team in Qatar who also do a lot of things on traffic flow simulation. It's a huge area, it's quite different, and it's just like have a wider range of what actually they're doing. Then eventually we're trying to get involved in different in-loop testing. And then, to power them up, then we try to connect with the actual server, the clusters, and, the cloud computations. And then eventually those are being implemented in different servers, then trying to test them out, trying to have like, a constant keep up with those things. So that was the idea why we're actually trying to do this. And at the end of the day, the main point of this is basically to tackle all of us, everyone in China agrees that in this area is, for high level autonomous driving, this could be, one of the possible ways. So for example, where the homologation, in China, they're actually focusing not only on, individual kind of testing. They do actually require companies to build their own server, building their own, simulation, tool chain to actually get this done. So that's part of the requirements for the companies to actually having the license for level 4, for example. So we'll go to the next page. So the first time my team starting to prepare with this probably at the start of 2018. And the first version of this was released in September 2020. Basically, there was 6 core functions. They do a lot of simulation cloud, scenario library, which is what my team focusing on. Then there's, for production level dynamic simulation, sensor simulation, and also different kind of in-loop testing and rapid validation. Then we're trying to focusing a little bit more on the major 3 things where we think that the Chinese OEM actually are leading with. So we're providing 3 major functions. One is the rapid testing for different kind of algorithms, and the other one is pretty much on scenario editing. So then it's basically automatic testing. So we go to the next page. I think it's going to be all right. So this is basically a little bit demo on what this actually are doing. So in general, I think most of the stuff our people actually are looking at is, a bunch of their inputs. So this is are the typical inputs we have from the collected data, for example. Then once we have that, I think there are different ways setups, and you had to provide different APIs, and that's what they're doing. Then once this been through, we're basically trying to connect all their algorithms in the system. Then my job is basically to feed them with different kind of scenarios. They would be written in descriptions first, language description. Then we translate into machine readable languages and trying to feed them into a system and trying to test them out. I think next one should be the video. Actually, let's go to the next page. So here are the 6 part where actually go in with individual parts. So one thing in the first one, we basically, sorry, can I go back in previous page? 2.4, yes, 2.4. I think it's a little bit laggy, but okay. So 2.4. So the one is the map editing. So that part we do a lot on the way on the 2.4 or 2.5. Okay. If we start, one basically we do a lot of editing and mapping and processing. We do different kind of static entity, adding curvature, feeding, trying to mix up with different kind of junctions, etc., etc. Then the next one is automatic testing. We do a lot of things on, enhance with different kind of companies, servers, and trying to do their different kind of databases in general, and trying to do the executions, take a look on different kind of configurations, generation of batch of different scenarios, and trying to run them systematically without actually doing so. So that was in general the core part. Go to the next one. Next one is the basically there's a video about this in general. If we go to the next one, so in general we do providing this. So this is I think it's a pretty good reference.
Do you want to play the video?
Sure, go ahead. Great. I didn't expect the firework to pop out, but anyways. The reason why we're actually doing this is a lot of actually supporting the local government actually to providing a lot of kind of forum, actually doing a lot of exhibition and also conferences. This is basically a lot of good training for people actually, people who actually want to be involved in this kind of industry. So actually that kind of, support for the society is also part of the culture of Qatar, unfortunately. So we're providing this to a lot of universities, to actually all those institutes, and then providing also different conferences for online testing and online hackathon, for example, and then providing that to them. And also a part of that is actually we're actually teaching courses in universities with this platform, so they could be provided for that. So that is I think there's one more video at the end of it, and that will be pretty much it. Hopefully there's no. So this is the basic for the competition. So I think that's the last slide, but I want trying to basically wrap up why Qatar is doing a lot of efforts and providing the AD chauffeur platform, and specifically how it actually basically connected to what actually I do. I think in general, the feeling in China is they have two different kind of culture. One is the one very, authoritarian, as in, they want everything in control. They want to have everything clearly written down, and all those things are very, very rigorous and very robust in doing that for high level testing, which is in general that is the feeling from old-fashioned people. But for us, we're in this we don't believe that kind of thing can be done for high level automation testing. So we're basically trying to provide a platform where also supporting both sides. One is for those people who are very robust on their ideas. The other one is pretty open-minded, throwing a lot of probabilities in their either in their algorithms, in their methodologies, and trying to figure out more kind of dynamic kind of system. And in there between, one thing is basically utilizing all the thing we have, either the proving ground, the testing data. So that's why we're providing a open platform, AD chauffeur, where we can connect all the people in there, and eventually it should be in my personal perspective, I think to actually get this done, you should actually definitely try to involve as much as the data as possible, and then utilizing what's actually in the middle ground, where between the prior knowledge and posterior, that's where all the musics are playing, and that's where we're actually been focusing a lot on. And that's what I have. Any questions?
Thank you, Pauline. Are there questions in the room? I'm tempted to ask 2 questions, but we are a bit short of time.
Just one question maybe is on one of your pages you showed there was a test report mentioned. What kind of, but there were some wild graphics only, so I couldn't imagine what is the test report really showing? Is it something like what retrospect would refer to as a risk evaluation? Is it a Word document with whatever kind of words, or what is the result really in terms of a test report?
So actually, Axel, that part actually I was the one who developed it. I think in general there's two parts. One is the expected results, and basically that's been written before the test being thrown in. A bunch of criteria and KPIs are actually being written there. And of course, the second one is after each test there will be a performance, during the performance is done. And there is a little bit, gap between them, and this recording all the biases, all the variances between these two kind of prior kind of KPIs and criteria and the one done that. And that thing give you a little bit, understanding how your performing are done for your system are done in the given test cases or test scenario. And
maybe the question in terms of the World Intelligent Driving Challenge, I think that is an international, or it should be an international level. So do you have that kind of tool in English as well? Can you change the language? Or is it internationally available? Are you selling it?
Currently we're trying to cover the Chinese OEM first. We want to be the actual window to everyone else, but we in the AD chauffeur, I think at the end of this year's kind of release, we'll be having an English one. And we're definitely happy to show everyone else, like we have annual reports on that, where actually the results are looking like for every OEMs in China.
Thank you again, Pauline, and thank you for being with us almost at midnight.
Not almost. Half an hour after.
Actually,
half an hour after. Oh, okay. So thank you.
Finally, you can go to bed.
Thanks, you. Guys. So the next speaker is Gil, and Gil has had an amazing career. He was vice president of Intel and is now the chief regulatory affairs officer of Fortalix and also co-founder. And it seems you are everywhere in all standardization organizations and even in UNEC. So Gil is with us here in the room, and I'll hand over to him. The floor is yours. Thank you. So why don't we see the video? Yeah, now let me see myself, and it's good. Why Pauline is still on? Pauline.
You have to speak, then the change system.
Thank you. I'm just looking forward to your presentation. I can hear you.
Yeah. So
switch on your mic, please.
Yeah. I cannot. Okay, I'll pin it.
It's automatically doing. Just go.
It should do it. Okay. So thank you for the opportunity. And just to add some brief introduction, Fortalix is kind of a unique startup. It was founded by non-automotive persons, since Axel here is priding himself for being in automotive for the last 30 years. We are priding ourselves, 40, okay. So we are priding ourselves for not being in automotives and being some new perspectives and a new mindset into that. So I was requested to connect the world of standardization and evaluation. This was following the autonomous event in which we jointly participated in a workshop. And I will just give a brief overview of the world of standards and regulation. I missed the morning in the previous workshop, so I may be repeating myself. And from that, I will dive how these will affect or relate to the technological challenges that we have, and also show some pragmatic solutions. Now, the presentation that I submitted contains 65 slides. I do not intend to cover all of them, okay? There is a breakpoint in the middle with the title backup slides. The intent was to deliver as yeah, oh, you chopped it, okay. Yeah, the intent was simply to supply information. So let's start with trying to clarify the world. There are standards and there are regulations, and they are being developed and handled by different entities. Standards are developed by different standard development organizations. We have heard some of them, and in the next slide, we will see some of them. And the common mistake is that the fact that they are not mandatory to comply with. Yeah, what do I need to do? Okay, it's still, we see most of them. Bolin is still there. Bolin, it's hard to get rid of you. Yeah. Okay, we'll see. Well, I can try and pin it. You can, and then. Oh, yeah, now it's pinned. Okay. Standards are not mandatory to comply with because they are just recommendation. They become mandatory to comply if someone that has the authority to tell you to comply with the standard is telling you to comply with the standard. And one example is USB. USB is a very common standard. No one is forcing any laptop manufacturer to put it in the laptop. This is market forces. However, the EU decided to issue a regulation to put USB-C as the charging port. Okay, they have some issue with some fruit company from the Silicon Valley, but that's an example of making a standard mandatory. A lot of time, standards are really evolving from the industry. Then there is a committee that defining them as a standard, and regulators really leech on that and recommend on how to use it, or enforcing some usage. So in the automated driving system world, we have several players. SAE from the US, ISO, which is globally and also getting input jointly with the SAE. They have some collaboration agreement. ASAM is a European German consortium, which is developing standards, and we'll see that later on. IEEE, which I would define as somewhat late entrant to the world of ADS. It is a very well-established player in other domains, but for automated driving system, it's still struggling, I would say. And another late entrant, which is trying to capture standard marketplace, is UL. UL, again, they are well-established in other domains. In automated driving system, they hired Phil Koopman that wrote for them a UL 4600 with a committee, and that's their presence in the automated driving system domain. On the other hand, on the regulatory world, we do have other players, right? We have different country level authorities, ministries of transport. And we also have, whether you look at the different federation, the state level or the province level or any other local government. And we have the federal level. Oh, I had a typo here, it's NHTSA, not NHTS.
And these are examples of federal level authority that may set regulation for a specific federation. We also have a major player, which is the WP29, the World Forum for Harmonization of Vehicle Regulation under the UNECE. And in a previous presentation, the morning one from TÜV Süd, we saw the full list of the informal working groups that are working under GRVA. Another player in the domain is the World Economic Forum, which is mostly playing as an influencer. They're trying to promote economic programs around the world. Recently, their focus is in Dubai and Emirates, and they are promoting the deployment of autonomous vehicles in that area with a lot of cooperation from the oil money over there. So it's working well. Now, here are some nice slides that I got from the autonomous event, and I thought it would be nice to share because they give you a good perspective on the evolution of those regulations. So if you look at the world of vehicle regulation, there are regulations that are really regulating the vehicle itself, and there are regulations that are mostly impacting the drivers. A classical example is safety belts. If you look at the US, there are regulations that require you to have a safety belt in each vehicle that is on the road. However, the provision that the driver or the other passengers must click the safety belt is a state level regulation. And definitely state can either require that or ignore it. So in this world, there are things that are enforcing on the drivers and those that are enforced on the vehicle. And what's happening is that as we are progressing toward automated driving system, then this line is becoming blurry. And actually, you should ask yourself, okay, so what should happen, right? Should we, the vehicle regulation expand and remove the load from the driver, or the driver regulation actually be enforced on the vehicle? And the answer, or what I believe is the right answer, is that actually the vehicle regulations, okay, or the regulations that are enforced on the vehicle are taking the ownership from the driver because the system is actually driving the vehicle. So requirements that were imposed on a driver before are now imposed on the automated driving system. You have one example here. There are other examples. Earlier, there was mentioning of Intel's RSS, for example, and over there, the automated system has to give the right of way. This is part of the statements in that model over there. So that's the direction that the regulation are going. That's the direction that the WP29 is going. This will be the direction that the German law will go once the ordinance will be set. And it's happening all over the world. Now, what is the problem that the regulators and actually other entities that are dealing with liability need to solve, or what are they handling? So in general, it's the question of whether this system is safe enough. And there are many questions that need to be answered, right? There is no way to rate the system today. We saw some ideas from Michael and others. There are no real standard to set safety, and I will dive into details later on. And there is a gap. They don't know what to demand for testing and homologation and certification and pick your term. And what does it mean that an automated driving system is safe enough? Now, the tools that are available for those regulators and entity are at the bottom of the slides, right? There is test driving. You can put the vehicle on real life test driving. You can put it on test tracks. You can put it in different X in the loop systems, right? To different level of hybrid systems. You put the vehicle in a room. You screen movies in front of it. You water it so it may think it is raining. Well, having fun, right? And of course, there is the world of simulation, which is the so-called virtual testing. Now, the problem is that till today, there were no good measurements that you could derive from these tests. And in fact, the only measurements that has been used quite widely is the quantity of miles that have been driven. And when you are trying to think, why was this measurement used? Then the only valid answer you can find is because you can measure it. Okay, it's like looking for the lost coin under the streetlight. It's a measurement that means practically nothing because not all miles are born equal. So you cannot really use it. Recently, or 2 years ago, there was also the measurement of number of a disengagement, which is yet another one that doesn't help you. It depends on the test driver or others. So this is the problem the regulators needs to deal with. And in some cases, you know, even you cannot rely on a good history. This is an example of an automated driving system that went through an evolution. And luckily enough, it fits the levels of the SAE, though, right? Level 1, 2, 3, 4, and then you go to level 5. And level 5, you remember, after there were a lot of safety arguments in place, the design domain is very similar for all those systems. You can assume, and in reality it is, there was reuse of existing software that already proved itself, and a lot of virtual testing and simulation. And yet, in 1996, when Ariane 5 was launched, yes.
Tous les paramètres propulsifs sont normaux et la trajectoire est normale.
Very expensive software reuse issue.
37 seconds into the launch.
The analysis showed that this was really a reuse issue and that didn't fit the right hardware on the system. Okay? And there are many more details, but this is really a demonstration of some of the problems that will come with this automated driving system. And what do we see there? We talked earlier about the culture change in the automotive industry. Now, for years, the automotive industry had to test mechanical and analog phenomena. Okay, and these may behave differently, but they behave in a continuous fashion. So you can apply different testing methods based on the assumption that you are searching for local minimum or local maximum. And all the classical fault analysis methods and hazard analysis were actually developed a long time ago, in the 60s. Software was just starting to show up there. Now, the problem with software is that you are living in a different world. Software issues are either systematic, but in that case, they will be singular, or they may be very random by nature. So if you want to describe it graphically, I simply found these graphs on Google because they are nice. Okay, you are looking for like that single spike in this whole space, or that spike here in this whole space. So you need to develop different methods in order to evaluate and test and measure those systems. Standards are evolving, and they are trying to cover all these areas, including metrics and measurements. Okay, but they are still in evolutions. There is a lot of focus on the methods. There is a lot of focus on the process. That's easy to set, but there is less work or not mature enough work on metrics. So this is just an example of the different standards that are being worked on, whether it is by ISO. SAE ORAD is a generic name for a set of standards that's being evaluated. IEEE, you can add the P2851, but basically a lot is being done, and a lot is in overlap, which is also not helping solve this problem. Just a quick overview on some of the standards. This is ISO 34502. Bolin is the secretary for the ISO work group that's working on it. And this is really a scenario-based safety evaluation framework. Again, it describes a process. This is really the key. It describes the process or the different steps that you have to go to, not what to do exactly, or what is the implementation of each step. But at least it gives you a framework. Right now, ISO is also working with a major work group on 5083. This is yet another example of something that may become a process. Okay, it will go out only in 2023. There was an initial report, but now the working group is working on standardizing it, and we will see it in 2023. It is trying to deliver a much more comprehensive environment, including cybersecurity. So it's both safety and cybersecurity together. And of course, it's in collaboration in SAE. There are SAE partners over there in that work group. So yet to be seen. Now, these are just two examples from what's happening at the process level. Another level is the implementation layer. And this is where ASAM is delivering its own standard. The standards from ASAM are not processes, but they are more formats, languages that you can actually use to connect tool chain and to create different systems, whether it is for simulation, validation, or other. And again, due to the lack of time, I'm not diving too much into all these standards, because I also want to show you some real beef at some point. So with those systems, and to answer, I will start replying some of Axel's questions. We have to distinguish between two terms: simulation and verification. Simulation, you have a lot of issues to tackle them. We've seen some of them in previous presentation, but this is basically you want to model the world accurately, whether it is the sensors, the behavior of the environment, everything. And your key issue there is that there will be good correlation between the simulation and the real world. On the other hand, in the verification layer is a layer that is using simulation. And over there, you need to figure out, what do I want to test? Which scenarios? How can I find the edge cases? How do I cover the test space? In an automated driving system, the test space is basically infinity. How do I cover it to the maximum that I can? And how do I analyze the data in finding out what did I test and what is missing? So I would like to introduce a method that has been used in the chip design world for many years. And to understand it, on this side, we see directed testing. Directed testing is really you write the scenario that you want to test because you believe that they may help you hit a bug or a hazard or a safety issue, and you test them. And of course, some of them will hit, some of them will not hit. This is a very effort-intensive and time-consuming process, and the coverage is very low. Coverage-driven verification is really generating tests automatically using constraints and using randomization. And this is really like you are covering the full space with a given resolution because, as I said, it's an infinite space. And it consumes a lot more compute power. In order to do it, you need massive scale simulation. And this is really the challenge. And you have seen Bolin already mentioning the need for a massive scale simulation. But the idea is that your measurement is how much of the testing space did you cover. And the more you cover, the probability of having issues and hazards and bugs in the rest of the test space is reduced. And to your question, Axel, you don't care whether it is an AI system or whether it is a non-AI system. You look at the system as a black box and you are testing the behavior of the system. Huh? And Again, I will try to accelerate. You can use the data in order to supply the arguments for your test case or a safety case or safety argument. Pick the terminology. Today there was a discussion on what is the right terminology for the safety argument. So this is where I switch to a little bit of marketing. Okay, this is a solution that can be either generic, but luckily enough, Fortelix is providing this solution. And the idea is that in order to cover this huge coverage space, you need some basic technology, and then you need all the standards and systems to support it, and we will see them. So what do you need? You need an ability to describe scenarios. And the ability to describe scenarios should be such that you can describe a large space with a very compact description. And you can, and that means that the scenario is not concrete, but rather an abstract scenario that is representing many scenarios. And you need also a very powerful way to merge and mix scenarios such that you can create test cases that you didn't think about them or the engineer didn't think about them. If you take a library of scenarios and you start to mix them randomly, you create many situations that you didn't think about them. Then you feed in these into a compiler that is actually reading the description, understands what you're trying to do, and generate these scenarios to any of the testing systems that you have. It can inject them into simulation or other testing system, of course, based on the capabilities of that testing systems. And then the last part is you generated many scenarios. You need to analyze the results, to measure them, to identify holes, and to identify gaps that you have there. So this is the basic layer of technology. And here, a word from our sponsor, Fortify is the system from Fortelix that implements this layer of technology. And the language that is used will be released by ASAM next month as Open Scenario 2.0. Which is a major step function above the current open scenario, which is a purely XML representation. The technology layer is not sufficient. You need to have a layer of usability, which should include libraries, catalog, templates, ODDs definition, common test procedures, and the different metrics and safety rating. Now, you may ask yourself, is it coming? So the answer is very simple. Yes, it is coming. It is being evolved by the different regulatory and standardization entity. And that's really the key message that I have here. So UNECE is working on the new assessment and test methods document, as we heard. This one will include a scenario catalog and recommendation on testing methods for virtual testing and assessment. Different regulations are also coming with different thresholds and requirements. You can just look at regulation 157 of ALKS. You will see the specification of the performance that you need to demand. A language, I mentioned already, ASAM Open Scenario 2.0, a very powerful language. That will enable, it's almost like a full programming language, very similar to Python. Just think what you can do with scenarios with the power of Python. Other standards to define the scenario variants and the different processes coming from ISO, and also the ability to describe ODDs in a standardized way. This is coming both from 503, ISAM Open ODD, and J3259. All of these are quite coordinated. And there is ongoing work on setting the metrics and the thresholds that you want to analyze. Now, the major challenge, as I mentioned, is really the correlation, because you rely on massive simulation. Over there is the Pierce Consortium that is working on that. ISO, UTAC-SRAM has already developed the methods to correlate its NCAP models simulation. AVL have their own methodology to correlate simulation. So the layers above this technology are coming, and you can simply utilize them and exercise such a system. And with this, I will move to really a short pragmatic example. SOTIF, in general, is the safety of the intended functionality, ISO 21448. And the ultimate goal there is really to identify unknown hazardous scenario and make sure that they are no longer unknown and no longer hazardous. Okay, that's the goal. So you want to reduce area 3 and area 2, which are the areas of hazardous scenarios. That's the whole methodology behind SOTIF, and SOTIF is articulating a process, steps that you have to go in order to do that, and how to cover area 2, how to cover area 3. Again, no pragmatic implementation. The standard itself is describing the process. The additional 120 pages of appendixes are giving pragmatic examples of how it can be done. So if you apply the CDV approach to that, you simply start to generate scenarios, and then you discover the following things. So here we have a simple scenario where the ego car is here, and this is the expected route. And there is a traffic light here and a traffic light here, and this is a gas station, and we have another player in the scenario. Now, what you do is you start to vary the scenarios, and you create different instantiations. So here is the ego car coming. Okay, and this is just one example of it. And now let's look at the situation that happened here. Okay, it will stop. Now, look at the traffic light at the second junction. It's green. This car is actually crossing the junction in red. Okay, so this is a variation that was created, this combination. And, sorry, okay. So we have this player and we have this traffic light as some strange combination that you wouldn't have necessarily thought about it initially. And now let's see how the ego car will react to this. And what we see is that it is trying to avoid the hazard by going through the gas station. Unfortunately, okay, didn't help. And I think that with that, my time is up, right? Yeah, I had half an hour. As I said, I have tons of slides. I can tell you a lot more about it. But in the presentation itself, I put another example of applying this approach to the ALKS regulation with example of how the language, hey, what's going on here? How the language and the data analysis, never mind. Yeah, how the German and the data, how the data analysis looks. The key message is the technology layer is there, and the system around it are being built. And we do have some approaches to solve your problem of verifying AI.
You don't.
I have one question.
Yeah.
So we see so many simulation tools for testing. And was there ever made a benchmarking, so feeding different tools with the same scenario and look what is the result?
Yeah, so we are in our
the results compares.
No, they don't compare because different simulators have different capabilities.
Oh, yeah,
so for example, let's take two public without getting into commercial comparison. You have Carla and you have Sumo. Yeah, you can fit the exact same scenarios into both simulators. The models inside the driver models are different. The behavior will be different. Okay, now you have to have a good correlation to the model that you are developing. Otherwise, you are just wasting time simulating. You are generating heat. That's it. That's what you are doing. Yeah, so nothing more than that. So now if you're looking into evaluation of different simulations, so Marius Dupois have just established, I think it was like a few months ago, something he calls CertSim, that he is doing evaluation of different simulation. Look for him on LinkedIn, or he may also have a web page with that. Marius invented open scenario and open drive, and
Okay,
okay,
yeah.
so he knows what he's talking about.
One would assume that there is a best practice to validate the simulation.
One would like to assume,
Yeah.
but but there is no.
No.
This comes exactly back to the point why the automotive industry likes at least gray, if not white testing, because we don't trust anything. What is in that black box? We would love to understand what is inside, to define corner cases, to put another level of stress, to find out the final limits. Not only pre-described scenarios, everything may be good, but you may be just 1 millimeter on the side of the problem, which you didn't find. So gray testing would allow you, this is a critical area. Now I implement some other parameters, whatever.
But
and you are on a higher level of testing.
So
That is
I
at
will
least the
very
idea behind.
apologetically, I will say, Axel, that you are thinking like an automotive guy and not
Yes.
like and not like a software guy.
That's true.
Okay, because
100% agree.
yeah. So
Let me try to.
The future is software.
I don't disagree, but where I agree with Axel, or where I kind of go his way. What about error scenarios? What about a blown out tire? What about the loss of engine power? What about the loss of a sensor? When are we going to see that in simulations?
So the language supports that.
Cool. I didn't know that.
Yeah. So now in the language, you can define events and you can feed them or capture them. Now it's a question whether the model of the ADS that you have can respond to that, and whether the simulator can respond to that.
But I didn't know that the ASA, because many of the approaches before that I heard about did not allow for that. So I think it's cool that.
No, again, the language is very powerful. Everything is extendable, and
do you think that will go into required testing?
What the problematic issues? So
I mean, there's corner cases in the use cases, in the child, the red ball, but there is also corner cases.
So it's very hard for me to say, because I think it's also a culture change, and I can demonstrate it by an example from the UNEC. You'll excuse me for another minute. There is a work group that is working on a scenario catalog, and they collected scenarios from various sources. Fortelix also contributed scenarios, and we contributed a scenario where on the highway there is a vehicle driving in front of you against the direction of the traffic, which is
very classical in some.
Well, you may think it's very classical, and indeed the guy from German, Klaus Pastor, said that there are many cases like that in Germany.
Absolutely.
However, there was a debate for a few hours there whether the catalog should include such cases of wrong behavior or things like that.
Well,
So
I can understand. I totally see how that comes about.
yeah, so I think it is a culture change, and the mindset need to be changed.
Okay. Thanks.
Okay, thank you.
I totally agree with you. We have to come together. That's the point. Classic automotive industry with, of course, the software industry. We have to find a language to understand each other. That's one of the key issues.
Okay.
Thank you again, Gil, for the answers to all those questions. And of course, we could continue. So there is one last presentation today, and the presentation will be given by Huai Peng from MCT. So
the video is pinned, so you may need to unpin it. Something right.
Genau.
Which one?
Alle Fenster aufmachen, dann siehst du den. Du hast jetzt nur.
Ah, okay, so you see here. Yeah.
Why, are you there?
I'm here, Axel. I'm
Very good.
ready.
Very good.
All right. So thank you for the invitation, Axel. I'm going to talk about three things. Number one, I think everybody here in this group already know VNV of ADS is critically needed. Second, I want to say quickly about the earlier VNV practice at MCT. Third, the MCT ABC test concept. Next slide. Next slide, please. All right, so obviously USDOT already are seeking comments on how do they regulate the so-called ADS, automated driving system, level 3 to level 5. Next slide. There are a lot of ongoing projects in Europe and Japan that's focusing on the VNV of ADS as well. Next slide. There are German AV regulations in progress. The KBA will be responsible for overseeing a certification process. Next slide. And then China, of course, also are publishing public road testing rules. There will be some approval testing, and then also they are talking about, literally I call those EDR, data collection necessary. And you need to keep the data 90 seconds before any incidents until after. Next slide. So in summary, VNV of ADS is an area of active development in many parts of the world. Next slide. All right, so let me talk about the earlier VNV practice. This is not too different from what many other people were doing in their companies, in the sense that they have a challenge and they need to design something. So we obviously, as a university, what we did is extremely simple, but the basic concept are very similar. Next. All right, so this is what I call pre-ABC test history, and that's because of a project we did deploy Navia shuttles on our campus. Next slide. And the project was between June 18 to December 19. And the testing, of course, happened before June 18. Next slide. And basically, we look at the route, and then we identify key scenario. Next slide, press one more time. All right, so we look at the route, we imagine what may happen there, pedestrian, bicycle, left turn, right turn, and so on and so forth. And then we design routes inside MCT. And then we run the Navia shuttle. We also present some challenges to the Navia shuttle. Next slide. So I don't know whether some of these videos play, but maybe not. If not, it's okay. Basically, the idea is that we actually recruited a lot of students, and yeah, we have measured the RTK. So all the vehicles involved in this test, we have RTK measurement, very accurate, about 1 inch accuracy, and we analyze the results. Next slide. Next, okay, so we don't really have a full failure analysis, but the key failure scenario is the LiDAR is not able to detect small objects such as a traffic cone. So we analyze all the common objects on the road, and we want to make sure that we can detect a small object without jeopardizing the life of a small kid. So we are using traffic cone as a representation. Next slide. Now, after that, of course, we enter the concept page of what is a more rigorous concept of testing level 4 vehicle. Next slide. Okay, so the ABC tests, they all have a meaning. A means accelerated evaluation. One more, B means behavior competence, and C means corner cases. So I will explain how we achieve A and C, but the concept, the backbone of everything is B, the behavior competence. Next slide. So basically, we imagine the whole world, we decompose them or try to cover as much of the real world by the blue ellipse. And each of the blue ellipse is a scenario. And then within each scenario, we try to approximate the full size of the blue ellipse within these test cases. the boundary of the test cases are defined by the ODD. For example, in our deployment, we are only looking at 12 miles per hour top speed. And then we are driving at the neighboring vehicles and pedestrians all have their own behavior. For example, the speed limit is 25 and so on and so forth. So within the ODD, you define how big the red dashed ellipse looks like. And then we try to come up with enough number of test cases within this red ellipse. One more time. And we work with a lot of people, making sure that we are not just coming up with the idea ourselves, rather we talk with a lot of other people. Next slide. This is the library of the MCT scenario library, 50 of them. We know that 50 is not the final number. Obviously, we are going to keep improving the number of the libraries, but here is the current list, 50 scenarios. And we basically argue that we don't want to combine all these complicated multiple factors. We'll test one scenario at a time. Next slide. And our concept is that within every scenario, for example, pedestrian crossing, cutting, left turn, car following, these are the 4 examples. Our suggested approach is we collect naturalistic driving data. Based on the data, we build stochastic models. And then finally, within the stochastic model, we come up with accelerated evaluation framework. And then we try to come up with test cases. And the test cases are divided into easy, medium, hard, different levels of challenges, depending on the control reachability analysis. Next slide. But basically, how we come up with those areas are first, we define the impossible to avoid set, which are the red, and then also possible to avoid set, which is defined in blue. And the blue region is further defined into really the blue, which means the trivial area. Green means easy, yellow means a medium, and orange means hard. Next slide. As an example, this is the pedestrian crosswalk case. So we analyze the behavior of impact between the car with a pedestrian. And when we of course, this is somewhat arbitrary, but someone can define the line between red and orange to be 0.2 second delay and 0.65 braking, and the line between orange and yellow to be 0.4 second delay, 0.41 G braking, and so on and so forth. Again, the line is somewhat arbitrary, so this is a design choice. Next slide. This is another example. This is a cutting example, but basically based on the independent variables, we define the whole region into different areas. Next slide. And then we try to come up with so-called accelerated variation and corner cases. The question is how. Now, if we sample the stochastic model naturalistically, you can see that most of the cases are not in the yellow or orange area. In the meantime, if you are sampling in an accelerated fashion, click one more time, you can see that we can arbitrarily select to sample more from the yellow and orange region. In other words, we will be able to achieve quote unquote accelerated evaluation, meaning we artificially increase the number of hard cases in the orange and the yellow areas. One more time. And so basically the idea is that the behavior competence are the core of ABC test. Accelerated evaluation and corner cases are achieved through intelligent test case parameter selection. As indicated in this region, we will see a lot more challenging cases. Also, the idea that when we are sampling some cases at the very boundary between orange and yellow, red, that's what we mean by corner cases. So corner cases, we don't mean very hard to see in real world, but corner cases in our definition is at the boundary between impossible to avoid crashes and possible to avoid crashes. Next slide. Okay, and we actually gave an MCT ABC demo involving 7 scenarios. One more time, and we will play a video. Next slide.
In this example test loop, an ABC test car will encounter 7 different scenarios in a single loop.
Is the video playing?
Consists of 1. A highway merge. 2. A highway cut-in. 3. An opening door. 4. A deer in the road. 5. A crossing pedestrian. 6. An unprotected left turn. And 7. A roundabout merge. The test loop begins with the highway merge. The test car approaches the highway on an entry ramp. The challenge car remains in the right-hand lane, preventing the test car from immediately merging. A successful test would involve the test vehicle slowing down or coming to a smooth stop before safely merging, preventing the test vehicle from hitting the challenge vehicle. In the second scenario, the highway cut-in, the challenge vehicle approaches the test vehicle from the left and abruptly cuts in front of the test vehicle. A successful test would involve quickly slowing the test vehicle down to avoid hitting the challenge vehicle. Next, for the opening door test, the test vehicle approaches a stationary challenge vehicle from the left. The challenge vehicle's door opens abruptly into the test vehicle's path. A successful test would involve the test vehicle successfully swerving to avoid hitting the open door of the challenge vehicle. The fourth challenge places an obstruction in the form of a deer on a blind curve on the right-hand side of the road, directly in the path of the test vehicle. A successful test would involve the test vehicle slowing down and proceeding cautiously. For the next scenario, the crossing pedestrian, a mobile robotic platform representing a pedestrian abruptly moves onto the street into the path of the test vehicle. A successful test would involve bringing the test vehicle to a smooth stop, preventing the test vehicle from hitting the pedestrian. In the sixth scenario, the unprotected left turn, the test vehicle approaches an intersection. From the opposite direction, the challenge vehicle makes a left turn directly into the path of the test vehicle. A successful test would involve bringing the test vehicle to a smooth stop, preventing the test vehicle from hitting the challenge vehicle. For the final challenge, the roundabout merge, the test vehicle enters a roundabout. As it circles around, the challenge vehicle enters the roundabout, merging suddenly in front of the test vehicle. A successful test would involve the test vehicle slowing down or coming to a smooth stop, allowing the challenge vehicle to safely merge and preventing the test vehicle from hitting the challenge vehicle.
Okay, next slide. I think that's basically my last slide. Thank you, Ansel.
Thank you for your presentation. Are there any questions in the room?
Yeah.
There is.
So
Gil, come
you
closer.
mentioned, I think you can hear me.
Can you?
mentioned that in one of your slides that you pick scenarios within the ODD. So referring to a question that was before, don't you want to test the response outside the ODD? Or if something that is not defined in the ODD is showing up or happening?
No, actually, so let me give you one example, right? When we deployed the driverless shuttles on our campus, our top speed is only 12 miles per hour, and we avoid a lot of left turn. We mostly make right turn only, and then we don't need to test roundabout entrance. We don't need to test steep uphill slope. We don't need to test tunnels and so on and so forth. Obviously not, because our route dictate our ODD, and ODD dictate which scenarios you want to test.
So as a general approach, you would this may work when you have a very given and fixed route, right? but
Or fixed area. If I know I'm in Phoenix, I don't need to test for snow or kangaroo.
yeah, but how about testing for like sign that no left turn when school kids are present or something like that?
Those can be easily programmed into your map. You don't need to test for machine vision, right? Again, I think we certainly believe that it's wrong to imagine the test vehicle is level 5. We should be smart in designing the level 4 for that ODD and only test in that ODD.
Well, I think the point that Gil is making, which is a general problem, is how do you make sure you're not unintentionally leaving your ODD? And what happens if you do? And do you actually recognize that you have unintentionally left the ODD? I think this is where Gil's question goes to, right?
Yeah. So we believe level 4 vehicles will first be deployed at airports for hauling luggage, at seaports to haul the containers, or they are managed local taxis. Top speed is only 30 miles per hour, and so on and so forth. They are managed. They are not just arbitrary. Somebody can just drive it at 60 miles per hour. That shouldn't be the case, because these vehicles are just elevators, right? They were deployed in the places that the companies know where they are deployed. So the ODD must be well defined. Therefore, the designer know how to design them safely. The verification validation guy know how to test them thoroughly.
I think I agree with almost all of that. My question is, I think this problem of, do you now need to deploy cameras in that area that basically monitor the area for compliance with the ODD, question mark. I'm not saying it's the case, but I think there is, it's difficult.
I think what you're saying is that other road users may do something wrong and jeopardize the safety of the level 4.
Let me say, if we assume, let's move away from the campus. Let's say we design a level 4 highway pilot.
But we are not doing that.
Hang on. Give me 2 more sentences here. So I define something that is supposed to be working on a highway in a traffic jam scenario. The problem is now, is a pedestrian that left their car because they got bored in the traffic jam and are now walking around on the highway, is that inside or outside the ODD now?
It is outside. So crash is a 2-party tango. You cannot blend the behavior of the other road user to the ADS, right? So we are only certifying or verification of the behavior competence of the ADS. We are not certifying the safety. Again, because safety is a 2-party tango.
That's the point, yeah. Okay.
We accept that. Even so, in my mind, the question is still working. Is it realistic? In the real world, it's a little different. An ODD is
no. So again, are you certifying safety or are you
I understand
checking behavior competence? That's the question.
In the end, we need a reliable car which is working under all kinds of circumstances, which are probably coming.
Define all kinds. Define all kinds.
Of course, yeah.
Okay.
Okay.
Thank you very much.
Thank you.
Catch-22.
I love these kinds of. Thank you very much. I really love these kinds of disputes because that's what we are living from. This is what the face of the automotive industry is, to understand the software industry. And this is obviously as well the role of standards and normation institutes like IEEE, SAE, to lead us into understanding first each other, and secondly,
to find a compromise which is realistic enough to say it from an automotive perspective, and which is on the other hand possible and can be done with the modern tools. So thank you very much to everyone. It was a real pleasure. Everyone survived this long workshop. The ladies in the back did record everything. So whoever did fall apart is in bed or whatever, he can download the video. It is all available on the IEEE servers. First of all, a big thank you to all the speakers. I know how much time goes in and how much effort all that needs. Some even came from Sweden, for example. And where did you come from, Gil?
This is a stopover.
Okay, it's a stopover. Okay, but coming from America, whatever. So I like this kind of global approach, really.